Ladies and gentlemen, please welcome Stanford University's Dean of the School of Medicine, Dr. Lloyd Minor.
Good morning, and welcome to the 7th Annual Conference on Big Data in Precision Health. For those of you who are visiting Stanford for the first time, welcome. It's not quite as warm as it usually is. We still hope you enjoy yourselves and that you have some time to look around the campus while you're here these next couple of days. I want to begin by thanking the organizers for arranging a magnificent program. Every year it seems like the program gets more and more exciting, and a lot of work goes on behind the scenes in advance of this conference to make it all come together and happen in the way it does. The topics that will be discussed in these next 2 days range from the social determinants of health and the impact that big data has on helping us understand and act proactively on those determinants, to how we can use machine learning and other analytic techniques to improve the drug discovery process. Truly covering the gamut of issues related to precision health and biomedicine. This is a really exciting time in data science, artificial intelligence, machine learning. I don't think that any of us 7 years ago quite envisioned, when we started this conference, now in its 7th year, when we quite envisioned the way in which the fields related to data science, would evolve over such a short period of time. But we're seeing it, and the pace of that increase in activity is not diminishing in the least. And I think you'll see the impact of applying analytic techniques, applying machine learning, artificial intelligence to problems in biomedicine. You'll be able to get a glimpse of that impact during these next 2 days. It's now my pleasure to welcome to the stage for a fireside chat Dr. Ewan Ashley. Ewan is a professor of medicine, genetics, and biomedical data science, and he's also an associate dean in the School of Medicine. Ewan?
Hey.
Welcome.
Nice to see you. Thank you.
So it's hard to believe the 7th one of these.
Kind of amazing, actually. Yeah.
It is.
Time just goes by so quickly.
It really does. Yeah. So as you look over these past conferences and also your career, which is very much involved with the issues that are going to be discussed here the next 2 days as one of the leaders in this field, what's changed? What are you excited about today, and what are you excited about looking forward?
Yeah. Well, you know, the data hasn't gotten any smaller. That's the biggest. That's the most important thing. First of all, it just keeps coming. I mean, I was looking this up this morning just on the way in. You know, the internet in the early 1990s was 100 gigabytes. That was the traffic in one day on the internet. And now, I mean, you can buy a USB stick that can hold 100 gigabytes of data. We're talking about something like 150,000 gigabytes of data per second passes the internet, and most of that is 80% of it or so is video. So the size of the data is enormous. We're also more connected. You know, when this conference started, I think Facebook had about 1 billion users, and we thought that was enormous. And you know, they've been sitting at 2.5 billion for the last several years. Also, the smartphones, so many more. We've been buying something like 1.5 billion smartphones per year for the last few years. So I think the world has changed in very many significant ways where you know, there's a lot more data, there's a lot more data flow, the volume, variety, velocity of it that we used to talk about in the early days of the conference certainly hasn't changed. It's gotten larger. And if we think about even specifically in the biomedical domain, and my domain, thinking about genomics, we used to think of having 100 individuals and having a few genes sequenced for them was a great control data set when we were trying to interpret clinical testing. And around the time this conference started, there was a database of maybe 5,000 individuals, and we thought that was huge. And now we're worried because 100,000, 150,000 exomes in the NOMAD database isn't large enough. And we're looking forward to the day when we might have 1 million, because I think, as you mentioned in your opening remarks, we have this opportunity to really lean on the whole population, to think about the population, to measure the population, but to then bring that to bear on a single individual and try to make the care of a single individual better. And then the last thing I was going to say about the change, I mean, this sort of second revolution, or the second coming at least, of artificial intelligence has been just such an amazing impact. I mean, for many, of course, including for the Turing Award winners this year, they never went away. They've been working on this since the 1980s. But really, it was probably with our own Fei-Fei Li in the ImageNet competition that she was putting together in the late 2000s. And the really big jump forward, probably with GPU computing in 2012, was what really launched, I think, the second coming of AI that has really started to impact biomedicine and well beyond, as we see in our lives around us. So.
Right. And you're involved here at Stanford in all of the data science-related initiatives. You're involved in the Human-Centered AI Institutes being formed. You're also involved in the data science initiative and in looking broadly speaking at our computational resources. How do you see things coming together here at Stanford, and what are you looking forward to in the next 3 to 5 years of how we'll be able to have even more impact than we've been able to have in the past?
Yeah. Well, it's been such a privilege to be involved with all these incredibly talented staff and faculty and students here. Just an amazing honor. It's very exciting to have launched the new Human-Centered AI Institute with John Etchemendy and Fei-Fei Li at the head. Bill Gates was here a few weeks ago, and that was part of the launch, the governor of California as well, and many others. I think that encompasses so much of what we're excited about, especially here in the School of Medicine, and the idea of artificial intelligence as an augmenter to humanity, and thinking of humanity at the very center of what artificial intelligence can do. And I think that looking forward, that's one of the things I'm most excited about. I think is not just thinking about what AI can do for us, which is where I think we are today. We have lots of examples in biomedicine of where an AI can learn from humans and then essentially mimic them and do well. But I think what we want to do, and something that we're really excited to do here at Stanford Medicine, is to really put the AI back in to practice. Put the AI in with the human, and in our case, with the patient, and then have them interact together. And I think that then the thing that I'm really excited about is to see what happens, because the human will start to adapt to the AI. I mean, our aim is to try and keep the AI out of the way so that the humans can really interact closely. But then as the human adapts to the AI will start to adapt to the human, and I think there will be a virtuous circle where we learn a coexistence, where the human is better because of the AI, and the AI gets better minute by minute, year on year, because it's learning from the human. So that's one of the things I'm really most excited about for the next few years of where we might go.
That's great. If we fast forward to 7 years from now, so we're back here in this room for the 14th annual conference, what will we have accomplished in terms of what we should accomplish in the next 7 years? What are your hopes?
Yeah. Well, I think that one of the things that we haven't yet really managed to achieve is proper integration of the various data streams that we have. And I think that we've been working on that, and we have a lot of work to do. If we think of it in the context of healthcare, of course, or specifically in the hospital, we're surrounded by data. We have data from the monitors, data from the electronic health record systems, the data from our own interactions with the patients, taking their pulse, listening to their heart. And I think that what we have done less well to date is really bring that data into one place in a way that can then be integrated so that we can compute across it. And that could be human computation, it could be AI-type computation. But I think integrating those data streams, which means bringing them together and making them consistent, putting them in a computable form, is really one of the challenges. I think if we can do that, then we really will be able to make another giant leap forward, which might take us somewhere really quite interesting in 7 years. The other thing that I would really love to see, and I think all of us have wrestled with this, is how to deal with that medical record data. And I think we might see a change. I mean, perhaps people have been saying this every 5 years for, I don't know, decades. But I'm really excited by the idea of the large tech companies being so interested in healthcare. And I think that they really understand computation. They really understand data. And I think that we can't help but do a little bit better if they're involved. I think that we might move away from there being certain structures in place that we've been stuck with for many, many years and move towards more of a data model. Because if we have a data model, how we describe the healthcare data that we're so interested in, then people can build to that. The big tech companies can do it, the old style companies can do it, anybody can do it. And I think that we want to move to a situation where the data is in the hands of the patient. And if it's in a structured data model, then it can be on their iPhone, it can be in the Amazon cloud, it can be on the Google cloud, the Google AI can compute on it. The things that the tech companies do better than anyone else can be brought to bear. So I would hope that in the next 5 or 7 years, we might be able to get to some of those challenges.
Indeed. You mentioned the electronic health record, and that gives us an opportunity to put in a plug for, we'll be hosting our second conference on the electronic health record coming up this fall. We had the first conference in June of 2018, and it was well received, and so we'll have the sequel to it, really to maintain a focus on just what you were saying, interoperability of electronic health records, as well as making them more user-friendly and more adaptable to the needs of the practice environment and the needs of the patients we serve. Yeah. What do you think are the biggest impediments to bringing the data? It seems like, just as you were mentioning, that the pace of AI, machine learning, as applied to areas of biomedicine, precision health, that pace is not being restricted by algorithm development or analytical prowess or computational power. Right. I mean, all of those have progressed enormously in the past, even the past 5 years. Yeah. But the pace is really being slowed because we don't have the data streams that are needed to take advantage of the power that exists in other sectors. So what do we need to do to either generate the data or make the data more available for the types of analytic methods that you just discussed?
Yeah, I think that we do have to wrestle, and we've been wrestling with it, but we haven't really wrestled it to the ground yet with the real challenge of privacy. And I think that, when we started this conference, we talked a lot about learning from Facebook and the fact that the next generation of kids and teenagers and millennials were so willing to share all their data. Fast forward to 2019, we're in a slightly different situation.
Yes.
We've seen that kind of sharing weaponized against us. I mean, in democracy around the world, and people are naturally now much more uncertain, I think, about sharing, and uncertain about what an algorithm can learn about them. But in healthcare, I think that we've respected the privacy of individuals and had rules and regulations around that forever. So I think in many ways we may be in a better situation to ride this wave, really just by applying the rules, applying the philosophies that we've used for some time. So I think that we have to work together within a healthcare scenario and even outside to try and really be transparent about when people are sharing data, where we're going to store it, how we're going to store it, how it's going to be secure, what is going to be, what the processes we'll put around it to make sure that they cannot be traced if they don't want to be traced and they don't want to be identified. So I think that's one of the real challenges. Another one is that I think we've all been so impressed with AI and what it can do, but I think we mustn't forget that for the most part, AI systems are learning from humans, and humans have an inherent bias. And so human data streams, or data streams that have been annotated by humans, shared by humans, have their own inherent gender bias, racial bias, and many other biases too. Yeah. If our AIs are learning from that human data set, then they're going to inherit those biases. Yeah. And so just as we work against bias in the human society, we also have to be aware of working against it, I think, in an AI world. So I think those are probably two of the areas that we really need to wrestle with over the course of the next few years if we're really going to make the most of the opportunity here.
Great. Just to finish up, one last question. You mentioned a goal that I certainly resonates with me, and that is, how do we get an individual's data in her or his hands? Yeah. And then how is it meaningful? What do we as healthcare professionals, physicians, need to be doing to accelerate that process? How can we help to make the data that we're interacting with every day on our patients, how can we make that more meaningful for the people who really should and actually do own the data, and that is our patients?
Yeah. Well, I think definitely on two levels. I mean, first of all, we are our own healthcare system, so we have to look after and prove that we can do this on our own patients first. Yeah. And so I think putting processes in place in the healthcare side to make sure that patients don't have to go down 3 flights of stairs and then go to some dusty records place and request something that takes a week to come and then comes on a CD drive or like a huge stack of papers. I think we have put in places here, systems that people can have their records shared through the FHIR protocol, for example, into their cell phone in their hand. So we need to start there. But I then think we have a responsibility as Stanford and in Silicon Valley to help try and show the world how to do that and really push other healthcare systems into the same place so that people can finally have their own data in their own hands to do with what they want.
Great. Ewan, thank you. You've been an instrumental force from the beginning in this conference, and I really appreciate the great work you're doing for us, with us, and we'll look forward to every year, but in particular 7 years from now.
Yeah.
Take care.
Thank you so much.
Thank you. Thank you.
Right. So how's everybody doing? Come on, some energy, guys. Good morning. All right. So it's a great pleasure to kick off our session with the keynote by Jeff Dean. Jeff Dean knows, everybody knows Jeff Dean in the tech audience. For those of you who are from the medical side, Jeff is a legend in the technical community. The New Yorker just ran a very nice article about him on how he and his close friend Sanjay Ghemawat built Google and essentially built the rocket engine, as they call it, that makes the company what it is. It's a fabulous read. I have the privilege of calling him a co-author, which is fabulous. Someday there'll be a Jeff Dean number, just like we have the Erdos number in mathematics. And today he's going to talk to us about his ideas around how AI and machine learning can improve healthcare. As many of you know, that Stanford has a partnership with Google. I don't know whether he'll talk about it or not. So without further ado, let's have Jeff on stage. And welcome, Jeff Dean.
Thank you. Good morning. Wow, it's bright up here. So I'm going to be talking to you today about the potential of using AI in many different aspects of healthcare, making people healthy. And I'm presenting work that represents the work of many, many people across Google. This is not all my work, but I'm very privileged to present work that we're doing in a broad set of areas. So first, why is now the right time to apply machine learning and AI to problems in healthcare? Second, I'll talk about what are some of the things that we're actually doing in the space. And given what we've been learning, I'd like to share some high-level lessons about things that happen when you do this. So first, why healthcare? I think one of the things that was touched on in the conversation is we've seen real advances in how machine learning can be used to tackle different real-world problems. So for example, in image recognition, we've seen dramatic improvements in the capabilities of computer systems to recognize images, to segment images, to identify interesting bits of images, purely from learning from large labeled data sets. So if you look at the Stanford ImageNet Challenge, which is a computer vision contest hosted every year, in 2011, the winner did not use a technique called deep neural networks. And that was the last year that the winner did not do that, and they got 26% error on this challenge. And then every year after that, people have used deep neural networks and machine learning approaches based on those to get better and better results. And we're now down at around 3% error for the winner in 2016, which is just a fundamental shift in how you think about computers being able to see things. They basically couldn't see before in 2011. Now we can actually see. And human error on this task is about 5%. And translation has improved dramatically. More computational power has really helped these methods so that we can use these approaches on larger data sets, get results more quickly, and so on. And we've actually taken these advances and then put them to use both by writing research papers that advance the state of the art of machine learning, but also putting them into our products that are used by billions of people. So it's more than just writing papers. We actually use the results here. So now in Google Photos, for example, we can actually understand These are your pictures of mountains. So if you search for mountains, we can find you your photos of those. In Gmail, we can help suggest replies to emails you might have received based on the contents of the message. Can you come over for dinner? Sure, we'd love to. What can we bring? Or sorry, we can't make it. These kinds of things. And so when we looked around at what other areas were now potentially tractable for some of these kinds of approaches, lots and lots of problems in healthcare sort of struck us as amenable to these sorts of techniques. And so I'll just give you a brief tour of some of the areas that we're working on and just give you some results that have happened. So I'm going to classify them into 3 different areas. One is discoveries in basic sciences. Another is improving care and efficiency of delivery of healthcare, primarily in healthcare systems. And then scaling specialist expertise to make it more accessible. I'll just give one example of discoveries in the basic sciences. The cost of genomic data has dropped dramatically. The cost of sequencing a human genome now is a few $100s, whereas it used to be tens of thousands or even millions of dollars for the first few genomes that we sequenced. And that has led to this explosion of genomic data. And one of the reasons these advances have happened is that the modern generation sequencers break things into very short sequences of base pairs, 30, 50, or 100 base pairs, and fragment the genome, and then you get raw read data off these sequencers, and now you have to align it and then try to reconstruct the contents of the entire genome from these short 100 genome fragments. And it turns out if you do this, you can recast this approach as a deep learning problem. So if you kind of take all the different reads that overlap a particular area and pile them up as an image, as you see on the right here, then what you find is that you can very quickly see that there's different visual characteristics of different kinds of things that you want to understand in the raw data. For example, the top thing has an actual mutation at a particular position, whereas the bottom thing is caused by sequencing errors, where every time you read one of these base pairs, you have a very tiny chance of reading the wrong letter. And those look very visually distinct, and these deep learning models are actually able to pick up on these distinctions and do a better job of variant calling than other approaches that sort of try to hand analyze this with more simpler statistical methods. And what you see is that it actually works quite well. So this is sort of the total errors, false positives and false negatives, for a variety of different approaches. The 2 on the left are the earlier, more traditional kind of statistical-based approaches, and the 2 on the right are various forms of the deep variant algorithm. And obviously, since this is the very first stage in genomic processing, having fewer errors here means that all downstream uses of genomic data will be improved if we can reduce the sort of errors at this stage. And one of the things you see is that the error rate is actually going down as we improve the software. And the other nice property that this approach has is it's very amenable to training on different sequencing machines. Before, the statistical models are very calibrated to the exact model of the sequencing machine. But this, you can just retrain the data with new data coming off a different kind of sequencing machine and get good results. OK. So one of the great explosions in the last decade is that most healthcare records, in the US at least, are now in electronic form. And that presents a great opportunity. I think we've sort of underutilized the data that is in medical records to help us make better care decisions. So could we use machine learning to analyze the entire medical record and get useful insights from it? And there are a bunch of kind of clinical models that people put in practice for various things, predicting mortality risk, predicting the risk of sepsis, these kinds of things. And most of those variables are actually quite simple. They use very simple, small number of variables that are often sort of high-level summary features extracted from a patient's state, and then a very simple kind of statistical model. But if you look at the actual raw medical record data, most medical records have 100,000, 150,000, 200,000 data points, including textual notes, other kinds of things. So could we use all that data to make better decisions? We published this paper the very beginning of 2018. And there were two major insights. First, if you take all the data in the medical record and you essentially line it up on a timeline, including all the notes, the lab results, we ordered these labs at 3 a.m., 7 a.m., we got the lab results back, and the score for this was 73, and we got a 54 for some other thing, and you treat that as a longitudinal sequence, that gives you this really nice, rich longitudinal record. And then you can apply deep learning techniques that are really good at sequential processing of long time series data. And that can also handle things like the clinician's raw notes, things like that. So in collaboration with actually Stanford, UCSF, and University of Chicago researchers at those medical institutions, we tried this approach on different collections of de-identified medical records. And what we found is that essentially you get all this raw data, and you can use that data for doing this. Each dot is a FIRE resource, and then you can predict a bunch of interesting things with the same underlying model architecture. So you can predict things like, what is the length of stay of this patient that's checking into the hospital? What is the likely length of stay? Do they need a particular kind of nursing facility? Are they likely to be readmitted if I allow them to check out of the hospital now? Are they likely to develop diabetes in the next 12 months? So kind of population health kinds of questions. And we came up with several different model architectures. The details aren't important. The second one is interesting in that it mentions attention, so I'll come back to that in a moment. But these approaches actually work quite well. And so, for example, for a bunch of different kinds of categories of things you care about predicting, for example, you might want to predict risk of mortality. If you have a better prediction of the risk of mortality, that enables clinicians to really focus their medical attention on the patients who are most at risk. And really, if you have more advanced warning of that, clinicians can focus their attention in appropriate manners. Things like resource utilization metrics, like length of stay, you can actually predict better, standard readmissions, and so on. One thing you can actually do that's kind of interesting, we haven't been able to find current clinical models that do this, is you can take all the data for a patient up to the point at which they're being discharged. And then these models can actually predict all the discharge codes for the patient with fairly high accuracy, which is good because you could expect all that information to be there in some form in the medical record. And one of the things, I mentioned this model that uses attention. So obviously, one of the things that will help is if these models can be more interpretable to clinicians. So, and one of the techniques we use is a system that uses attention so that it can show you what part of the medical record it's paying attention to when it's making a prediction of a particular kind of thing. And here, what you see is that this is a patient that the existing clinical model predicted to have fairly low risk of mortality, but this model predicted fairly high risk of mortality. And it picked up on this term PLEURX, which my medical colleagues tell me is a particular kind of catheter that you insert for a sort of incurable catheter issue. It's a sign that you're basically very near your end of life. And we're able to actually show that the model can pick up on this and show you why it's predicting a high risk of mortality. OK. Another thing that we would like to be able to do is to use machine learning to take the skills that the world's best experts in particular areas have and make those skills more accessible to people all around the world. And I will give you a couple of examples. One is in the area of diabetic retinopathy. So diabetic retinopathy is a degenerative eye disease where if you have diabetes, you really should be screened every year for this disease. And if you catch it in time, it's very treatable. But if you don't, you can suffer full or partial vision loss before you actually get treated. It's the fastest growing cause of preventable blindness in the world, and screening can prevent this blindness. But it's very specialized. You need very specialized training, an ophthalmologist level of training at least. And for example, in India, there's a shortage of more than 100,000 eye doctors, and therefore 45% of patients lose vision before diagnosis. And this is incredibly tragic because it's entirely preventable if we were able to screen people at the appropriate frequency. And so it turns out the computer vision models we're using to detect is something a mountain or a German shepherd. You can actually collect training data of retinal images and then opinions of ophthalmologists of whether that is, a 1, 2, 3, 4, or 5 on this 5-point scale, and assess using the same underlying model architecture trained on retinal images, give a grade of 1, 2, 3, 4, 5 to a new retinal image. And this turns out to work actually reasonably well. So if you get every image labeled by a number of ophthalmologists and use the average score to train the model, you actually get a model that is basically as accurate, slightly more accurate than the average US board-certified ophthalmologist at this task. And it's something that can now run on a computer and do 50 or 100 images per second on a desktop computer with a GPU card. And in parallel with this, we're also extending to other eye diseases and other modalities of data. So our colleagues at DeepMind are using OCT sort of 3D imaging of retinas to assess about 50 other eye diseases in this article published in Nature Medicine. And we want to do more than just publish papers. So we're actually have this system deployed in a network of Indian eye hospitals. We're actually working with the Ministry of Health in Thailand and are doing clinical trials in Thailand using this approach to treat patients in Thailand or diagnose patients. Okay. Radiology and lung cancer screening is another important area. So if lung cancer is sort of the leading cause of cancer death in the world. So it's a really serious problem. And we know that if you are able to detect cancer earlier, lung cancer earlier, patients' chances of survival go up dramatically, 5 times higher than if you detect it in late-stage cancer. But screening is really hard because the only effective screening technique is with computer CT scans. And these create hundreds of images. It's sort of a volume of images for radiologists to review. And early-stage cancers are really, really subtle in that they often are very small. They're only showing up on one of these hundreds of images. And radiologists can sometimes miss these screens, these early signs of cancer. So in work published on Monday, we've been able to show that we can outperform the average radiologist at detecting these cancers, particularly for earlier stage cancers. And there you see the ROC curve. It's better to be in the upper left of those graphs. So farther up and to the left is good. And there you see the comparison to individual readers rather than just the averages you see on the right, on the left. So let's look at what this looks like on a single case. If we can roll the video. Yeah, so this is the initial scan, and it turns out in this particular patient, they had an early stage cancer that was missed by the radiologist. And then they came back a year later and found a fairly late stage cancer that the radiologist did detect. And here's the initial scan with this algorithm, which highlights a very subtle thing that is obviously very easy to miss on this particular case. And so that, I think, is the real promise. You could offer lung cancer screening as a sort of general protocol and try to detect lung cancer screens earlier. Pathology is another example of things that are going well, basically because medical imaging, computer vision has made such strides. All of these areas are sort of showing great promise. So diagnosis and pathology is obviously hard. There's both the problem of underdiagnosis and overdiagnosis. And basically, these images in pathology are actually very high resolution, so they're 100,000 by 100,000 pixels. And you're looking for essentially a needle in that very large haystack. And what we found is that training a model on images where pathologists have actually circled particularly malignancies in those images, you can actually train models and actually find that the model outperforms pathologists given unlimited time, and given more time constraints as pathologists normally face, it significantly outperforms it. And we've built a prototype of this system that uses this model in real time on a conventional microscope. So as you move the slide around on the stage, it can actually, using mirrors, get access to the image that the pathologist is seeing, and then overlay an image of showing particular interesting points that the pathologist should pay attention to. And this is important because most of the world is still using conventional microscopes rather than digital pathology. And we're doing a bunch of other things. I'm not going to have time to go into them. One thing we've been examining is how well do sort of machine learning-based systems and conventional sort of pathologists interact and work together to make decisions. And what we found on this paper on the left is that pathologists take less time to make more correct decisions when they're paired with a system that is giving them kind of what you saw in the microscope, visual guidance of what things are interesting to look at and so on. And they also feel like the cases are easier to evaluate, so they're less stressed about it. Deep learning can help with drug discovery. We have a system that can dramatically accelerate by about 300,000 times the ability of computers to do simulations of what happens when you have these two molecules. Do they bind together or not? It can help with radiotherapy planning using different kinds of machine learning models. OK, so a few lessons of things that we've learned along the way. First, it's really important to pay attention to how messy the real world is. And I'll draw attention to this chart from the diabetic retinopathy work. So each row here is a patient image, one of those retinal images. And each column here is a different ophthalmologist grading those images with colors of the grade that they assigned. So if everything was consistent, you'd expect a uniform color on each row. And what you see is, obviously, I don't need to tell this to this audience, opinions vary across different physicians. And in fact, the agreement between two different ophthalmologists grading the same image is 60% on the score 1, 2, 3, 4, 5. Slightly more worrying, though, is that the agreement between the same ophthalmologist grading the same image a few hours later is only 65%, which is slightly terrifying because the difference between a 2 and a 3 is like, go away and come back in a year versus we better get you into the clinic Monday morning. And so we had every image in that study graded by 7 ophthalmologists in order to reduce the variance in the labeled images. One thing we wanted to do, though, is actually make even better models. And so we both found that we could get retinal specialists who were more accurate at assessing this because they have extra training in assessing diabetic retinopathy, but also changed the protocol by which we label the training data. So instead of getting a bunch of independent assessments by retinal specialists or ophthalmologists, we instead sort of lock them in a room and say, OK, you 3 retinal specialists need to come to an agreement of what score you think this image should have. And with an adjudicated protocol using 3 retinal specialists, we actually found that we could then train the model, same sort of underlying model architecture, on this better labeled training data, and get a model that is now on par with retinal specialists, which are much rarer in the world. So you'd like sort of the gold standard of care. You'd like that expertise to be used everywhere. And with this approach, we found that we can actually sort of get a model that is on par with retinal specialists at doing this task. Ewan actually touched on this. Often you're training on data that is representative of the world as it is, not necessarily the world as you'd like it to be. And so we've done some amount of work in this. This is not a solved problem, but how can you, for example, change machine learning algorithms to take account of some kinds of biases that are present in the raw data that you're training on? So we have an article there, Ensuring Fairness in Machine Learning to Advance Health Equity. Another interesting thing is in the third article there, when that paper was submitted, they suggested that that perhaps the data set was not representative of other data sets of retinal images. And so they asked the authors of the paper to evaluate it on a completely different data set. I think the original was using North American retinal images from a US healthcare system, and they asked them to evaluate it on a Thai data set of retinal images. And what they found was that the results there transferred quite well. So there wasn't any sort of worry about that. But it was a nice thing that the review process sort of injected that extra scrutiny. OK. And the other thing that's kind of interesting is we're now, all the things I've told you are things that clinicians already do. But what if we told you that you could see new kinds of information using a machine learning model in things like retinal images? So in particular, one thing we've found that we're able to do is predict cardiovascular risk from a retinal image to the same level of accuracy that you would normally get with a more invasive blood test. So you draw blood, send it off to the lab, 24 hours, you'd get results back. Instead, we can get that same level of cardiovascular risk assessment from a retinal image. And this is sort of interesting because if you ask an ophthalmologist to do this, one of the one of the subcomponents of this that you'd like to predict, this is sort of came about from a bit of a science experiment. Someone new joined the team, and in order to help them figure out how to use this training software pipeline, the leader of the team, Lily Peng, said, oh, why don't you try to predict a self-reported sex from this data set where we actually have retinal images and sex and age. And since ophthalmologists can't do this, she thought the AUC on this task should be 0.5, but at least they'd be able to train a model from end to end. And so they went away, and a few days later they came back, and the AUC that they reported was 0.7. And Lily said, no, that can't be right. Go check everything and come back. And so they came back, and they said, I fiddled with a few things, and now it's 0.8. And so that got people thinking, what could we see in a retinal image that perhaps we didn't know we could see? And if you ask an ophthalmologist to do this, they're like, I don't know, it's no better than flipping a coin, basically. And so I think this is the real potential, is are there signals and signs that we, as humans, can't see because we've only seen, 5,000, 10,000 images, retinal images in our lifetime, but in 100,000 or 1 million, maybe we could see more. And maybe you'll start to collect retinal images as part of your longitudinal health record. Another example is predicting stains. So normally when you're doing microscopy and you want to stain something, you actually put physical stain on the slide, and that often kills whatever you're trying to look at. But what we've been able to do is train a model that can predict the effects of stain without actually staining it. And so that allows you to get longitudinal kind of time series things of, how does this thing develop over time. And that's pretty nice as well. OK, so this is a rather broad summary of a bunch of work. We're doing lots of other things in this space, but we really think that there's real potential for AI to make new things feasible. And in particular in healthcare, the potential exists to improve the health of billions of people. Can we use all the collected human decision-making in healthcare to improve the next healthcare decision that is made by a doctor or a clinician? So that's what I'm excited about. And I think Nigam and I are now going to chat.
All right, so thank you for that sweeping tour of all of the work that you're up to. So we can sit down, and I'll kick off with a couple of questions. Being able to classify and predict is kind of a given. I mean, Google and many other companies, they've just demonstrated that hands down. How do you see us going into the clinic with these models and impacting workflows that improve care? What are your thoughts around the right modalities to experiment with that? Yeah, so I think, for some things like a diagnostic tool, it's relatively simple because you can sort of say, okay, I have a radiology image, and there's a radiologist who's going to look at that. One very simple way to inject that is to say, let's just give the radiologist access to an instant second opinion or sort of visual highlights about what the model thinks are interesting bits of the radiological data to look at. For other things like the medical records prediction task, I think there's many different ways to use that. So for example,
if you have a patient sitting in front of you, what are the 5 most likely diagnoses that might make sense for this? And then I think, it might be that 98% chance it's the thing the clinician is thinking about themselves, might be the second thing is a 1% chance of this rare thing that individual clinician has never actually encountered at all. And at that point, I think you then want tools that enable the clinician to go off and investigate, other similar cases, find out more about what if I treat it this way, what does that do to the likelihood of them coming back to the hospital in the next week versus this other, alternative treatment. And so I think it's going to be a more interactive tool for some of these kinds of deployments, and I think that's interesting and has UI challenges and all kinds of things.
All right, well, thank you. I'll do one more question. A lot of these, the training of these algorithms requires massive amounts of label training data. And up till now, because it's all experimental, we have 7 experts and 5 experts labeling things. What are your thoughts on how can we as a discipline get a cheaper source of labels?
Yeah, I think one of the things is that if you look at the totality of medical data in the world, there actually is a lot of labeled medical data from past patient histories and so on. And I think there's very real privacy concerns about how do you actually make use of that data. But for example, we've developed a technique called federated learning, which is what we use to train models on hundreds of millions of phones so that when new words come into existence in the vocabulary, the sort of vernacular of modern society, you don't have to type that new word on your keyboard in order for your keyboard to get smarter about it. But we don't want to send the raw keystrokes of everyone to a centralized location to train these models. So instead, we can train models collectively on the typing on all these hundreds of millions of phones in order to actually improve the model for everyone. And we ship the model parameters, but not any of the raw data. And so I think that kind of approach in healthcare systems could be, or even across healthcare systems, could be an interesting approach to getting more data for these problems.
Fascinating. We'll open it up to audience questions. There's a couple of microphones, I think 2 in both aisles. And while you formulate your question, please come up to the microphone. Actually, I already saw one hand up. I'll ask one sort of final question before we have somebody at the microphones. Okay. In healthcare, there's this known fact that there's a huge skew in the cost, in the sense that a very small fraction of people are responsible or result in a lot of resources needed for their care. How do you see the use of AI help balance out the cost of care?
Right. I think the right way to view this is the goal should be how can we get everyone healthier, right? And if you take the people who are currently very, very sick and consuming a large healthcare burden on the costs side, if you get them a little bit healthier, their costs will go down dramatically. And if you get people who are sort of in that intermediate band healthier, they themselves will consume less costs. So I think moving everyone a level up in terms of healthiness through behavioral change, other kinds of things, is probably the most likely way to reduce costs.
All right. And I think we have a first question here.
Hello, it's Barbara Roth, Vienna Vaccine Safety Initiative. I just had a question. How do you grapple with the data that we physicians never capture? I think the biggest bias is our own view of our patients and the preconceived notion of what we expect to find.
Yeah. So obviously, I think if we can, the medical record, as an example, is a very weak summary of what has actually transpired in the treatment of a patient, right? You've had a lengthy conversation with the patient, and that gets digested into a 20-word note. And I think that is a problem, right? If we could capture richer data about these interactions and decision-making processes, that would be good. But on the other hand, clinicians currently really don't like interacting with the medical record system because it's painful even to get that 20-word note and all the codes you need to fill in and whatever. And so I think AI and machine learning can really help here as well. So one of the experiments we're doing is, can we have a system that listens in on a conversation between a doctor and a patient with consent, and then can give you a transcript of what has occurred, and then give you a draft of the medical note that you might like to put in there, and also perhaps give the patient a summary of the conversation in maybe different language than what the clinician would use in the medical note. I think that's where we could go, because then you actually have the raw data in richer form if you need it, but you also reduce the burden of clinicians to spend a lot of time after hours typing medical notes into the medical record system.
All right, we'll go to the question in the back.
I'm just a reaction to that. I think it would be absolutely brilliant if Google could fix the electronic medical record problem. That would be a huge contribution. Obviously, I come from the medical side, not the tech side. So this may seem like a naive comment, but it seems to me that there are areas where precision matters a great deal, and there are areas where sort of general forecasting is okay. Like, and I mean no offense by this, but Google knows that I'm really passionate about luggage and penguins, but it still thinks that I'm a 70-year-old man, and I get some really weird prostate ads as a consequence. and that really doesn't matter, because I can ignore that. Right. But similarly in medicine, there are going to be some areas where precision is really important, such as the retinopathy prediction, and then some other areas where you can afford to be kind of, slightly hand-waving in the general direction. And it seems to me that that must present a very big challenge when it comes to what you referred to in the beginning, integrating very large numbers of data points that span the lifespan and all types of patients and all comers. And maybe you could talk more about how you target that, or how you refine the goals of what really matters.
Sure. So in the medical records work, for example, that is you training a single model with a large capacity to remember key aspects of many de-identified medical records that it was trained on. But we don't train a separate model for a 77-year-old man versus it's one large model. I think the more general point, though, is that many of the decisions we're making in medicine and healthcare are much more consequential than what ad should we show you. And so that means that the way in which these models are actually put into practice has to be much more thoughtful and careful and methodical, as kind of, as is appropriate. And so most of what we're doing initially is how can we give instant second opinions to existing clinicians in the way in which they're already accustomed to working, so that they can, get a quick oversight of maybe they missed something and this system picked up on something that they missed, rather than sort of replacing what they're doing with a machine learning algorithm by itself.
All right, we'll go to Marza here.
Hi, my question is, at the beginning, you noted that one of the reasons that computer vision has really made fantastic advances is that we have these large open data sets that people all over the world can benchmark their latest machine learning algorithm on. It's what we make all our students do, right, every year. How is Google going to help move the progress of research in this space forward with data sets that are currently not available to most researchers?
Yeah, I think the problem of accessibility for medical data for open research is actually a pretty significant one, because often it's the patient's data at heart. And I think one way we could make progress is to encourage patients to share aspects of their medical records for research purposes with their consent. At the moment, medical researchers can sometimes get access to de-identified or anonymized versions of data sets, but that's a bit haphazard, and it often means that people are working on different data sets for similar kinds of approaches to solving problems, and then you can't really compare the results. So I agree with you, it would be nice if there were more standardized data sets. So for example, the medical record space, there's a relatively small one called MIMIC that is used for all kinds of medical records research, but it's really small enough that it isn't necessarily representative of what real-world sort of healthcare system medical record data sets look like. But I think there's no easy answer here, because the data is much more sensitive than a bunch of pictures of cats and dogs.
So I'm going to jump in as moderator just a little bit. There's the availability issue, and then there's also the trust issue. In healthcare, there's been numerous polls that show that as an individual, We don't trust the government with our data. We don't trust insurance companies with our data. We don't trust the tech companies with our data. We don't trust our hospitals with our data. But then we still want to benefit from the application of machine learning. So that's a really problematic catch-22, and I'm sure you've spent a lot of time thinking about this. So would you share your thoughts about that?
Yeah, I mean, privacy and healthcare data is a very, very broad-ranging and complex topic, and regulatory issues that span countries and so on also are complex in this space. So I think if you set that aside, the opportunity in front of us, if we can figure out how best to do it in a way that has appropriate privacy guarantees, is we would like every healthcare decision that's been made in the past to be used to inform future healthcare decisions, right? That's like a good aspirational goal. And how can we find ways to make that as close to possible as we can? And things like federated learning, things like maybe automated ways of de-identifying or anonymizing data sets, things like this can push in that direction. But it's definitely a challenging problem.
All right, I think this aisle back and then over here.
Partha Bhattacharya, National Institute on Aging. So I have a question which delves into the data. It's a follow-up on the data question. How do we deal with integrating AI or machine learning approaches in clinical care when we do not have all the data? It's missing data, right? And what do we need to do to take advantage of the promises of AI to make clinical care better?
Yeah, I mean, I think one thing is that right now, different modalities of data are sort of treated separately in the care of patients, right? There's a separate PACS system for certain kinds of medical imaging. There's a medical record system. There's the patient's own fitness sensor data if they use a Fitbit or whatever. And ideally, you'd like to have all this data come together at the point of care so that with patient permission and other appropriate permissions, clinicians can look at the complexity of data that is associated with that patient and other similar patients in order to make decisions. And for any given patient, they may not own a Fitbit sensor, but some of them will, some of them won't. And you'd like to be able to make use of that. And you need to be able to figure out how to train machine learning models that can deal with heavily multimodal data like you see in medical settings.
All right, I think question over here.
First of all, wonderful talk. It was a great tour. Question is related to, I'll come back to the earlier remark about the goodness of the ground truth, and also to your remark during the talk about how the same diagnostician asked the same question twice gives a different answer, which we have seen many times before. Yeah. Have you considered, or has anybody tried to work on understanding what is the source of that variation, and is there a way to learn that and to mitigate the variation rather than trying to say, let's throw that away and then fix the end goal?
That's a great question.
I mean, I think the source of variation is really, at least in the diabetic retinopathy diagnosis issue, is just that the difference between a 2 and a 3 is not a crisply defined thing. It's sort of like, how dark do you think those hemorrhage-looking spots are, and how big are they? And it's not as well defined as you might like. And so that's why one person can stare at it and say it's a 2, and the next person can stare at it and say, no, I think it's more like a 3. And I think that's just inherent in the problem. It's not that things go from a crisply defined 2 to suddenly becoming a crisply defined 3. It's sort of shades of gray. I think we just need to accept the fact that the real world is messy, and that some of these opinions are a bit noisy. Machine learning algorithms are actually reasonably well suited at dealing with noisy data. As you see, if you get sort of multiple independent opinions, you can actually train an algorithm that is going to be better than any of those individual ophthalmologists doing that task.
All right, the monitor here is indicating that we need to wrap this session up. So join me in thanking Jeff one more time for this fabulous tour.
Thank you. Great.
And our next session is going to be led by Maddie Leonard, so I'll welcome her on stage while we disappear behind. Thank you.
And welcome. My name is Mary Leonard. I'm chair of the Department of Pediatrics and director of the Maternal and Child Health Research Institute. And it's really my great pleasure to moderate this session on social determinants of health. This is a topic where pediatricians are very invested in terms of the implications of this work across the life course. So we have a wonderful slate of speakers. The first is Kirsten Bibbins-Domingo. She's professor and chair of the Department of Biostatistics and Epidemiology at UCSF, vice dean for population health and health equity. She co-founded the UCF Center for Vulnerable Populations at Zuckerberg San Francisco General. This is a research center with a broad mandate focused on discovery, implementation, policy advocacy, and community engagement for communities at risk for poor health and inadequate health care. Kirsten is an internist at Zuckerberg, and she has expertise in cardiovascular disease, hypertension, diabetes, and chronic kidney disease, with a special interest in the development of these conditions in young adults. Please join me in welcoming Kirsten to the stage.
Great, thank you very much. So I wanted to share 4 observations about social determinants of health and big data. And I want to do this by telling you the story of my father. My father lived with prostate cancer for many years, and he eventually died of prostate cancer in this past year. He's like many African-American men. African-American men are almost 2 times as likely to develop prostate cancer, and if they develop it, they're twice as likely to die compared with white men. Prostate cancer is an interesting disease because for many men, it is a slow-growing disease where they will have it and die of something else. And for some, it is an aggressive disease. It's a disease that occurs earlier in life, and for African-American men, they're more likely to be in this group where it is aggressive and it occurs earlier. Now, we know how to treat prostate cancer. The treatments are effective, but they have side effects like impotence, incontinence, and in rare cases, death. We'd like to know how to target those types of treatments to the individuals who have the most aggressive forms of cancer, especially if it's something that's going to happen earlier in an individual's life. And so this is an ideal condition for precision approaches. The challenge is for prostate cancer is that less than half of the studies that of treatments for prostate cancer actually include any African Americans. And among our screening studies, African American men are included in numbers that are not compatible with their representation in the population. We've had an explosion of genetic data, and this graph really shows that trend over time. And that explosion has occurred, unfortunately, almost exclusively among European-descended populations. And that means our excitement about the use of this data in practice, most currently our excitement is around polygenic risk scores, it creates these certain types of biases so that genetic risk scores that are developed in one population actually perform remarkably poorly in other populations. So the first point that I want to make here is not about social determinants of health. It is about diversifying our representation in our genetic studies, which is probably the way many of us got to big data and precision health. And I want to make this point because panels on social determinants of health oftentimes veer into inequitable distributions of social factors that relate to health. This is a factor decidedly in our control. As scientists, as clinicians who implement these scores, understanding when these scores don't work in patient populations is actually our own responsibility. And it's our own responsibility to figure out how we do this better. So I want to turn back to my father. My father grew up on a farm in Virginia. For him, military service was the pathway to upward mobility. Military service is the place you can see the world, and you also have the opportunity to be exposed to many things. In this case, this is Agent Orange in Vietnam. He grew up in the South during a time of segregation, where he went to segregated schools. When he married my mother, who's German, this was illegal in the state where he was living. And throughout his life, while many of these things changed, factors like racism, of course, whether interpersonal or structural racism, persisted throughout his life. Being from the South, he also enjoyed a good plate of Southern food. Now, all of these factors in individual studies have been shown to contribute to risk for prostate cancer, as well as to the acceleration of prostate cancer. We know these are important, but understanding how they intersect with our understanding of the biological determinants of prostate cancer is not well known. And this is where we have the opportunity, given the opportunity of new types of data sources, to think beyond our ever-increasing opportunities to phenotype individuals based on biological characteristics, but to also understand how the social characteristics, the social and environmental factors that we know also influence the development of disease happen. This will require, of course, new uses of data, new uses of types of data, and I think that's the opportunity and challenge. So here, new data sources, new scientific methods will allow us to really understand for complex phenotypes that we've really well characterized biologically, how those intersect with the other factors that we know to be important to the development of disease. Now, there's a lot of interest in social determinants of health. This is a National Academy study that I was fortunate to be part of, and asking which social determinants we should actually put into electronic health records. And as you can see, a lot of places have actually adopted elements of these social determinants. The rationale for the National Academies Committee was to really say what factors could help a clinician in the care of a patient, what factor could help clinicians think about population health, so how a health system thinks about a group of patients that they're trying to take care of, and what factors would help us accelerate research on the intersection of social determinants of health and particular health states. So this was the short list of 10, but there are, of course, many, many others that have this particular characteristic. So we're at the point where we're trying to figure out what we actually do with this type of data. What is it useful for, beyond the understanding for that individual patient? And I want to give an example here of the way Cincinnati Children's has used its data. They are very interested in where their patients are and the context in which they live, and have thought about this across these multiple domains here. They wanted to use this data to think about how they could reduce readmissions for children with asthma. It's not going to surprise you that readmissions for children with asthma might concentrate in more poor communities, which in fact it did. But what they found when they actually looked at the locations of their asthma readmissions, that they were occurring not just in one neighborhood, but one specific apartment complex. And so this is a case where they had been thinking about intervening and predicting readmissions based on individual factors, but eventually used the data to intervene on the apartment complex itself, and thereby taking what they found in a few patients and actually improving the environment where many, many more patients were living using the data in this way. These are early days to figure out how we use this in population health, but I think the incentives and the alignment around many things suggest that there are opportunities to think about these factors, not just in how we improve health for individual patients, but how we can actually intervene in settings that we might not have intervened in before. This is our look at data on diabetes in San Francisco. It turns out if you are diabetic and your diabetes is controlled, those cases don't cluster in San Francisco. But uncontrolled cases of diabetes do in fact cluster. They cluster in the poorer communities in San Francisco, perhaps not surprisingly. They also cluster in other places that you wouldn't expect. And this gives us an opportunity to think about what's happening in those areas and other points of intervention, because we know diabetes is as much about context as it is about individual behavior. We've thought about this also in terms of how our patients age and where they are aging. We're interested in them aging in place. This is data across 2 health systems, but mapped on a background of where green space is in San Francisco, or where walkability is. Both of these are factors that greatly influence an individual's social environment and therefore their ability to manage certain chronic conditions and in some cases in aging successfully at home. So I think this is an opportunity. It's an opportunity, the interest in population health, the interest in integrating measures of social determinants into the electronic health record offers up new opportunities for how we might intervene not just on patients, but on actually communities themselves. There's, of course, risk here, and we've talked a lot about biases in healthcare records. So new data offers new opportunity and also challenges to think about how to use this in the way that best achieves the health goals of our patients. So I want to end with my fourth point by talking about where I was yesterday, which was at the Solve Summit. I love coming to Stanford to promote a UCSF event. That's a good thing of mine. So this is the Solve Summit. So I work at San Francisco General Hospital, Zuckerberg San Francisco General Hospital, and we've been very interested in the use of digital technologies to improve the health of our patients. And sometimes people are surprised by that. But it turns out cell phones are very ubiquitous. There is a great need to support our patients in how they manage their chronic conditions. And oftentimes, being able to do this in a more cost-effective manner is actually of interest to the health system as well. And several types of digital technologies offer that possibility. Now, this is a challenge because these technologies are developed in not my patients. And so figuring out how to adapt them to our patients is one of the things that has been a major focus in our center. And in this particular group, the Solve Health Tech group, led by Urmi Malasarkar and Courtney Lyles. We have experience doing this. We can show it works. We can show that patients are interested. And it turns out, although you're not going to market this to my patients at Zuckerberg San Francisco General, Medicaid is very interested in these types of technologies as well. And they're very interested in thinking about how they can use these types of technologies to improve Medicaid population's health. So this was our event yesterday, co-sponsored by the UCSF Health Hub. And we basically had 33 companies who applied to work with the Solve Health Tech team. 6 of them presented yesterday. They expected to choose 2 winners. They ended up choosing 3. And those 3 will work with the team here to really adapt their particular digital technologies to address the interest of more low-income, diverse patient populations. The 3 winners were Inquisit Health. It's a digital platform for peer mentoring that they've shown works successfully to help control diabetes, and they have a program that's very interested in culturally tailored interventions and culturally matching peers via this platform. Mommy, which I love that name, Mommy, recognized what we all know if you've been watching the news, that the perinatal, postnatal period for many low-income women, particularly African-American women, is one that's very vulnerable period of time. We have high rates of maternal mortality compared to a country of our resources should have. And Mommy recognized basically that there were that we live in a fragmented healthcare system, and this period of time was particularly vulnerable to fragmentation. So data coming for the child, coming for the mom, and a period when mom is between being pregnant and being not pregnant and being home. And so this is a platform that integrates these multiple data streams and actually helps to actually have data and then interventions in one place during a particularly vulnerable period of time. And then the last one was applied VR, that is addressing another timely topical issue of the opioid epidemic and has been using virtual reality to find non-opioid strategies for pain management, and very interested in adapting this approach to a more diverse and low-income population. So I do think that for those of you who are in the tech sector, this is an interesting time, and the opportunities to think about the power of these technologies for more resource-limited, low-income patients, I think is a really interesting and really exciting opportunity now. I'm looking forward to the discussion. Thank you very much.
Thank you. So as Kirsten mentioned, we'll save question and answers for the end. We have lots of time. So my pleasure to introduce our next speaker, Nicholas Christakis. I could use his entire allotted time just to tell you his titles, but the high point, he's the Sterling Professor of Social and Natural Science at Yale in the departments of Sociology, Medicine, Ecology and Evolutionary Biology, Biomedical Engineering, and the School of Management. He's a social scientist and physician who conducts research in the fields of network science, bioscience, and behavioral genetics. He's the director of the Human Nature Lab. In 2009, his book, Connected, The Surprising Power of Our Social Networks and How They Shape Our Lives, came out, was translated into 20 foreign languages, and that same year, he was named by Time magazine to their annual list of the 100 most influential people in the world. Just last month, his new book came out, Blueprint, The Evolution Origins of a Good Society, was published, is already on the New York Times bestseller list, and we're so fortunate that Nicholas was able to join us in the middle of his very busy high media book tour. So please join me in welcoming Nicholas.
Thank you. Thank you very much for that introduction. Thank you all for having me. So humans are embedded in social networks, and these networks obey very particular mathematical, biological, psychological, and sociological rules. And if we can understand these rules, it gives us whole new ways to intervene in networks to make them better. And in the broadest sense, taking the embeddedness of human beings in networks seriously allows us to begin to shift our gaze to the externalities of our interventions. So what I'm interested in is not so much the response to treatment among the treated. I'm interested in the response to treatment among the untreated. I want to know when we implement clinical or policy interventions in a group of people, not so much how do they respond, but how does everyone else around them respond? And how might we exploit some of these insights in order to magnify the impact of our interventions based on many of the tools that we've been discussing today? So for the past 10 years, I've been asking ourselves a question. So what if we can understand the structure and function of human social networks? What can we do with that knowledge to make the world better? And I'm going to quickly review with you some of our experiments that we've been doing most recently over the last 10 years. But before I do that, I'd like to start with just the very briefest of introduction of some basic principles having to do with social network structure. So here is a network map of 105 people and who their friends are. Every dot is a person. Every line between them represents a friendship in this case, although it could be a coworker or a neighbor or a sibling, for example. And this is what a real social network looks like. It is heterogeneous locations. People within networks are not all the same. They occupy different positions. And this can be quantified mathematically in a number of ways. 3 of the most basic ways are illustrated on this slide. So if you look, for example, at the upper left, you have node B. Node B has 4 connections. And on the far right, node D has 6 connections. This is known as the degree of a node, the number of connections it has. And this is something people typically know about themselves. How many friends do you have? You have 10 friends. You have 8 friends. I have no friends. People know this about themselves. But there are also higher order phenomena or higher order properties of individuals within networks. For example, if you look at nodes C and D, C has 6 friends in the middle of the network and D has 6 friends. And this might be the limit of their understanding of their social location within the network. But we, with this bird's eye view, can see that C and D are very different. And I can cultivate this intuition in you by asking you, who would you rather be if a deadly germ was spreading through the network? You'd rather be D. You should have the intuition that D is going to be less likely to get whatever's spreading and less likely to get it early in the course of the epidemic. Now who would you rather be if a juicy piece of gossip were spreading through the network? You'd rather be C. So what happens to you, whether you acquire information or are affected by germs, can depend on this aspect of the network, that is to say, how central you are in the network. And this can be quantified mathematically in many ways with things like eigenvector centrality or betweenness centrality, so we can tell the difference between C and D. Finally, if you look at nodes A and B, B on the upper left, A on the lower left, they both have 4 connections, but the difference between the two is that the friend of B's is not a friend of B's, whereas the friend of A's, the friend of A's is back again a friend of A's. So A's friends are friends with each other, whereas B's friends are not friends with each other. This is known as the transitivity of a node, and it can also be quantified in a variety of ways. So with that very trivial introduction to sort of structural aspects of networks, let me launch right into a quick review of 3 broad ways we might intervene in social networks to make them better and enhance public health and public policy using social networks for good. So my lab and many labs around the country have been advancing science in this area. One of the first ways that I'm going to quickly introduce you to is this notion of contagion or changing the flows. So here the idea is, given a structure of a network, in whom should we intervene so as to maximize the flow of whatever it is we introduce it? If you're a bioterrorist, the question is, who should you infect so that if you infect that person, everyone else will be infected? But if you're trying, for example, to increase adoption of new test ordering practices or a new pharmaceutical agent in a network of doctors, which doctors should you detail so that if you detail those doctors, all the other doctors in the healthcare system will change their practice? Or if you have a group of patients and you're trying to get them to enhance their diabetes self-care, for instance, which patients should you focus your interventions on such that if they improve their self-care, other patients around them will copy them, and so you will magnify the impact of your intervention. These type of interventions are contagion interventions. A totally different class of interventions are connection interventions. In these interventions, you manipulate the structure of the network. So here the idea is, how should we connect people to each other such that if we connect them in a particular way, it enhances desirable properties that we might want? A trivial example of this might be, for instance, Alcoholics Anonymous. You take a group of people who don't know each other, you connect them to each other, you introduce them, and you enhance their capacity for sobriety. So a structural intervention of who you introduce to who could have a beneficial impact. And a last idea that we've been very recently exploring in my laboratory that's much more subtle and that has also been intersecting with some of our work on artificial intelligence is what we call position interventions or changing the location. So a simple model of this might be you're a teacher, you have a seating plan for your classroom, and the chairs are nailed to the floor, you have 20 seats, and you have 20 students. To which chairs should you assign these students such that learning is optimized? Should you put all the best students in the front row and the weak students in the back row? Should you reverse that? Should you alternate the students? It's the positioning of the students in a network topology that's now the question, given a choice set of individuals that you have to slot into it. And this also we have been doing some experiments with. Let me show you some of those experiments in each of these categories, just a quick introduction to some of the work that we've been doing. This sets the stage for how we might go about manipulating contagion. We work primarily in the developing world, in Honduras, in India, and Uganda, and other parts of the developing world, but we've also done work domestically, and so have others, in schools, in churches, in workplaces, and the like. Imagine you map 2 networks, the network on the left and the network on the right, and on the right you have just enough resources to target the 6 individuals that are colored yellow here with a public health intervention. You go in and you teach them about vaccination or maternal and child health, for example. The usual perspective in public health trials is to come back a year later and see what fraction of those 6 people might have responded. Perhaps, for instance, 3 of those 6 people will have responded. But that's not what I'm interested in. I'm not interested in response to treatment among the treated. I'm interested in response to treatment among the untreated. I want to know, what does everyone else in the village do as a result of you targeting those 6 yellow individuals shown on the right? So perhaps in this case, 3 of those 6 yellow individuals responded, and they recruited 3 of their friends for a total of 6 people responding to the intervention in the right-hand village. Meanwhile, in the control village on the left, to whom no intervention was given, by secular change, perhaps 2 people respond. That difference between 6 and 2 is the pure measure of the peer effects in this type of an intervention. But now you should have the intuition that maybe you don't need to pick the 6 people at random. Maybe you could use mathematical tools to identify particular individuals who are structurally influential, such that if you intervened upon them, they might create bigger spillovers. For example, you might pick 6 central individuals, defined along the lines that I just introduced a couple of slides ago. So here you might again target those 6 people, maybe 3 of them respond, but maybe they recruit 30 of their friends to respond. Same village, same intervention, same number of people targeted, 10 times the effect, because you have shrewdly exploited the power of networks to magnify what they're seeded with, and now increase the impact of whatever it is that you're doing by enhancing spillover effects within that network. So we can experiment, in fact, with different algorithms for picking such potentially influential nodes. And my lab has been inventing and testing a variety of such algorithms. How do we define people, not so much by attributes of themselves, but like, for example, their height or their age or their diagnoses or things like that, but rather how do we define them by virtue of where they are in a network? So this is just a paper we published a couple of years ago now in The Lancet. Was one of our first papers documenting this in a randomized controlled trial. We took 33 villages in Honduras. We randomly assigned the villages to different network targeting algorithms. So this third of the villages, 5% of the people were chosen at random. And this third of the villages, 5% of the people were chosen according to who had the most connections, who had the highest degree. And this third of the villages, 5% of the people were chosen to a different kind of network structural algorithm that we have been testing. And this slide illustrates what the targets might look like in the same village if you were picking them by two different means. So the orange dots are 5% of the people chosen at random, and the yellow dots are people chosen according to whether they had the highest degree in the network. And then we delivered a variety of interventions. I'm just going to show you the results for a multivitamin intervention. Here on the x-axis is the days since initial targeting with a public health intervention. On the y-axis is the proportion of people who have adopted the multivitamins. And what we show is that using one particular targeting algorithm, which I didn't define for you, but it's in the paper, you can optimize adoption in these villages, getting 75% approximately adoption within 2 weeks using this technology. Here's a totally different experiment now involving the manipulation of connection, leaving contagion behind us and just looking at connection. So in this experiment, what we did is we've developed software that allows us to create temporary artificial societies of real people. It's integrated with Amazon Mechanical Turk, and we can, in a godlike way, define these societies, define the interactions between people, and experiment upon them in various sorts of ways. And we've done, I think, 30,000 people have participated in our experiments. In this experiment, in the lower part of the experiment, what we did is we brought people and we dropped them into a network that had this structure. This is an Urgis-Renyi random graph with 30% tie saturation. Doesn't matter, it's a network. People are dropped into the network and they're introduced to their neighbors. And they play something known as a public goods game. It's a kind of economic game that looks at how generous might they be to their neighbors and whether their neighbors might reciprocate that kindness. So do I cooperate with my neighbors and do they in turn cooperate with me? The nice cooperative people are shown in blue at the beginning, and the mean defectors who take advantage of their neighbors, who don't contribute to the public good, are shown in red. This is like high school science projects, where you're given a bunch of duds and they're not doing their job, and if you do the work, they get some of the credit, and your choices all suck, right? You either have to do the work for everybody, or you also defect and don't do the work, and then you get an F, right? So what happens in this situation is that people are introduced to their neighbors. The neighbors are defecting and they play multiple rounds of the game. And what happens is these initially cooperative blue dots get pissed off and they stop cooperating. And by the end, defection takes over the system, except for these few little blue dots on the edge here keeping civilization alive. So people, when they're exploited, they don't like to be exploited. They also switch to defection. And as a result of that, cooperation disappears from this social system. In a different branch of the experiment, what we did is we manipulated the rules of connection. In this branch of the experiment, we allowed people, in addition whether to choose to cooperate or defect, to rewire their networks in very specific ways. And in that branch of the experiment, cooperation persisted. Here's the point. I can take you people and connect you one way and make you really sweet to each other. Or I can take you same people and connect you a different way and make you mean sons of bitches to each other. So the same people can give rise to different properties, not given who they are, but rather how they are connected to each other. And we have done many experiments that show that. Another experiment that manipulates connection, which I'm going to whip through, and then I'm going to show you a final experiment and close with one idea, is this experiment, which involves some of our investigation of the impact of inequality. So everyone is concerned about the impact of inequality on health, on wealth production in our society. We decided to use our platform to do some experiments in which we created artificial societies with higher or lower levels of inequality. We randomly assigned people to be rich or poor. We gave them real money to play with. And then we dropped them into these little societies and had them interact with each other. And we furthermore manipulated in these societies whether or not people could see the wealth of their neighbors. This paper was published in Nature a couple of years ago now. So on the left-hand side, you have a network. The dot size is proportional to how rich people are. The letter, bigger dots are richer people. The letter at the beginning indicates whether they were randomly assigned to be rich, PR, or P, poor. And here they cannot see each other's wealth. They play the same kind of public goods game I introduced a moment ago. And their Gini coefficient is artificially created by us to be 0.4. That's a very high Gini. That's American or Moroccan levels of inequality. Scandinavian levels would be about 0.2. Total equality is 0, a Gini of 0. So they're put in this very unequal world. They play the game, and they cannot see each other's wealth. And by the end, the Gini has come way down. Inequality has been greatly reduced. The blue color indicates the cooperators again. The red color indicates the defectors. Everyone's very nice to each other. Most people are cooperating. And all the dots are big. Everyone is really rich. In the other side of the experiment, we randomly assigned other people. There were 1,500 people in this experiment. We flip a switch, and now we make each other's wealth visible. Now you can see how rich your neighbors are. And here you get none of these beneficial effects. The inequality stays high, more red dots, people are less cooperative, and there's less wealth produced. In fact, and this broke my left-wing heart, what we found was that actually inequality didn't have any bad effects in these societies. But visibility was very corrosive. So on the x-axis is the round number across time. On here is the average wealth produced by these societies. The dotted lines indicate the invisible wealth condition. The solid lines are the visible wealth condition. And then the colors indicate how unequal was the wealth at the beginning. You can see that there's not a lot of difference given how unequal the wealth was randomly created to be at the beginning, but invisibility was very advantageous. People were much better able to work together to produce wealth if they could not see the inequality in their societies. And you get very similar results with respect to the amount of cooperation. Once again, inequality is not what's really ruining cooperation, it's visibility between individuals. Finally, I'd like to look at some experiments of ours involving position. And this line of work also intersects with some of our new work on artificial intelligence and the addition of bots to systems of humans in what we call hybrid systems of humans and machines. So we are in the midst right now of creating heterogeneous systems of people and AI, or people and robots, like autonomous vehicles. And the question is, how will these hybrid systems work, and what are some ideas we might exploit to enhance the performance of groups of people arrayed in this fashion? So there's been a little bit of garbling here on this axis, but let me just illustrate to you these results. Once again, we drop people into a network, and now we give them not a cooperation challenge, but a coordination challenge. We give them each a color, one of 3 random colors, orange, yellow, or purple, and we tell them they can change their color whenever they want over 5 minutes, and they change their color every second or so. And the challenge is to pick a color dissimilar from their neighbors. If everyone picks a color dissimilar from their neighbors, if the group works together to solve the problem, they get paid. And the whole group gets paid. But if they're unable to work together to solve the problem, they do not get paid. So everyone wants to pick a color dissimilar from their neighbors, and every second or two, they look around them and they change their colors. So for example, this node here is orange. This node should switch to purple, so as no longer to be in conflict with his 2 neighbors. The color conflicts are shown in red. The red ties indicate 2 nodes that are connected that are in conflict, and the purple ties indicate 2 nodes that are connected that are not in conflict. On the y-axis is the number of color conflicts. On the x-axis is time. There are 2 kinds of conflicts, which I won't go into right now, and it turns out that the people start solving the problem. At 105 seconds, 1 conflict persists, but it's irresolvable. Neither of the 2 yellow dots can make a change to eliminate the conflicts, because if either of them change, they'd be in conflict with others of their neighbors. Nevertheless, they make a switch. Maybe they temporarily increase conflicts, and by the end of the game, or 245 seconds, everyone has picked a different color than their neighbors, and the problem is solved. So what did we do in this experiment? In this experiment, what we did is how hybrid systems of humans and machines, or artificial intelligence, could work together. Because we were sneaky, we surreptitiously replaced some of the humans with bots. We randomly assigned 4,000 people to 230 groups, some of whom were just composed of humans, and some of whom were composed of humans and bots. And we endowed these bots with very simple programming. And what we did is we measured what fraction and how fast of a group of people, a group of groups, could solve the problem. So on the y-axis is the probability that the group has not solved the problem, the game, and on the x-axis is time. So the yellow line indicates the just human groups. At the beginning, 100% of the groups haven't solved the game. And by the end, at 5 minutes, about 65% of the human groups have solved the game. And then we experimentally manipulated the programming of the bots, making them either perfect. Every 1.5 seconds, they looked at their neighbors and they picked a color that had the minimum conflicts with their neighbors, or making them slightly noisy, so they maybe or occasionally deliberately made a mistake, or very noisy. Sometimes they made many mistakes. And we manipulated whether we put them randomly in the network, in the center of the network, or in the periphery of the network. And to make the long story short, we found that if we added slightly noisy bots, little bits of error, into the center of the network, we could enhance the ability of these groups to work together to solve the problem. So it's this ability of bots to work with humans to help the humans to help themselves. And we are building on this work to design and add simple bots to other situations involving social dilemmas and collective action problems. We are exploring the kinds of simple programming, what we call dumb AI, that might make them effective, not just the noisiness idea or position idea that I just introduced. And these bots can also be used to address other sorts of social problems, like combating inequality or racism online, for example. So the gist of this idea is that in my lab, we are not focused on developing super smart AI to replace human cognition. We are developing dumb AI to supplement human interaction. We just want to add a social catalyst. We just want to reduce the difficulty of humans working together to solve their own problems. So think about these two objects. As you all know, they are both made of carbon. On the left, you have graphite, which is soft and dark. And on the right, you have diamond, which is hard and clear. And there are two key intellectual ideas here. First of all, these properties of softness and darkness and hardness and clearness are not properties of the carbon atoms, they're properties of the collection of carbon atoms. And second, which properties you get depends on how you connect the carbon atoms to each other. Connect them one way, you get one set of properties. Take the same carbon atoms and connect them another way, you get a completely different set of properties. And it's the same with our connections and the performance of human groups. New properties emerge in human groups, not because of who the people are, but rather because of how they are connected to each other and how some of the phenomena that I've been describing this morning work together. New properties such as cooperation and violence, health and happiness, innovation and productivity emerge because of the connections, because of the ties between people, and not necessarily because of the people themselves. So it's not just what's happening in the people around us that matters. Our experience of the world also depends on the actual structure of the ties around us, near and far. Thank you very much.
Thank you, Nicholas. All right, our last speaker, I think, is the perfect person to bring this session to a close. He's our own David Rakoff. He's an associate professor of medicine and health research and policy here. His research is focused on determining how the social environment impacts the development of chronic disease using quantitative methods from epidemiology, economics, and demography. His work is unique in that it integrates statistical and conceptual models of econometric and advanced epidemiologic methods with consideration of the underlying pathobiology preceding chronic disease risk, such as processes of DNA methylation. Welcome, David.
Thanks very much. Thank you. So I became interested in studying social determinants of health for one particular reason. And that is that a particular social determinant of health may be related and associated with a whole bunch of different health outcomes. So it may give us a particularly effective approach to improving health and preventing disease. So this is something that's been known kind of anecdotally, but I was able to work with colleagues here recently, Chirag Patel, who's now at Harvard, John Ioannidis, and Mark Cullen, to try to quantify this for one particular social determinant of health, income. And our question was, how many risk factors for disease is this one thing, income, actually related to? You might imagine that there'd be a lot of particular bias in the studies that are published. Not many people want to publish a study that says income isn't associated with this risk factor. So we were curious to kind of quantify this in an unbiased way. So we looked at income and 330 different risk factors for disease. And what we found, the depth of those associations and strengths of those associations even surprised me. We did an out-of-sample validation, counted for multiple comparisons, and what we found is that there were 66 out of these 330 risk factors that were pretty strongly associated with income. And these were really over a wide range of things. So they included things like blood lead, exposure to mercury, HDL cholesterol, and a lot of components of diet that came from eating more fruits and vegetables. And so this kind of supports the general idea that if we can focus on social determinants of health, it might be a particularly effective way to kind of supplement what we're doing at an individual level with drugs or sort of more targeted interventions. I want to be clear that I don't think those are sort of mutually exclusive options. It doesn't mean, well, we should stop treating people with statins, for example. It just means by addressing social determinants of health, that all of those sort of individual targeted things can get a boost, and we can really have a potentially cost-effective way to do a better job of improving people's health. So you may be saying, well, this seems pretty complicated. All of these things, if they're very correlated with each other. And the answer is yes, this is pretty complicated. So this is a paper that I worked on with my colleague Bob Hyatt up at UCSF, where we put together a model of how socioeconomic, behavioral, biological, and things in the physical environment were related to breast cancer incidence. And so what we did is over a period of several years, we've gotten people together with expertise in each of these areas and kind of mapped out how all these things are related. But this is still kind of a very simplified version of the way social determinants probably actually work. One of my favorite posters that maybe you've seen before is from Roche on the cellular and molecular pathways. So I used to have this on my office wall for a while as kind of inspiration. So this is what many decades of work in molecular biology has shown us for the way the body works and the complexity of these biological pathways. And so this is kind of my goal of what I think. I don't think the social world is necessarily any simpler than that. And so we want to start taking approaches to kind of recognize the complexity. But that does come with some challenges. So how do we make sense of this when things are so correlated and so complicated? And I think here, too, we can also, in the social determinants of health field, learn from what's been done in molecular biology. And so one approach is kind of taking an approach with social determinants of health that's similar to the GWAS approach used in biology, where we take a whole bunch of genes and we look in a prediction model of what predicts a particular outcome. So I've been doing this in a smaller way over the years with a number of colleagues. Here's just an example of looking at a number of psychological and social factors and how they predict onset of adolescent obesity among girls. We're able to sort of confirm a lot of findings that were known in the literature, so income and education were important predictors. But by casting this wide net for a whole bunch of different risk factors, here we were only looking at 100, but it was sort of more than what's been looked at typically. We were able to kind of find potential new causes of the onset of adolescent obesity, things like anxiety, interoceptive awareness, and many things having to do with eating disorders that were also related to higher weight gain among girls. But one thing I've noticed in this work over the years is that what we see in social determinants of health is similar to what we see actually in GWAS studies. So on the right here are the size of association between different SNPs, genetic mutations or genotypes for obesity. So we have these really strong effects like FTO, and then they get a little weaker, and then weaker and weaker still. And what we found lately in genetics, I mean, 10 years ago, people were thinking, oh, there was a gene for this, gene for that, or even sort of, a top hit sort of world. But what's happened now is we found, okay, it's not this, 5 or 10 genes for a particular complex trait like obesity, but it's actually thousands of different genes with tiny, tiny effects that actually add up to sort of a substantial genetic component for disease. So what we're doing right now in social determinants of health, we're still in this sort of top hits era, where we're, based on our data sets, are really kind of only identifying a few factors that are related to diseases or risk factors such as BMI. But I think where we need to head is sort of looking at this sort of tail of the distribution that we're now seeing in genetics, and that there may be really thousands of other factors that we're beginning to measure, but that we haven't analyzed yet, that may be important things to think about in terms of targeting social determinants of health. So how did this happen in genetics? we're here at a big data conference. It was because of big data. So, 10 years ago, and it's amazingly, we were talking about this sort of at the beginning, the 7 years that we've been here. I mean, really, just in those 10 years, the sample sizes for the genetic studies have gone from around 10,000 up to many hundreds of thousands. So that's enabled an identification of these sort of small effect gene sizes. And I think we need to do the same thing with social determinants of health research. Another sort of point of this slide, actually, is a point that Dr. Bibbins-Domingo brought up earlier. We're sort of lagging behind in social determinants of health research, but maybe we can sort of correct some of the things that were done. So the color coding here is for the blue studies are studies that were done in Europeans. And so as we sort of move to data, again, I'd like to echo her comments that for social determinants of health research as well, we need to think about having more inclusive populations so our research benefits everyone. Now, this, of course, is just about prediction. But what we really want to know is if we change social determinants of health, will health actually improve? And so that's a really important distinction I want to make. So what I want to talk about is something that you can think about as the CRISPR for social determinants of health. So what you would do in genetics is you'd identify something, you do a gene knockout study, or you do CRISPR, and you'd isolate this one particular gene and look at what the effects are for a particular health outcome. So for a lot of social determinants of health, that's not something we can do. But the sort of CRISPR for social determinants of health, the sort of closest analog we have is quasi-experimental studies. And that's where we take this big, complex constellation of things that happen, and we try to isolate one little change that happened and see what the effects are on health. So I'll take a minute here and give sort of two examples of how we've done that with that same just social determinant of health that I talked about, income. And so let's take the example of poverty. So poverty we know, and income I just showed, is correlated with a whole bunch of different things. How can we look at what the effects would be if we actually made a change to poverty? You may be thinking, oh, that's impossible. We've been trying to get rid of poverty, for many, many years. How does this even happen? Well, actually, every day, you can just pick up a newspaper and find ways and policies and little things that are happening and big things that are happening to change poverty and change the influence and the meaning of poverty for different people. So one example of this that I've looked at is the Earned Income Tax Credit. So this is a program that spends $70 billion a year for working families in the US and lifts 4 million children out of poverty. So it's a really big program. And this map here just shows sort of the depth of that program in different states. So like the high poverty states like Mississippi, nearly a third of the population benefits from this Earned Income Tax Credit. And the key for this sort of identification approach, or doing these natural experiment or quasi-experimental studies, is the fact that this wasn't just one program that was implemented in a single way for everyone at a single period of time. So each states have raised and lowered their benefits over time. The federal government has changed the policies in sort of nonlinear ways. Sort of depending on the number of kids you have, you get more or less benefits. And so we can use all of this information, doing multiple types of studies to get at what the impact of this sort of change or changes in this policy might be. The key here is that this isn't something that the individual changed, which can be highly confounded. So it's not that this person did something and earned more money, but there was an environmental change, a change in this social determinant that changed how much money and this poverty benefit that people received. And so we've taken looks at this over the last decade, really, and shown a lot of sort of positive benefits of this sort of EITC change. So fewer low birth weight babies, reduced smoking, reduced food insecurity, higher HDL cholesterol, and even fewer colds. So we think a lot about social determinants of health and what governments can do for social determinants of health, but corporations and businesses actually can do a lot as well. So I was fortunate to be involved in this project, an evaluation project of when a factory, actually this was the company Knights Apparel, when they decided to start paying their workers a living wage at a factory in the Dominican Republic. And so what was really unique about this is when the workers were hired, they didn't know that they were going to be receiving a living wage. They applied for, it was in a free trade area in the Dominican Republic. They applied for a job. They received this job on the first day. Oh, actually, you're getting 3.5 times the salary you thought you were going to get. And so what we did is we found a similar factory, and we looked before and after in these individuals, and we said, what kind of difference does this make to people's health? So right now, we've just done a short evaluation of this over about a year, but now this has been going on for about 10 years now, and so we're looking to go back and look at, over a longer period of time, how this has impacted people's health. We found fewer depressive symptoms, higher self-rated health, more protein intake, and more money spent on food from grocery stores rather than convenience stores. So I'd like to conclude here by saying and acknowledging, yes, things are very complex. This is not an easy thing to do, but by taking the time and learning from the approaches that have been done in sort of other fields, especially molecular biology, but in particular using big data, I think we can really make progress in understanding social determinants of health. First of all, through environmental-wide association studies, we're really casting a wider net on the factors that we consider. So not kind of staying with the same 5 or 10 things we've studied for many years, but really expanding to sort of thousands of different things, thousands of things that are measured with mobile devices, measured through geographic information systems, and from other sources of administrative data. And then critically, we need to take what we learned there and look at things that have actually changed in the environment and do what economists and sociologists and epidemiologists have been doing for many years, and look at how these changes affect health outcomes. But the key there, again, is that I think what we've been able to do in the past has been really limited, because just like that that arc of those genetic data I showed, I think a lot of these are very sort of small little impacts that accumulate. So we really need these large multi-100,000 person sample sizes in order to make progress. But it's a super exciting time. I think now is the time that we're going to be able to achieve this, and hopefully we can all do that. Thank you.
Welcome all our speakers to the stage. Take some questions. This is always challenging because the lighting. Okay. Do we have someone at the back here? Can't quite tell. Maybe while this is coming into focus, I'll ask a couple questions. So I think all of you need good data on social and economic data on your participants or the people that you're studying. And in our opening session, you and Lloyd talked about people's willingness to share clinical data, and that's been maybe less of a barrier than I anticipated. I wonder if you can say something about looking forward, how hard is it going to be to capture data on social and economic data and things about people's own social circumstances for use in these kinds of studies?
Sure, yeah, I think we need to keep people's trust for sure and show them that by using this data, we're providing a benefit for them. I mean, income is famously sort of the last question that people ask on surveys because they know people won't answer it and will stop answering the survey. So we have to be, acknowledge that we keep this data private and that we're going to do something useful with it. But the other thing I would say is, when you think about quasi-experimental studies, administrative data, for the most part now we're not having to ask people these questions. So there's a lot of things in the environment, where people live, what they're exposed to, what policies they're exposed to, that are things that are external to them. So we don't have to rely on actually individual people's data, but data on their social environment, their connections, and data on the physical environment.
Either of you want to add to that?
I think one of the challenges, I don't know if this is on, but I think one of the challenges is that with the social determinants in the electronic health record, there's a lot of enthusiasm and push to put them there. But I think that is where we're asking patients, we're saying this is going to be important for your clinical care, and that I think now takes us outside of, just for research, but actually means we have an obligation then to protect what patients do consider sensitive information. We had, we realized that race ethnicity was not something that was routinely measured in our electronic health record as self-reported race ethnicity, which would be the standard. We made a big effort to do it. We did a lot with our frontline staff to make sure that those fields were populated, but the message was trust that we are using this information not to discriminate, but to actually hold ourselves accountable in how we provide care. But we then have to live up to that responsibility.
Yeah. don't know if you wanted to add anything, Nicholas, on this point.
No, I mean, I think many of the speakers this morning have already covered how there's a plethora of data, these new technologies for massive passive observation of individuals give us, I think, powerful new tools. I would just add a comment, which is the divide between what I'd call public, private, and personal ownership of the data. So one of the things that I'm concerned about is that, and many people here I'm sure know much more about this than I do, is the vast amounts of data that are in private hands. These companies know huge amounts about us, whether it's credit card companies or online social networks or the phone company or whatever, and they are analyzing the data and building products with the data, and the data is not necessarily available to anyone else. So I think getting that right and figuring that out is going to be a challenge in the coming years. Public data, of course, is either public or owned by the government. And then there's the issue of personal data ownership. I mean, should you own your own data? Should you be paid for access to your data? And some people argue, I think cogently, that if we created a market for data, we would actually enhance consent and enhance quality. So, the credit card company could say, look, we'll give you free rates if you let us anonymize your data and share it with others. That might be a model that is workable.
Yeah, interesting. Okay, back here on this side.
Hi, question for Dr. Christakis. First of all, bula bula. And second of all, in contemplating mapping social networks for social good, can you speak a little bit about whether there are practical tools to do that on an individual level in a big society like the United States, for example, as opposed to Honduran village? Is it possible to attempt that without being a Facebook or a Google? Or are there ways to do it without either being nefarious or seeming nefarious?
So we have developed software. I didn't discuss our software initiatives in the lab, but we build software to support a lot of the research that we're doing. One of our software applications, which is publicly available for non-commercial use, is called Trellis at trellis.yale.edu. And that software we use in the field can also be used domestically for from scratch mapping of social interactions at moderate scales. So for example, a school district or a village or a workplace of a few thousand employees. If you're talking about truly national networks, and if you actually mean sociocentric networks, that is to say, if you wanted a national sample of people, for each individual, you wanted to define and ascertain their connections in what's known as an egocentric network, you could use our software or other tools to do that. But if you really want to map, like comprehensively, how is everyone interconnected with everyone else in what is known as a sociocentric network, then you have to be the phone company or Facebook or one of those other providers. I don't see another solution. I suppose you could invite the American public to sign up and share with you who their friends are, but I think then you would just be recreating an online network, and you would have other reasons to do that other than research.
Thank you.
Yeah.
Did I answer your question?
Yes, thank you.
Perfect. Okay, on this side.
David, you had pointed out a number of studies really showing this increased connection or understanding of income and health. And I was just wondering if you could elaborate further on how that joint research looking at income and health might inform public policy discussions that are happening at the state and federal level, where on the one hand, people are talking about increasing minimum wage for better living conditions, and on the other hand, we're talking about Medicare for all, value-based care. So how does this work that you're seeing help to inform both of those conversations so that they're actually happening in unison?
Yeah, I think, the way these things can play out can be really complicated and can have really unintended consequences, can have results that we don't know about. And what seems like it's a similar policy, it's reducing poverty, the way you do that may really matter to people. So like with the earned income tax credit, a lot of people in qualitative work have talked about, I really like that I received that as part of the tax system, and it doesn't feel like a handout, and I'm not going to a welfare office to get that check. I'm getting it as a citizen in the U.S. And so I think, I don't have a lot of, even after studying this for a while, priors about what might work and the nuances of what would work best. And so I think really, seeing how states try out things, evaluating when a minimum wage happens in different cities, when when the EITC is increased in different states, you can really kind of play that out and see what happens, and then other states could try to adopt it, in a sort of feedback sort of way of learning.
Okay, I think we're on this side.
Yes, there is a challenge with social determinants of health. And the challenge is there are certain population that we know the intervention, they know, let's say, they need to eat better, but they say, I don't care. I just want to eat whatever I want. I want to receive healthcare. I want to eat burgers every day. If I get overweight and I need a bypass, I need to be able to go to the hospital to get it. So how do we do?
Yeah, well, so I think that's, that gets a little bit to what my kind of offhand comment was at the beginning, and that, I don't think, certainly I'm not advocating, this is one solution, we should just sort of address social determinants of health and forget everything else. In that study in the Dominican Republic, what I didn't show is that there was potentially increasing rates of obesity from that increased income that the workers had. So you have these negative consequences of that in that one particular area. So I don't think that means, we should just keep paying people, keep people in poverty so they don't get overweight. But there should be a combination of other things. You should pay attention to the food environment, pay attention to other things as well. So certainly, these kind of intervention on the social determinants of health, I think, we have to evaluate them, we have to see, can set things in a good direction, but then you need to pay attention into the details and how these things play out.
Nicholas, did you want? Oh, I'm sorry, Kirsten. Yeah, to add something.
Yeah, I just said, so that's absolutely true. Social determinants intersect with behavioral determinants of health. Those are both important. I do think that we have to understand that the environments where many communities live affects the ways in which they make choices. So individual behaviors are affected by environments, and that there are ways to think about how to optimize those environments to allow people to make the best choices. I think that the experience here in our area around creating incentivizing options for fruits and vegetables and disincentivizing options for soda, for example, has actually changed large patterns of behavior in several of the areas where these types of policies have been adopted. And they are not meant to say that individuals are not responsible for choices, don't actually make choices, but I think we have to understand these and how they intersect with one another.
And then, Nicholas, the next level would be in terms of the networks and your position in the networks. And I think you've done some work related to obesity. Does anything intersect with this question?
All these, I think there are multiple aspects to the question which my colleagues have also addressed. And, this relates to some of the underneath what you said, I thought was also this issue of agency. What are we to do with individuals who nevertheless make poor choices on their own behalf? What is the meaning of that? Are they really free to make those choices, or have they been so inculcated with certain belief systems that they make bad choices for themselves, and so they're really not free to be making the choices? And then even if they do, what does it mean to be in a civilized society? I mean, do we let this man's house burn? I don't want to live in a society in which we ignore the burning houses of people who, let's say, build houses poorly. I would like to be in a society in which we all are taxed and have a fire department which shows up and puts out the fire. So it's complicated, though, because you could make the argument that no, you should let his house burn, otherwise people won't learn. So there's that underneath it, and the thing that Mary alluded to is, of course, one of the key social determinants. I think longshoreman and social critic, I think his name was Eric Hoffer, famously said, when people are free to do as they choose, they generally do what everyone else is doing, which is a fundamental aspect of our humanity, of our species, is that we copy each other. And as Mary alluded to, I did some work years ago that looked at the social contagion of obesity and the fact that people are understandably very influenced by the weight, body size of the people around them. And when people around you gain weight, it resets your ideas, we think, of what an acceptable body size is, and then you gain weight, and then you pass it along. So there, are you free there? I don't know. That's a subversion of free will in a sense.
That's great. Okay, over here.
Thanks for the great talks and the discussion. And one of the areas that it flows really well into is this integration that we had in the earlier part of the session, integration of the digital tools to workflows as professionals or choices as individuals that we have. And I was curious, in your experience, when you try to effect those choices, what are the aspects of these nudges or suggestions that really make a difference when you're on that fence or fork point of making a decision, the smart and informed one or something else? And what are the features of these nudges that matter?
Anyone?
Are you talking about for clinicians, for individual,
I'll start with an individual and then maybe also a clinician.
With all due respect, I think the question is a bit posed in a difficult way to answer because not all nudges are the same, which is the essence of what you're asking. And so the nudges we use to get people to donate their organs are rather different than the nudges we use to get them to buy one vegetable over another in a fruit stand. So if you're asking, are there systematic rules about how to design nudging interventions, I don't know the answer to that. I don't think there is such a kind of abstract high-level theory other than the claim by the people who advocate for nudges, and I am one of them, a kind of paternalistic, light paternalism on the part of the state. I don't think there's any grand theory of that other than the recognition that how you structure people's choices affects them. So famously, as I'm sure you know, if you just switch organ donation to be opt-out versus opt-in, even though you're giving people the same choices, you get radically different outcomes. And people think it's just. And so we've done that. Would you like to restate your question maybe, or did we not understand it?
I'll just put an example. So for me personally, if a nudge or a suggestion is timely and simple and it has some kind of reasoning behind it, I'm more likely to, either as a professional or as an individual, to adopt it or pay attention to it.
I don't know if this is along the line of what you're asking, but I do think one of the areas that has been intriguing to me, and we were talking a little bit about diversifying participation in studies and things like that. I think one of the things that has been, I would like to see more of in the literature, in the nudge literature, is to incorporate the effects at the individual and sort of community and network level. I think that if you look at groups that have been actually successful at doing this, they've actually leveraged the power of community to actually say, this is something we want to participate in a way that I think is really important and I think not appreciated as well as possible. One example in my field for, blood pressure control, we've been doing it for years. We are at about 50% control rate in the US, right? Really poor, despite multiple decades of medications. We know what to do. And we think of this as a patient adherence problem, and we focused a lot of individual interventions on patient adherence. And my colleague down in Southern California has been doing these wonderful randomized controlled trials in black barbershops, right? And showing that he can get effect sizes as great as multiple medications in improving blood pressure control. Why does a barbershop intervention work? There's nothing magic about the barbershop intervention in some ways. It is a place that people go to regularly. They go regularly, and it's not like having to go out to a doctor's office. They go to regularly as a part of their routine. It is a communal place. It sort of normalizes blood pressure control, the thing that we're all doing. There are supports that are built into that. And then they lowered the barrier by actually having people to go into these barbershops. But I do think we have to think about our nudges, both individually and collectively, in a much more systematic way.
All right, great, thank you. Okay, over here.
Hi, this is a question primarily for Nicholas. I was wondering, as you're doing this work, have you been able to apply some of the methods you've developed to kind of model the prevailing social and political trends that are happening in the real world? For example, some of them may not be so desirable, like the anti-vaccination sentiment, but literally contagious. And can you explain with some of the methods you've developed why are these ideas so contagious? Like why do they work?
Well, yes is the answer to your question. So things like There are epidemics of peanut allergies. There are epidemics of mild autism. Interestingly, there's not an epidemic of serious autism, just an epidemic of mild autism. There's epidemics of anti-vax which is astonishing. You have some of the wealthiest communities in the United States that have vaccination rates that are, worse than Haiti, for example. And these are clearly social phenomena in large measure. We've also looked at vaccine resistance in Indian communities and poor Indian communities in the country of India. We have done some work in this regard. There's a subtle idea in what you said that would take me like 2 minutes to give a sort of anecdote to describe.
Sure.
Should I do that?
Yeah.
Okay. I'm going to take a risk here. I can't even see you guys, but I'm going to take this risk and tell you this. This is the classic example I use. So let's say you have a network of people. Let's say you have 2 islands in the Pacific, 100 people on this island and 100 people on this island. And in this island, everyone is having sex with everybody else. And in this island, nobody's having sex with anybody else. So in my world, this is a null graph. This is a fully saturated graph. You can think of it other ways if you want. But in neither island is there an epidemic of venereal disease. It's fine. Who cares? What the structure of the graph is different, but it doesn't matter. Now, a sailor washes up on the shore and has sex with one person. Where do you get the bigger epidemic? We're going to assume the sailor is infected with a sexually transmitted illness. And so you get the bigger STI epidemic, STD epidemic, in the graph that is fully interconnected. So the structure of the network has something to do with the size of the epidemic. It's pretty clear, right? Okay. Now, let's imagine that you have an island over here. Everyone is having sex with everyone else. Everyone is having sex with everyone else. But in this island, everyone is immunocompetent. And in this island, everyone is immunocompromised. Again, no outbreak. Sailor washes up on the shore, has sex with one person. Where do you get the bigger epidemic? Of course, in the network or in the island where everyone is immunocompromised. So not only does the structure of the network matter to how big the epidemic is and the spread of the thing, but attributes of the individuals, namely their own individual immune status, affects the size of the epidemic and the speed of transmission, okay? Now, finally, and this audience is probably mostly clinical, and probably all of you know this, but if you have sex with someone with active syphilis, you have about a 1 in 3 chance of getting it. If you have sex with someone with active HIV, you have about a 1 in 500 chance, depending on the sex act and all kinds of other details, but roughly speaking. So now we have an island, everyone is having sex with everyone else, everyone is having sex with everyone else, they're all immunocompetent, a sailor washes up on the shore, here he has syphilis, there he has HIV, where do you get the bigger epidemic? Of course, with syphilis. So it's not just the structure of interactions of the people that matters, it's not just the nature of the individuals that matters, attributes of the thing itself also matter, the pathogen. In the case of microbiology, we have 100 years of science to guide us. Are there hydrophilic or hydrophobic proteins on the surface? Is it a big or small pathogen? All of this stuff that we can do. But in the case of ideas, we do not. So I cannot tell you why anti-vax sentiment is so particularly delicious that it spreads from person to person, or how that's different, for instance, than some of the other phenomena that do or do not spread. I mean, we know if you put cats in the video that helps. But other than that, we really don't know. So I cannot answer your question on the level of why is it that some ideas go viral and others do not. We still don't fully understand that. We think that there are some things, like why do some, and incidentally, for pathogens, this virality of the pathogen is distinct from its lethality. So the spreadability of a pathogen is or could or not be correlated with how deadly it is. So this spreadability of the thing is a property of ideas, but it's still poorly understood. I don't know if I answered your question, but I hope I did.
Okay, over here.
So my research is in big data hotspotting, and our group is working on some of these issues right now to look at economic analysis. And I have a study later today presenting a poster stating that about 20% of the population is using 80% of the resources, almost based on the Pareto principle. I'm not going to be like Atul Gawande to put a term out there and not give objective data. But my question to you is, and this is for all the speakers, would you expect the social determinants of health to regress to a mean as you would for any other condition or for any other statistic?
Any takers?
No, that's my vote.
Okay.
No, the reason is there's this famous paper by Lincoln Phelan called The Fundamental Causes of Disease. There have always been socioeconomic inequalities. How they get defined, of course, varies across time and space. And the people at the top always get more than the people at the bottom. And there will always be people at the top. And so I'm not saying this to suggest we shouldn't address inequality, nor am I saying to suggest that we should just ignore the social determinant of illness. Instead, I'm saying is that as we make progress on addressing one, there will be other inevitable challenges in addressing others. And there's even the further difficulty, which is really depressing to me, is that a rising tide, I'm sure my colleagues know these famous studies, a rising tide doesn't raise all boats equally. And my favorite example of this was the Back to Sleep campaign for sudden infant death syndrome that was done about 20 years ago. So it lowered the incidence of sudden infant. So there was a high incidence of SIDS, and there was a big ethno-racial gap. And the national campaign was implemented, the Back to Sleep campaign, to get kids to sleep on their backs. The rates went down nationally, but the gap increased between the rich and the poor, or minority groups and non-minority groups. So you have this awkward situation in which you've improved the well-being of all groups, but you've widened the gaps. And this happens a lot when Medicare was introduced in our society, which would be a great thing to provide a public. I'm in favor of universal health care. But actually, you might paradoxically find that the introduction of universal health care widens the gaps between the rich and the poor, because those at the top are better able to take advantage of, let's say, innovations or benefits. This is an endless challenge in the field that all three of us work in, and I certainly don't have an answer, but I'm sure my colleagues do.
Okay. I do, actually. No, I don't have an answer, but what I'll say is that that's not inevitable. And so each sort of intervention like that, like we've shown particular things where, you can improve everyone's health and also reduce inequalities, or improve everyone's health and increase inequalities. And so it's just something to sort of keep in mind every time you're looking at one of these studies, not just look at the mean, but look at that distribution.
Yeah, good. Anything?
No, just that, just to recognize that the idea of the concept behind this, that the people who have resources to engage with whatever is new, whatever is going on, are more likely to be the groups that benefit, I think applies to what we're talking about today, which in digital health and technology. And I think it's an important feature for us to think about. It's not just how can we incorporate these social determinants of health, but how can we realize that we ourselves are part of that force that is really going to influence health, and make sure that we're conscious so that we're not contributing to these divides that are going to be inevitable.
Yeah, these tools, just to pick up on what you just said, these tools, these digital tools that we might be quite excited about introducing, and might even be introducing them specifically to decrease the gaps, might actually have the opposite effect. They might improve everyone's health, but increase the gaps. Mm-hmm. But I'm glad to see examples that both happen.
Yeah.
Thank you.
Great. Okay, on the right, or your left.
Ala Youssef, University of Toronto. Excellent panel. I think all of you laid on top of each other the presentation of how we can have a different approach to understanding big data and population health. My question is more regarding the measures we use to collect and measure things related to disease prevention and moving towards improving quality of life population. So we know a lot of these measures are not reusable, the data from them, because they're either incomplete or they're not followed longitudinally. As we think of big data evolving and generating, should there be standard measures where maybe new approaches where it's more convenient for people to complete, and more of an approach for us to use a standard measure so that we can compare and understand the difference between populations and differences, and have a complex understanding of the complexity of the context itself?
Kirsten, do you want to start?
Yeah, I think that would be ideal, obviously. I think we're in an environment where for things like disease surveillance, which is what you're talking about, I mean, the challenges for departments of public health and people who are charged with doing surveillance is that they don't control most of the data that they're using to surveil, right? And so even little things like we have a rising tide of chronic diseases that health systems know about and departments of public health essentially don't know about, right? And so even opportunities just for health systems to think about sharing data with departments of public health, using sort of broader tools to think about that, I think would be a marked improvement over what's happening in most places that are looking to surveil disease. That's even one step. That's not even common data elements and those types of things, which would obviously make it important. I think the measurement issues they're huge, but even before that, the fact that the data sits in very siloed places that doesn't allow for disease surveillance is probably where I would start.
Yeah. Perfect. Okay, thank you. That's a really nice way to bring everything together. I want to thank our panel and our participants with such great questions. Thank you. I think we'll be taking a break. Okay, thanks.
Your seats are
Reactive medicine is the medicine that we've practiced in the United States for decades.
You come to see your physician when something's wrong with you.
What we are attempting to do is take primary care to the next level.
The focus of human-wide is to consider how can we leverage the best of the art and science of medicine to prevent disease before it strikes.
Human-wide is really an opportunity to be able to take a subset of patients and it'll allow us to be able to wrap our arms around these folks in a unique way.
The information gathered from them in this study will enable us to design approaches to primary care that will benefit, we believe, hundreds and then thousands of other people down the road.
We want to help patients. We don't want to treat their diseases, we want to treat them.
Good afternoon. I'm Dr. Megan Mahoney. I'm the Chief of Primary Care at Stanford and a practicing PCP at Stanford. Thank you for joining our session on human-wide. What is human-wide? It's a bold new approach to primary care driven by real-time patient information, and it's a showcase of how we can bring in the cutting-edge technology and tools into a clinical setting so that we can not only cure disease, but also predict and prevent it as well. Stanford Primary Care partnered with all of the patients in the pilot so that we could create a comprehensive portrait of their health using wearable devices, pharmacogenomics testing, and genetics testing, as well as wellness assessments. What we did with that was we would map a customized care plan based on a patient's health-related goals, what they stated what was important to them. Often that would be based on their cardiovascular risk or a genetic risk that they were concerned about, or even a concern about a medication that they're taking and a side effect that was on their mind. And the patients were able to achieve their goals by staying in regular communication by phone, virtually, or even in person with a team of health professionals. And it's not just the PCP, but also care coordinators, nurses, clinical pharmacists, nutritionists, and a behavioral health specialist. And so with human-wide, we combine the high tech with the high touch in an intervention that can provide truly holistic care to patients in a way that I know a lot of us as clinicians and as patients would desire. And it's the manifestation of the vision of precision health, bringing it into a clinical setting and making it reality for our patients. So now what we're going to do is look at a video clip of Dr. Russ Altman, who will be sharing the pharmacogenomics results with one of the human-wide patients.
Nice to see you.
You too.
I'm Dr. Altman.
I'm
Welcome
Debbie.
to the Pharmacogenomics Clinic.
Thank you.
In this clinic, though, we're focusing on your response to drug, and we've learned that we can find small differences in the DNA that might make you, for example, metabolize a drug more quickly and get rid of it, so it's not actually in your bloodstream as long as it might be for somebody else. Or it might work better for you than for other people because of a little difference in your DNA.
Well, specifically, I'm concerned about narcotic pain medications because I'm going to be having surgery, and the surgeon has strongly recommended that I take narcotic pain meds after my surgery for the pain.
Have you had bad experiences previously?
Primarily, I get really dizzy and disoriented, sort of drunk and, high.
Wow.
And I don't have any pain relief, so I just feel awful.
That's even worse.
Yeah.
So you're getting all the side effects, but not any of the benefits.
And then I itch. I itch terribly all over my
Very
everything.
common. There might be even drugs that have not even been released on the market yet that will be impacted by some of these genetic differences, and so it would be useful, even going into the future, to know about your status for some of these enzymes. So the first one that I'm going to highlight.
Great. So Debbie is a lot like a lot of our patients that we see in our practices, where there's a specific health concern that's not being adequately addressed in our traditional primary care setup, and yet she has to cope with it. And with Human-Wide, Dr. Russ Altman is an example of a clinician who was able to provide hope, because with the new streams of data, the pharmacogenomic data, genetic data, the data on psychosocial factors, and the biometric data, we're able to walk along that journey with our patients and address these concerns as they arise. And that's really the promise of Human-Wide. And with this approach in primary care, we were able to see meaningful results, and I'm going to share some of them with you. One is with the digital health devices. When the 50 patients who were enrolled were given the digital health devices, 50% of them were able to either prevent or improve the management of their chronic illness. The pharmacogenomics component ended up being very useful. Over 90% of patients had a clinically significant finding, and about 25% of those patients were able to have their medications adjusted, a medication that they were actively taking. And one example is a patient that I saw. His name is Eugene, and he was experiencing some leg spasms. He was taking a statin, which we know often can contribute to leg cramping. And based on his pharmacogenomics test, we were able to see that he's actually a slow metabolizer of statins, and we were able to adjust his dose, and lo and behold, his leg spasms abated. So the population health genomics screening that we executed ended up revealing these risks for genetic conditions that were previously overlooked. And so the example is that out of the 33 women who were screened for breast cancer risks, 5 of them ended up being identified as having very high risk. And then they were just enrolled in enhanced surveillance to mitigate that risk. And we'll be hearing from one of those participants today. And we also did qualitative interviews of both patients and providers, and we found that the intervention was feasible and acceptable to both patients and providers. And among the patients, particularly the patients with medically complex histories, really appreciated this close connection that they were having with their healthcare team as a part of this program. And they appreciated the fact that when they had a particular consideration, or if they needed their care coordinated, they knew how to access the right team member for their care. From a provider standpoint, in primary care, we are trying to address the high rate of provider burnout, and Stanford Medicine has made a lot of strides in transforming primary care on a large scale to address provider burnout. And Human-Wide's team-based approach distributes the responsibilities of healthcare across many different team members. Also, the connectivity to patients between encounters increase the value and the efficiency of the in-person visits. And so from the provider's perspective, they felt like there was an increased professional fulfillment related to the Human-Wide program. And then also, they felt like they could get their patients in at the right level of care at the right time. So as a next step, what we're planning to do is to deploy the most successful elements of Human-Wide throughout primary care and integrate them into our workflows at Stanford. And then in addition to that, we would like to see how we can share our findings so that we really can see precision health come to life here at Stanford and beyond. So thank you.
The initial participants in Human-Wide are excited to be engaged in a study that first is going to enable them to understand their health and their well-being much better, but also the information gathered from them in this study will enable us to design approaches to primary care that will benefit, we believe, hundreds and then thousands of other people down the road.
Human-wide represents the beginning of a movement.
Great. And so for the next 20 minutes or so, I'll invite our participants. These are clinicians and a patient who were involved in the human-wide intervention. And I'll start with Dr. Latha Palaniappan, who is a professor of medicine in the Department of Medicine. And she is the scientific director of precision genomics and pharmacogenomics in the Division of Primary Care and Population Health. Welcome. And next, I'll invite Nancy Shin, who is a clinical pharmacist and leads many research efforts as well as educational efforts on the ground in the Primary Care 2.0 clinic. And she has a specific focus on digital health and pharmacogenomics. Welcome. And then finally, we'll invite Deborah Spaisman, who is a patient who participated in Human-Wide and also is an employee at Stanford University. Welcome, Deborah. Excellent. So thank you. So we'll just start off with a few questions and then we'll open it up to the audience. So I'll start off with you, Debbie. If you could just share with us what your experience was like overall and how did this compare to your previous experiences in primary care?
Well, the number one interest I had was in the pharmacogenomics and the genetic testing, primarily pharmacogenomics because I was going to be having surgery. And I had, as you saw in the video, I was going to be having a prescription for pain meds for after the surgery, and I was very concerned about how I normally react to pain meds. But also, I do have a family history of breast cancer, so the genetics aspect was important to me as well. I would say the overall experience of Dr. Mahoney is my PCP. So getting to spend as much time with my doctor, with you as I did, was just an added bonus. Had a lot of conversations that wouldn't have ordinarily come up, and I really appreciated having that extra touch. So for me, the overall experience was very positive, and the bonus was having that pharmacogenomic testing and finding out that one of the more commonly prescribed pain meds, Vicodin, was not working for me because I am a slow metabolizer, in addition to the fact that my body doesn't have the enzyme required to metabolize that drug into the painkiller morphine. So I was given a recommendation to use Dilaudid, which is already in the form of morphine. It does not require the body to metabolize it. And the results were dramatic. I had pain relief. I had none of the negative side effects that I had with Vicodin or any of the other codeine or any of the other narcotic pain meds I'd taken before. And I had clear-headed results. It was really dramatic and made a huge difference in my recovery. I had 2 surgeries, actually, in the last 6 months.
That's fantastic. I'm so glad to hear that. Okay, thank you. So Dr. Palaniappan, I wanted to ask you about what your reflections are on the outcomes coming out of Human-Wide and what implications do you see?
So I really applaud Stanford Medicine for taking a design thinking approach to primary care. And what we saw in analyzing the data is that there were incremental gains and small wins with each patient. And we really need to translate that over larger populations and over longer periods of time to realize fully the promise of precision health. So I am excited to be part of this project, and I really did see that happen with patients like Ms. Spaisman. So for each patient, we collected over 200 additional pieces of data, and like Ms. Spaisman, 25% of the time we were able to make a recommendation on either a current or future predicted medicine that might need to be changed based on pharmacogenetic results. So pharmacogenetics is done by taking a saliva sample and spitting into a little test tube, and we mail it off to a company, and we test about 22 variants that give us your predicted response to over 400 medications. And the medications that we most often changed were statins, as Dr. Mahoney mentioned with her earlier patient, antidepressants, anti-anxiety medicines, and also medicines that are involved in the care of cancer, which we also found, and for future treatment, possibly, as well as cardiovascular disease. One of the things that we were trying to be very careful about is recruitment of diverse populations, because often race ethnic minorities can be victims of the digital divide. And we were very careful to recruit a very diverse population, and our most activated patient was an 86-year-old African-American woman. So I think we were able to accomplish that.
Great, thank you. So let's talk about the connected devices that were used in human-wide. So Nancy, maybe you could share what specific devices were used and what was the value that was added there.
Yeah, so every patient in human-wide received a wirelessly connected blood pressure monitor, a glucose meter, a scale, and for those that used their iPhones, we were able to utilize the pedometer function through their Apple Health Kit. And the value of that was all of these devices had corresponding apps on their phones that either connected into the Apple Health Kit or into Stanford's My Health portal, which integrates into Epic, which is our EHR system. And this integration really is the key part of all of this, because it automatically sends the data to us so that all members of the healthcare team can have access to patients' home data in real time, and patients don't need to manually record numbers and bring them to their doctor's appointments. And the reason why this data connection is really such a vital part of human-wide and really in our primary care setting is because it provides more information about their chronic diseases. We all know that chronic disease does not just occur at the doctor's office in that one visit. It's a continuum of care, and we can't always just rely on a few data points like a lab once a year or a blood pressure visit at one time. And for example, if a patient's A1C, which is the common standard measure of diabetes control, if that A1C is 7%, that's wonderful, and we might think someone's diabetes is well controlled, but it really doesn't give us the nuances of how often they're having hypoglycemia, how low their blood sugars get, how high they can go after eating. So really this home digital piece is a really key part of their management. So through all the data pieces that we got through human-wide, we were able to act on things that may not have occurred until months later at their patients' visits. So we were able to adjust medications, start medicines, discontinue medicines, send referrals to specialists, catch patients that were lost to follow-up. So really, a lot of the clinical actions were very valuable. And then in addition to the clinical actions, we also use those data points as touch points. So if patients were doing well, if they were meeting their blood pressure goals or catching up to the right amount of steps they had set for themselves, it was an easy way to just reach out to the patients and connect with them and give them a word of encouragement and really solidify that team-based care relationship that we have with them. And I think really that was the most valuable piece to the digital connected tools that patients had experienced.
And then I'd like to hear if you have any observations about some of the barriers to the technology as well.
Yeah, so surprisingly, the biggest barrier to the tools were the tools themselves. So even with our most tech-savvy patients, we did run into issues with Bluetooth connectivity, device hardware issues, software upgrades. And I think with any of us, really, anytime that we have an additional step we have to take to fix a problem, that kind of discourages use of that device itself. So there was a lot of enthusiasm, and patients really did want to use the devices, and some people had no problems. But if those type of barriers came up, it definitely did change the frequency of use of them.
Mm-hmm.
Great. So hopefully we'll see some improvements down the line. So then I have a question maybe for all three of you, and then we'll open it up to the audience. So if you want to make your way to the microphones, you're invited to do so. And this question is, what surprised you about the program as it evolved? And maybe we'll start with Latha.
So I was surprised that, despite the fact that we do have so much information in medicine now, that we were still able to, using these new technologies, incorporate new elements into our care of patients that, and frankly, I've read a lot of papers about pharmacogenetics and pharmacogenomics and genetic testing, and you really need to have the rubber meet the road to see how it is going to affect patient care. And I think that we did see in the 50 patients that we did have incremental gains, small wins. We're able to more precisely treat these patients, both for their current state as well as projected future state. So we were able to look at their family histories and, with genetic counseling, predict what diseases they might have in the future, what medications they might encounter, and be able to put in their medical record what to look out for.
Yeah, I see. Thank you. You, Nancy,
yeah, I think for me the most interesting thing was just to see how patients use their digital connected tools and how receptive people were, and some of them really viewed them as one and the same as their health goals. So as part of Human-Wide, people were also set up with one-on-one wellness coaching, and they really used the tools to kind of help track their progress. So I think that's just really supportive of how receptive people are, and if we have great tools that work well, I think it can really help and advance people's health goals.
Great, thank you. And how about you, Debbie?
For me, the most surprising thing was because I was so focused on the pharmacogenomics, when I had the genetic testing in that counseling session, my test did show that I was not at risk. I don't have the BRCA gene. I was not at risk for breast cancer genetically. In the counseling conversation, it was brought up that because of my family history, I am at a high risk. And as a result, my care program has been upgraded. I will be having more than just the annual mammogram. I'll be alternating every 6 months with a breast MRI as well, due to my high risk. And in addition, if you roll in the whole pharmacogenomics aspect, if I were to get breast cancer, pharmacogenomics revealed that tamoxifen, which is the most commonly prescribed medication for breast cancer, would not be indicated for me. It would not work as well for my chemistry.
Right.
So that was very surprising and fascinating.
Yeah, that was very useful as a clinician as well. I mean, I had been seeing you in clinic for years, and I think I was aware of your family history, but it wasn't until you went through Human-Wide and went through the genetics counseling that we were able to identify this elevated risk for breast cancer. And I'm not sure if Dr. Palaniappan, you can explain that a little bit.
So as Debbie mentioned, we were able to see, that she did not metabolize codeine as well, because that's a prodrug. And it's sort of, the FDA gives us, brings drugs to market when they work for a majority of the population, but there's edges that they don't work so well for. So in Debbie's case with the codeine, about 3% of people don't metabolize codeine in that way. So if you've ever had any problems with codeine, please come see me and we'll try to get you pharmacogenetically tested. But I estimate in this room there's maybe 6 people that have that. And we are also able to look at different enzymes for treatment of potentially cancer in the future and recommend potentially different drugs. For instance, we can, in the case of Eugene, we saw that he had a family history of heart disease. He was already on a statin, that he might encounter a drug that might be used to prevent clotting in the future, and we put in his electronic health record an allergy to that drug, So if he were to ever encounter it, we would use a different drug that he would metabolize a little bit better. So it has been very exciting to be very proactive about this. And I estimate, and I'll say it now, it's on film, that in 10 years that everyone in this room will have pharmacogenetic testing that influences their care. It is getting to the price point that I think it will be more generalizable. And I'm excited that we're doing the research here at Stanford to make that possible.
Thank you. And I'm glad you brought up Eugene, because that case really does exemplify how all the different data streams do come together and can be synthesized, because he also benefited from using the wearable devices, because he brought his blood pressure cuff home and noted that he had elevated blood pressure measurements. And in the office, his blood pressures were all normal. And so what ended up happening was that the human-wide clinical team diagnosed and then later verified masked hypertension, which obviously contributed to his overall cardiovascular risk. We mentioned that he had familial hypercholesterolemia. Well, we were concerned about that, and so it was really helpful to be able to then track him and prescribe the appropriate diet, exercise, and then eventually the medication that would help manage that risk. So perfect. Well, thank you. I think we have about 8 minutes to open it up to the audience. Hopefully there are some questions.
If it's okay with Dr. Mahoney, can I ask the audience a question? So if you don't mind closing your eyes for a moment, and just, if you're willing, raise your hand if you've had genetic or pharmacogenetic testing already.
Yep.
Wonderful. And please continue to close your eyes, and please continue to raise your hand if you've discussed those results with your doctor. So the results are, we've done surveys on this. Thank you. You can put your hands down and open your eyes. So I'll tell you what the results have been in the studies that we've done, and similar to this room. But about a third of people have had genetic testing or pharmacogenetic testing, and only about a third of those people discuss it with their doctor. And that's what we want to change through this process of human-wide and precision health. We want you as consumers who go to other sources to get genetic and pharmacogenetic testing to be able to discuss it with your physicians and have it improve your clinical care.
Okay, we have a question up in front here to the right.
Hi, so I had a question about pharmacogenetics. Is that something that changes over time, over your lifetime, your results, or is it something you can just do at birth and then going forward, so-and-so is, so instead of every time you go to the doctor and they tell you, are you allergic to X, what are you allergic to, and so on and so forth, if it's already in your medical records, that's something that could be done? Or
So that's a great question. I'll just paraphrase it and repeat it. So the question is, do you do just pharmacogenetic testing once, and is it good for your whole life, or do you need to do it over and over? So your genes don't change over your life. So theoretically, you could do it once. But what does change is our knowledge about those pharmacogenetic variants. So we currently test for 22 different variants for 400 drugs, but going forward, it will be even more and more variants and more drugs, and we'll have better evidence. So I tell all of our patients, and I probably told Debbie and others this, that this should not be your last pharmacogenetic test, and that you should do one in 5 or 10 years, because the evidence is going to get better.
Excellent.
Thank you.
Question. Yes, over here.
Hi, Cindy Murphy at With Health, and we use genomics with our patients to enable telemedicine across medical specialties, so I applaud you for your work. You brought up a point that is very near and dear to my heart, which is physician education and health literacy in a roundabout way. And that roundabout way was, how many of you have spoken to your doctor about this? And I think there are two very interesting components to that. One is health literacy of our patients, right? When you get a genetic test, how do we increase that health literacy for the people that are actually getting the testing? And then the second piece is, how do we better educate physicians around genomics and pharmacogenomics? As we know it takes a very long time to educate the physicians, and there's no compensation for it. So if you could elaborate on that, that'd be helpful.
Sure. So I'll go ahead and take that one, and I'll paraphrase it again. The question is on physician and provider education around genomics. And we did a survey of our physicians, and there have been national surveys as well that show that this is a gap. It's not something that was taught in medical school for a lot of the physicians. And every 10 years as a doctor, we have to take a recertification test. So I just took my 20-year board recertifications. I hopefully will only have to take one more. But so there are thousands of questions, as you can imagine, and there were only 2 on genetics and pharmacogenetics. So I think it is going to take a while to infuse into medical education, and that is a clear gap. So as part of this program, what we did was create a continuing medical education program for our physicians, and one that we are taking out to different areas. I also recently spoke at the American Academy of Family Practice and about this, because as you have mentioned, our patients are coming to us with the genetic tests, and so we really need to be prepared, and it's something that I'm passionate about as well.
I think what's really exciting about this evolution that's happening is that the price point is coming down on these genetics and pharmacogenomics tests, such that when we started to think about implementation within the Santa Clara team that was implementing human-wide, we decided to purchase tests for the providers and have everyone go through the process of submitting the results, receiving the results, receiving the interpretation from a consultant and expert. And so not only did they have this growing appreciation for their own clinical findings that came out as part of the testing, but then they can also walk their patients through, obviously, all the different steps and address any of those concerns with their patients preemptively because they've experienced it. Because as Dr. Lata Palniappan has pointed out, we didn't receive this training in medical school, so this is all new for us as well. So I'm glad you raised that point. And I think the next person is over here, and then we'll go to the back.
This is very exciting, and you guys are definitely in the forefront of the practice of medicine or primary care. I'm wondering if you expect, or what your thoughts are about the data set that you will have generated by the time that you accumulate more encounters, and whether you may be in a position to recommend more of a core set of genomic profiling. There may be recurring observations that you make that there are some particular genes that are much more interesting to study than others, and there may be a background that's more noise or more focused in unusual circumstances. I wonder if you could comment on that.
Dr. Palniappan.
So great question. So the question was, there's a large data set generated from this, and what will you recommend as generalizable in terms of genetic testing? And what I will emphasize is that we have tried to be in this program to be very evidence-based in what we offer. And so genetic counseling is always recommended before genetic testing, despite the fact that there are direct-to-consumer companies that do genetic testing. That is not currently recommended without genetic counseling. And Ms. Spaisman is an excellent example of where that was helpful, because despite being negative for BRCA, her family history still warranted increased surveillance. And so this is where it's important to acknowledge the limitations of genetic testing and to really understand that family history and other components can bring so much more to our care or add to it, as opposed to just thinking that genetic testing is the answer for everything.
Correct. No, last question in the back.
Yeah, thanks for a great talk. I think we're seeing employers adopt a lot of point solutions for diabetes management, hypertension, perhaps less so pharmacogenomics. But I was wondering, this seems like an approach to bring it all in-house under primary care, which makes a lot of sense to me. What do you think about the pros and cons of those two different approaches? And perhaps you've seen patients that use these employer-sponsored models, and how does that integrate with primary care?
Mm-hmm. Right, so I agree with you that primary care is very well positioned to implement a lot of the interventions, especially if we have most of our patients insured by value-based payment model programs. But then you open up the question, if I appreciate the question appropriately, you open up this question about whether the employer
has a stake in this and could actually benefit from providing either, let's say, blood pressure cuffs or the pharmacogenomics and genomic testing, and we're already seeing that evolving and happening today. So I think all directions sounds like it's a great idea. From a primary care standpoint, we do have a lot of contracts with employers in Silicon Valley, as you can imagine, and those collaborations have been fantastic because in that setting, we're able to truly see the value of prevention and prediction, and that's just very exciting. So I'm not sure if I'm answering your question.
Yeah, you are.
Okay, great. Well, I think we're out of time. My apologies, but I wanted to see if we could appreciate the panelists and wrap up the session. Perfect. And so now we're going to break for lunch. Lunch is outside on the lawn, and I'll see you there. Thank you. Perfect.
real pleasure. I'm Lawrence Baker, and I'm the chair of the Department of Health Research and Policy here at Stanford. And it is my pleasure to moderate, coordinate our HHS Spotlight session this afternoon. Of course, the Department of Health and Human Services and CMS within that particularly are central to the data and analytics ecosystem in healthcare. And we have two terrific speakers today to give us a chance to hear about things going on there and engage with us in some questions and answers about that. We have time for the two speakers. So our session will have first Allison Olschlager from CMS, followed by Don Rucker, the National Coordinator of Health IT, and we'll have those two speakers up here for a few minutes each, followed by a chance for some question and answer interaction with the audience. So be thinking of your questions and the things you'd like to ask. We'll have 15 or 20 minutes for that at the end of the session. So with that, I'd like to introduce our first speaker. Allison Olschlager is the Chief Data Officer and the Director of the Office of Enterprise Data and Analytics at CMS. She works in that role on transforming the American healthcare system by connecting people and data for the kinds of activities that we're talking about at this conference. She oversees the systems and the policies that govern CMS data sharing and organizing data that can be available to different stakeholders, researchers, academics, and others. She works on the processes and directs the public release of CMS data and information products, and manages the development of advanced analytics using CMS data that can help inform policy decisions. She came to her role at CMS from the Lewin Group. So please join me in welcoming to the stage Allison Olschlager.
Thank you. Good afternoon, everybody, and thanks for having me. It's always exciting to be the first speaker after lunch. Hopefully, you're not all in a food coma. So I'm here to talk today a little bit about what we're doing under the My Healthy Data initiative at CMS. My Healthy Data is one of 16 strategic initiatives that we have at CMS going on right now. But it's something that's really a priority for me and my team, but also for the administrator and for folks across CMS and across government. But before we talk about My Healthy Data, I just wanted to take a step back and talk about the scope of what we do at CMS, right? So across our three programs, we cover 140 million Americans. The Medicare program, which covers our aged and disabled population, the Medicaid and CHIP programs, which cover low-income enrollees, and the health insurance exchanges. And so when you think about the work that we're doing and the data that we have access to, right, it's enormous what we can do with our data. And that's one of the reasons that we're doing the My Healthy Data initiative. My Healthy Data started as an initiative around empowering patients with access to their data. But we quickly realized that it's not just patients who need access to their data, right? It's stakeholders across the delivery system, health plans that are making, decisions about the quality of care provided to their enrollees, providers who are making direct decisions about patient care, and then also researchers, right? There's so much innovative research that can be done using all of the data that we have access to at CMS. And so My Healthy Data is about all of these things, about empowering stakeholders across the healthcare system with data. And it's not just something that we're doing at CMS. It's a government-wide initiative led by the White House Office of American Innovation. I want to talk about two specific projects that we have under My Healthy Data that I think are going to be relevant to this audience. The first is access to data, access to CMS data for research. And I'm sure a lot of you are familiar with accessing CMS data for research, but if you're not, ResDAC and the CCW are great resources to kind of get started with accessing CMS data for research. But what I wanted to talk about here is the fact that we are, under the My Healthy Data initiative, really expanding the type of data that we make available to researchers. So historically, it's been Medicare fee-for-service claims. There are 40 million Americans enrolled in the Medicare fee-for-service program. But just last year, we announced Medicare Advantage and counter data would be available to researchers, another 20 million people. Later this year, we'll be making TMSIS, Medicaid data, available to researchers, and also data, what we call EDGE data, which covers enrollees in qualified health plans under the exchanges, right? So we're going from the 40 million in Medicare fee-for-service, their claims information, their health services, their prescription drugs, that sort of information to that type of information for 140 million Americans who are consuming healthcare in our system. We're also thinking about how we give researchers access to data. So about 5 years ago, CMS launched the Virtual Research Data Center, which is a way for researchers to remotely access CMS data and analyze it in the CMS environment. It's more cost-effective for researchers. You don't have to store the data on your site and deal with all the security issues associated with doing that. It also is more secure for CMS because we can, you're coming into our environment. We're not giving you access to the data in your space. But as technology has grown and tools have grown, we're coming to see that the VRDC hasn't kept up with the pace of technology, right? So we're thinking about cloud. Right now we're in an on-premise data center, but people want to be able to scale and do machine learning type analyses. So cloud is an opportunity that we're looking at to kind of grow our capacity. And then also new tools. We're definitely a SaaS-based institution. Government and academics are largely SaaS-based, but folks coming out of school now studying data science, they are learning Python and R, and so how do we enable those types of tools in our system so that people can do the types of amazing research that they want to do? The second thing I wanted to talk about is Medicare's Blue Button. So Blue Button is an initiative that we started in 2010. It was also a government-wide initiative around giving patients access to their healthcare data. And at CMS, the way we started was a portal. So beneficiaries would log in to their mymedicare.gov portal, and they'd be able to get access to their data in a PDF or text format. Medicare beneficiaries have a lot of services. They have a lot of prescription drugs. Think about the pile of paper that is if it's in a PDF format, right? And taking that to your caregiver, your daughter, your son, saying, help me understand this data, or to your provider, and saying, okay, here are all the prescriptions I have. So we, over the past few years, realized quickly that we needed a better way to give patients access to this information in a usable format. And that's why we launched Blue Button 2.0. It's a FHIR-based API that allows Medicare beneficiaries to direct their claims information, their healthcare services information, to applications and services that, and I think, oh, there we go. Lost my microphone for a minute. When we were designing Blue Button 2.0, we really thought about how do we build this in a way that we're using industry standards, right? That we're not going out and doing this on our own, but doing it in a way that matches what the rest of the industry is doing. So that's why we're using OAuth 2.0 for beneficiary authorization and using FHIR, Fast Healthcare Interoperability Resource, as the format for the data. HIPAA is obviously a big thing that comes into play here, right? Beneficiaries under HIPAA have access to their healthcare information, but they also have the right to share that information and to direct the covered entity, CMS, to share that information with anyone that they choose. Consent also comes into play, right? Making sure that the beneficiary actually understands what they're doing with this data, who they're choosing to share it with. And that takes me to my next topic, privacy and security, right? Privacy and security is a huge issue when you talk about giving data to applications and services, right? We start to move outside the bounds of HIPAA and into the realm that's covered by the FTC. When we think about privacy and security for Blue Button, we think about this in two ways. The first is, how is CMS protecting our systems, right? So those are the things on the left-hand side of the slide. We are doing system security. We do bug bounties where we actually have people come in and try to hack our system, and they get paid by how many vulnerabilities they find. We have a Blue Button terms of service, which means that any application that wants to connect to Blue Button has to agree to the terms of service, and we can cut them off if we think they're doing anything bad with the data. And then we monitor production applications blue button use. So the data, for example, are loaded weekly. There's no reason an application should be pinging the blue button system 500 times in a day for data when the data haven't been refreshed. We're also thinking about how we help beneficiaries make good choices about the applications and services that they're connecting their data to, right? So HIPAA says a beneficiary can connect their data to whoever they want, but we want to help them make good choices. So we vet applications before they're connected to Blue Button. We want to know, what are they going to do with the data? How are they actually helping Medicare beneficiaries? We want to understand their security platform and how they're protecting the information when it gets to them. And we want to understand how we want to see their terms of service that the beneficiary sees to make sure it's in plain language, that the beneficiary can actually understand how they're going to use their data, how they're going to protect it. Are they going to share it with third parties? That sort of thing. We also have a plain language authorization for the beneficiary when they're choosing to connect their data to an application. So when they connect their data to an application, it's kind of like if you log into a website with your Google credentials or your Apple credentials, right? So it pops up and it says, enter your My Medicare login credentials, and they do that. The second screen that pops up is a screen that says, okay, you're about to connect your data to ABC app. Are you sure that you want to do this? This is the type of information that we're going to be sharing. Have you read the terms of service? And here's a link to the terms of service. And there are risks associated with sharing your data. So make sure that you actually want to do this. And then at that point, they can either click accept or they can click deny. And then it moves forward, right? So it's about informing the beneficiary and helping them make the right choice for them. And then finally, if they want to revoke access, turn it off, they decide they don't want to use an app anymore, we have a dashboard that lets them do that. So one of the really exciting things about Blue Button that I'm seeing is there's all these great apps around, maintaining your personal health record, medication interactions, that sort of thing. But there's also a potential to use it for research, right? So when you're doing a clinical trial, beneficiaries are already consenting into sharing their data. What if they could consent to sharing their Medicare claims to identify adverse events? The data are refreshed weekly, which is different from the data in our research platform, right, which are refreshed on a quarterly basis. So it really gives you the chance to identify things like hospital admissions, readmissions, other types of events that you're looking for in your study. So if you're a researcher, you're interested in accessing Blue Button, how do you get started? So the first thing is to go to our developer sandbox. We've built synthetic data in the FHIR format. We have 1,800 developers working in our sandbox right now, building applications, using the synthetic data. Then once you've built the application or service that's going to connect the data, then you come through the production process and get production access to the Blue Button system. But that still doesn't mean that you get beneficiary data, right? Because the final step is getting the beneficiary to authorize access to the data to flow to your application or service, right? So it's these first two steps with CMS, but then the final step is actually engaging with the beneficiary and getting them to share their data. So with that, I'm actually going to hand it back over to Lauren to introduce our next speaker, and then I'll be out to address any questions. Thank you.
Thank you very much. As Allison says, there will be a chance to ask her questions after our next speaker, so if you have questions, hang on to them. But let me introduce now our second speaker, Don Rucker. I'll start with the most important things first. Don is a Stanford alum, having received his MBA from here and studied informatics a few years back. Since then, he's had 30 years of experience in the healthcare space, working as an emergency medicine physician in a number of organizations, working on the development of electronic medical records, spending 10 years as the chief medical officer at Siemens, and now working as the national coordinator for health information technology, where I have it written here, he leads the formulation of federal health IT strategy and coordinates federal health IT policies, standards, programs, and investments. I am just delighted that he's willing to spend some time with us today, so please welcome Don Rucker.
All right, thanks very much. Great. Well, thank you for having I have to say, visiting the Stanford campus when I started here as a grad student in Ted Shortliff's, what was before was even called medical informatics back in 1984, we were in 2 World War II trailers a couple feet from here. So the physical plant has certainly changed. So ONC is a staff agency within Health and Human Services, and we're in charge of, I guess, the regulation and the encouragement and the coordination of electronic health records. And as I think everybody here knows, that's been a bit of a long, arduous journey. And for a variety of reasons, mostly related to how we pay for healthcare in the US, the electronic health record, which of course is our central data store for health information, has really evolved to be more of a billing tool and a billing documentation tool than really what we might think of as a native store of actionable clinical data. Obviously, there's a lot of clinical data in there. Vast progress has been made, but there's a definite flavor certainly in all of the text notes around billing. And if we look broad picture at EMRs, I went into this field. The reason I actually went to Stanford after my residency was to actually automate healthcare so that we could get out from the no value add activities that are so much a part of clinical care, sort of so-called SCUT. We haven't yet to achieve that, and I think we have yet to really make the EMR a tool for deep and fundamental patient engagement. We had a number of great discussions this morning about social determinants of health and thinking about how to get patients back into the game. We need modern computing for that. We just need modern computing. This has not escaped Congress. So in December of 2016, the Congress passed the 21st Century Cures Act. Now, a lot of that act has to do with FDA and clinical trials, but there's a whole section in there on healthcare information technology. And just to do a little time warp, as you remember, December 2016, there was a presidential election. I think probably it was safe to say it was a surprise to everyone on both sides of the aisle. Of what happened there. I remember when I had my interview with Tom Price, I was joking with him. I said, I never expected to see you here in the seat as he was sitting at his secretary cabinet desk. And he said, yeah, me neither. So it was certainly interesting. The Cures Act, though, was passed almost unanimously by Congress, 390 plus votes in the House, and 92 votes, I believe, in the Senate, signed by President Obama. I can absolutely assure you that President Trump, Secretary Azar, the entire administration is very much engaged in the goal of the Cures Act, which is to get patients back into the game electronically. That means today getting patients' data on their smartphone. How do we go about doing that? That is really the nature of the game that we have to have. And Congress came up with a couple very specific provisions here that I think are really going to fuel the entire discussion of big data. Because, some of the talks you heard earlier today, it's worth understanding that those application programming interfaces and how they got that data was really pretty much one-off or very vendor-specific things. There really weren't sort of broad standards there. So how do we get to that? That's really empowering. The 3 things that Congress has in Cures that ONC is implementing. One is hooking the health information exchanges together, trust exchange framework, common agreement. That's a bit of a deep technical dive. I just mentioned it. If anybody is interested here, my guess is this is not your foremost interest. The second is Congress heard a lot of complaints about what's called information blocking, which is that providers will not share their data. And as you've observed, for those of you who are, economic observers as well as computational or clinical observers, in much of the American delivery system, the name of the game has been to buy as many hospitals as you can and become a price setter to payers. That is the name of the game. Obviously, one of the concomitants of that is a question of leakage, right? So how do you get the patients in? In that kind of an economic environment, sharing information is not necessarily the highest priority. So how do we do that? So Congress made information blocking of clinical information to patients illegal. In our proposed rule, which is out for public comment till June 3rd, healthit.gov, you can take a look. There's a couple simple PowerPoint slides that will give you the flavor of it. Unless you are a lawyer, you're probably not going to want to parse the 700 pages of explanation there, but the slides will give you the gist of it. So if you have a chance, take a look at that and put in your comments by June 3rd. That information block, and we've put in some exceptions on that, but the real game changer here that Congress came up with is the requirement that there be application programming interfaces without special effort. So think about, if you're designing, what does that mean? Application programming interfaces without special effort. What that means really has to be you're going to have industry standard APIs. That is really what that means. And in the smartphone world, that really is RESTful, JSON, and FHIR. I'm guessing a lot of folks know that, but they're very straightforward standards. They're materially easier for programmers who are not deep into decades of healthcare experience to implement. So we want a broad app economy. And the ONC, the Cures rule, our goal is to have an app economy. And what will this do? Well, first and foremost, it'll allow patients to shop for their care. Increasingly, we have a core data set that we're starting with structured data. Increasingly, it will allow patients to get their data on their smartphone and shop for it. We're exploring some of the ways to get price information in. In our rule, there's a request for information on how we might represent price information. More on that in a bit. But it is patient empowerment. And of course, patient empowerment may be on shopping. Patient empowerment may be on engagement, and it'll come in all kinds of forms. It'll be, where do I want to get a surgery or something? How do I manage my diabetes? How do I manage my coronary artery disease, CHF? I think there'll be all types of things. The technical standards are OAuth 2, very secure standard. It is the patient who gives the consent to the app. It's the patient who chooses the app. Under HIPAA, the big privacy law, once the patient has that data, it is their responsibility under the HIPAA right of access. There's a large national discussion about secondary uses of data. You're all aware of that. I think there'll be some of this. There's a lot of it floating around on the Hill. Ultimately, I think Congress is going to have to figure out what our country's approach is in comparison to GDPR in Europe, the California rule, the other state rules. But that information, the way we have this designed is that patients control their information, have access to it. And we want to get patients to be active participants rather than the passive participants managed by third-party payers here, which has really been the norm in the last 55 years or so since the start of Medicare. Those APIs, of course, will really be also some of the fundamentals of big data, as the conference has shown. Specifically, what we're doing there, what was identified is that the typical APIs are really queries with an N of 1, number of 1. So we're working with all of the big payers who, interestingly enough, have a devil of a time getting the electronic clinical information on your care, believe it or not, to build out population-level queries so that they can look at an entire population. Now, those things, we talked about the individual right of access, which is a patient right under HIPAA. Population queries of whatever format will need to be either IRB or signed agreements under HIPAA between the providers known in HIPAA speak as covered entities and other parties who in HIPAA speak are known as business associates. So those are not on demand, they're negotiated service level agreement type of thing. But we think this is going to provide a very different, very empowered way of looking at healthcare. As we look at medical data, right, in this conference, it's worth noting today, if you look at the landscape, in the broader American landscape, clinical data sits in 3 disconnected silos. One silo is sort of the clinical data, right? So lab information, imaging, DICOM, the charts, right? So that's one silo. The second silo, which is not really, amazingly enough, much connected to the first, are in quality measures, which are really one-way conversations to payers. And the third silo, which is not really connected to either of the other two silos, is financial data. So the X12, the electronic data interchange, all of this claims, payments, remittances data. So we have some interesting opportunities, not enough time to talk about them, to start thinking about getting all of this into an integrated modern data stream that is integrated, and that will allow things, for example, machine learning, to eventually think about replacing some of these quality measures, which are often gamed, with the broader analytics. Jeff Dean's talk this morning gave a flavor of how machine learning on vast amounts of data is more predictive than heavily classic statistics-based approaches on individual data. So we see the APIs and interoperability really framing a much broader discussion of healthcare and getting healthcare back where the rest of the economy is, frankly, today. As we look at AI, and again, obviously I'm a fan of that. It's very interesting seeing the second AI revolution having been on the tail end of the first AI revolution. Some of the claims could be verbatim substituted from 1984 to today, so it's a very interesting historical thing. And then, as now, often we focused on diagnosis. But I would throw out that the real big data issue to solve in American healthcare is affordability. Not diagnosis, it's not even interoperability, it's how do we afford care? So I think a focus of artificial intelligence on things like how do we get value, cost comparisons, just the vast sea of inefficient, labor-intensive operations is really what I would throw out to you to think about as part of this broad future of healthcare. It is a very exciting time. I think the data standards that we're pushing in conjunction with CMS has a companion interoperability rule asking the payers to expose all of their payment data, as well as their last 5 years or whatever other clinical data they have, can combine together to really have a very active, live, real-time operational feed to build new products facing patients. Both rules, which are in sync through the White House and Health and Human Services, are open for public comment until June 3rd. Our Trust Exchange Framework rules open until June 17th. I encourage you to take a look at those, put in your comments, and there's an official way of doing it. It's a extraordinary time to think about getting modern computing throughout American healthcare, right? Not just the Stanfords of the world, but to all Americans. And I think we have time for some questions. I believe the rest of the gang is coming out. Professor Baker and Allison. We're coming out. Okay.
Yes, thank you, Don.
All right, thank you.
Let's thank Don for his comments. And let me invite the two, please sit down. We now have a few minutes for questions from you all. There are 4 microphones that you know from the morning session. Please use one of the microphones if you have a question. Please, when you ask your question, let us know who you are and where you're from, and we'll take it away. Please, right here.
I am Jonathan Hare from WebShield and EP3 Foundation, and this is for either Don or Allison. First of all, I applaud what you're doing. You're sort of putting your data where your mouth is in terms of patient access and sort of the value of getting the data out there, and sort of creating a market for applications. Last time I checked, there was 350,000 mobile apps for healthcare, so having that, sort of the developer sandbox is great. The fly in the ointment is, you say you need to get patient authorization as the last step. But how do you know who the patient is? How do you know that's actually the patient? So last time I checked, the only thing that works at scale in terms of proofing a person is knowledge-based authentication. Asking you questions about data from like Experian or LexisNexis or Equifax. Last time I checked, you guys use Experian, is that right? So IRS has tried that. They use Equifax, which people tell me has actually more data about people in the US. And the IRS found they had a 70% success rate of fraudsters beating the knowledge-based authentication and taking people's tax transcripts because they wanted to commit tax fraud. And actually, claims fraud is actually a lot more lucrative than tax fraud. So the question is, would you consider providing or actually creating a challenge to get people inventing new ways to authenticate patients and scoring those that can be certified? Because that seems to be the weakest link. How do you know who the patient is? And do you have a program to make that happen?
It's a really important point. I'll start and then let Don talk too. But Don mentioned our interoperability and patient access rule, and it's not something that I and my team work on, but we have a great team at CMS that's thinking about these issues. And one of the requests for information that we have in that rule is around patient matching, right? So how do you actually know and link patients together, whether it's linking their data, authenticating them as an individual. So it's something that we're really thinking about and interested in kind of getting the perspective of stakeholders across the community around what are best practices in this space.
Yeah, obviously this is a major issue, and it really is a trifecta of authentication, are you the person, your consent to what you want to do with your data, and then authorization, which is what are you allowed to do, right? So you have to solve all three of these things. In the future, this is going to change, right? Because, for example, every smartphone and every browser uniquely identifies you from everybody else in the world right now, a little known fact, right? Because of the patterns of use. In the initial go-around, we're going to use the exact same authentication mechanisms in our rule as we do for portals. Now, of course, the difference between a smartphone and a portal is you have a portal for every separate provider. You go to 4 people, you have an illness that has not yet got an ICD-10 code, but it's called portalosis. Right, you have a perfusion, you want it in one spot. On the initial go-around, we're going to do the authentication by provider, right, that they know they've taken care of you. But over time, that's going to change.
Thank you. Let's go to the microphone in the back here.
Hi there, my name is Chetan Sarabu. I'm a pediatrician here at Stanford and also at a company called DocAI. Don and the team, I wanted to really thank you about articulating patient control and access to information and engagement. One group that has been really left behind in this revolution has been adolescents. Adolescent health information is very complex because every state has different laws around what an adolescent might be able to have hidden from their parents and vice versa. And so to get to the point, was wondering if you could talk about what the ONC is doing or can be doing to better support adolescent health informatics. For example, being able to separate out sensitive medications, diagnoses, so that adolescents are also properly empowered by this revolution that's happening.
Yeah, the heart of what you're hitting at is something that is called data segmentation for privacy, which is that you lock down some data in a different way than other data, right? And this is also a related issue in substance abuse. There's a law called 42 CFR Part 2 for folks who are in the substance use business. We have some provisions, again, you should comment. In fact, folks like APIs or don't like APIs, I mean, you should definitely comment about that. The people who don't want to share the data, I assure you, they're commenting on it, and they have scads of lobbyists working to prevent you from getting it. So you should comment one way or the other. The challenge with data segmentation for privacy was really highlighted by all of the big data talks, which is all of this data is correlated. As Jeff Dean said, it may not be correlated that the human eye can see it. The retina scans and the sex would be a perfect example, right? So you can hide, let's just take that example, because we had it mentioned here at the conference. So you can hide the sex from this, you can take the sex field out, but if you have a retina scan with a 97% area under the curve on data, the data is identified, right? So the classic example is HIV, right? So you'll hide the HIV diagnosis, but if you're on, Truvada getting CD4 scores, or your GPS on your phone says you're at the HIV clinic every week, how do you, right? The data is infinitely related. So I think data segmentation for privacy is very complicated. We've done some stuff with the American Academy of, the pediatricians, Chris Lehman's group, in particular, trying to get better support for pediatrics. But you've highlighted one of the computationally increasingly harder things to do, because the better the AI machines get at doing the correlations, the harder it is to hide anything. And that's, I think, the reality of it.
Okay, we'll go here in the front.
I'm an old guy. I'm an MD, PhD at Stanford in mind, brain, and computation. It's a center here. And Don and I were contemporaries.
Wait a minute, that means I'm old. That's what we're talking about by inference.
Sorry about that.
I'm denying that inference. I'd like that redacted.
Sorry about that, Don. So I'm 72. My parents are dead. At age 66, I started collecting my Medicare checks, and as an old epidemiology healthcare guy, my feeling that I was prepared to come up here and advocate was, baby, you get your check when you're 66 years old. Your de-identified, anonymized data is ours. Let's share the data. You've had your time in the sun. You're not worried about privacy and so on. So there's that. There's that, Allison and Don. And let me back off from that stance a little bit to maybe opt out instead of opt in. And I'll leave it there.
Yeah.
So mandatory or opt out?
Yeah. I think I would say that the issue of privacy and secondary use of
for
data.
Old guys, not not for the 25-year-olds.
It's all relative. Let me put that out there. I think it is obviously a major national issue, right? We have so much data, so many ways to cross-identify it. Obviously, there are major business models, right? Look at Facebook, you look at Google, maybe contrast it with Apple, which is pretty aggressive in stating that they do not share the data. So the Apple Health Kit, they make the connection, but they don't actually, unless you use iCloud, get that data computationally. My sense is that ultimately this is going to be a congressional, presidential, elected person issue. It's certainly not for us as agency employees, even somebody who's, a political appointee. I think this is something where we need national consensus, and, I think everybody needs to weigh in.
I agree. I think it's, privacy and security is a really complex issue, and Don mentioned the work that's going on in the Hill. I do want to point out with CMS data, it's there's two pathways, right? So there's Blue Button, which is definitely an opt-in to whether you're using an application or you're doing research with the data. But we also do have this pathway for researchers, as long as you have an IRB approved study, to get access to the CMS data. So it's there's two options, but it's always, privacy and security is always a complex issue that we're trying to thread the needle through.
It's worth pointing out to folks, and this is a subtle point, that HIPAA, so the privacy law, is actually very interesting. So we've all signed end-user licensing agreement on software. I agree, right? Click to the next thing. Do you agree? Microscopic print, some contract, right? There's not a human being who's not a lawyer who's ever read one of those, as far as I can tell, right? I agree. Yeah, where's my app? Where's my data? Oh, God, I got to click that thing again. HIPAA has a very different model, which is HIPAA is enumerated permitted uses, right? So in HIPAA, it's worth pointing out that it is only to be used for treatment, payment, operations, clinical data. One of the speakers this morning talked about the various privacy things. So HIPAA has a very, very different philosophy, and the enumerated use philosophy, that may be very interesting as we think about privacy, to think about it that way rather than anything you can dream up. Just throwing it out there for folks to think about.
And just to build on that, right, HIPAA does allow for research in cases where the study has been approved by
those are IRB, right? So that's,
right. So that's one of the authorized uses in addition to treatment, payment, and operations.
Thank you. We'll go here, and then if we have time, we'll go here.
Hi, my name is Shannon Muir, and I work at the Governor's Office of Planning and Research as a science officer for, get ready for it, the California Initiative to Advance Precision Medicine. But long before I went into policy, I was an academic for a very long time, and so I'm much more familiar with the big data aspects and programs that are happening at the NIH with Anvil and Big Data to Knowledge and All of Us and similar programs. And so I'm wondering if you can talk about any integration that's going on between HHS and CMS with NIH.
Yeah, absolutely. So one of the things that we've been thinking about with Blue Button that I mentioned is how do we promote promote the use of Blue Button for research purposes, and have been talking with NIH about All of Us through a partnership we call Sync for Science, which also includes the ONC folks, about how do we, All of Us, right, is collecting all of this information to do precision medicine research, and so how do we connect Blue Button and the Medicare claims into that system? So it's an ongoing piece of work that we're collaborating on.
Yeah, we in part fund Sync for Science, which is essentially, you can think of it as sort of smartphone Fire-enabled apps to allow your data to be shared with research, and how, what are the mechanics of doing that, because that is obviously one of the interesting potentials here in terms of trials. We're also doing some work on Sync for Genes that has some similar goals.
Thank you. So we have one last question here. If you can ask it relatively quickly, it'll help us out.
Yeah, so what about, so I'm in my 30s, so let's say I had prostate cancer, so my doctor made a decision regarding surgery or any other treatment because patients decided to share the information, and there is knowledge for those patients that decided to share the information on how to treat me. But I don't want to share my information to improve treatment for others. What are your perspectives for those kind of patients?
Well, that's an age-old question in economics. I think Dr. Baker can probably answer. This is the tragedy of the commons, I believe. Maybe you'll give us your perspective on that.
Actually, no, I'm going to turn it back over to the experts on this. No, obviously, data are valuable, and creating opportunities for research and respecting privacy are the kinds of issues we've been talking all about, and so trying to make sure we can take advantage of that.
I think when you look at the app ecosystem that we're jointly trying to put together here with the White House, and what we're really about is trying to do two things: empower the American public as individuals to get better control of their care, shop for their care. But we're also trying to build new business models, new ways of thinking about the world, arbitrage out many of the, frankly, cosmically wasteful things that go on in American healthcare today. And so when you look at the data, there's going to, even you see this with privacy, there are going to be all kinds of folks trying to build brands on new products and services, we believe. I know Administrator Verma, the White House, in many discussions with Jared Kushner about this. We believe that there are going to be new business models and new enticements for people to share. That is the goal here. It was mentioned that there's several 100,000 healthcare apps out there, but today those healthcare apps are notable for the fact they actually have no medical data, right? They may have your Fitbit data, they may have your diet data, they may have pictures of you playing with a cat, whatever. That's a computer science pattern recognition joke attempt, failed. But hey, you got to try. You got to try to be out there. But there will be fundamentally new business models. We would be stunned if they're not, that will be enabled by this. And the test of each and every one of those business models is, can they engage the public, right? Are they adding value? The ones that add value are going to succeed, and the ones that don't aren't. And we think that in that world, people very much are going to want to be part of it. And we've seen this in industry after industry after industry. You look at all of finance, you look at all of entertainment, you look at all of travel, you look at any number of verticals. They've been absolutely transformed by that smartphone, internet, IP address, RESTful JSON type of protocol. It would be really stunning if that doesn't happen in healthcare. I mean, we're sitting in Silicon Valley. I just can't imagine if, Bob and I around 10 years from now, that 20 years or 30 or 40, whatever, that we're not going to see scads of that.
Well, thank you both very much. Please join me in thanking our panelists for coming, spending your time with us, answering our questions. Terrific session. So we are going to wrap it up and leave the stage. Our next session, our next panel is on artificial intelligence. So stick around for that in just a moment.
Hi, everybody. My name is Natalie Pagler. I am a pediatric ICU doctor and the Chief Medical Information Officer at Stanford Children's. As an applied clinical informaticist, my team and I are responsible for optimizing our information systems and bringing new technologies like AI into the clinical setting in a safe and thoughtful way. We are constantly trying to understand what is being developed by our data scientists and figure out how to rigorously evaluate that so that we can truly and meaningfully improve patient safety, efficiency, and quality of care. So I'm very excited to introduce this next session, AI in the Clinic. It is my pleasure to introduce our first speaker, Marzia Ghassemi. She is an assistant professor at the University of Toronto in computer science and medicine. She was previously a visiting researcher at Alphabet's Verily and was recently named one of MIT Tech Review's 35 Innovators Under 35. Her PhD research at MIT was focused on creating and applying machine learning algorithms towards improved prediction and stratification of relevant human risks. Her work has been applied to estimating the physiologic state of patients during critical illness, something I'm very excited about, and modeling the need for a clinical intervention and diagnosing phonotraumatic voice disorders from wearable sensor data. Welcome, Marzia.
Hi, everyone. I'm Marzia Ghassemi, and I'm going to talk to you today about what my group does at University of Toronto. So we focus on learning healthy models for healthcare. And why do I say healthy models for healthcare? I'm saying that because, when I started my PhD, it was in computer science at MIT, and I had to, sort of figure out what I was interested in, and I thought, I'm going to work in health. And there's the simple, ideological reason of, improvements in health are going to improve human lives. And so that's a great thing. We want to do that. But what really interested me is when I would go to the hospital with friends that I had or other colleagues, I would see the same patient get very different treatment recommendations from different clinicians, even in the same institution. And when I questioned this, my collaborator said, we really don't have that much evidence to go on. We really don't know what it means to be healthy. We see people when they're really sick. And so being healthy is never a state we observe people in. In fact, we define being healthy as an absence of interactions with the healthcare system. So you are healthy when there's no data on you. That should worry you because we're at a precision medicine conference at Stanford. So what do we do now, right? We treat patients, there's medicine. What we do is we run randomized controlled trials, right? This is the gold standard, right? We have 2 medications, we recruit a study population, and then we learn some sort of rule with statistics or machine learning, right? The question is, do those results generalize, and for whom do we think that they generalize? So it's pop quiz time because it's the afternoon and you're all really tired, so we need to wake you up. All right, so question number 1. How many of the current treatments that are used in hospitals do you think, what percentage are based on randomized controlled trials? Gold standard, right? You want this to be high? It's not. It's 10 to 20%. So that's not good. Let's take something that we do have randomized controlled trials for, asthma. Lots of people have asthma, and randomized controlled trials were run to see what sort of treatments work best on people with asthma. Now, what percentage of people who have asthma now and are being treated with those recommendations do you think would have qualified to be in the RCTs that were used to design their treatment? Yeah, that was a good guess. 6%. 94% of asthmatics are in the exclusion criteria for the RCTs that were used to design their treatment. And this is not because of malintent, right? This is because when you're trying to study a mechanism, you remove all the variation and change one variable. And that's how we do this. But we're obviously missing a ton of nuance here. And so can we use machine learning to take all of the data that's available, all the things we've talked about today, all the things you've heard about, and say this is all really medical data in some sense, right? It's health data. It's how we're interacting with our environment, with other people. It's how we are healthy. Can we use that to learn what it means to be healthy? Well, yes, maybe we could, right? I'm here to sell you on the fact that you can, but extracting knowledge from healthcare data is really hard. Medicine is not new, and neither is machine learning. So the reason we haven't done this successfully so far is because there are differences in using data that is found as a byproduct of the healthcare system versus recruiting a specific population and studying one thing in that population. And so for reasons of heterogeneity, sparsity, and uncertainty, it is hard to do robust machine learning in healthcare data. And I think one thing that always concerns me, one thing that I like to highlight to anybody who's not, sort of a core machine learning person, is the machine learning people are all a little bit afraid of the hype cycle right now because there can be unrealistic expectations. So I have had clinicians come to me and say, I have the data, you have the machine learning. Together, we could, no. Anytime anybody says the machine learning with a capital T, you should run away. It's not good, it's scary. So what can happen in machine learning is that models can be very good, superhuman, at doing something that we have optimized them to do. But that means that they are often wrong in ways that humans are not. So the top row is a deep neural network telling you what it thinks the optimal king, penguin, starfish, freight car, and remote control are. These are famous examples in computer vision, by the way, like highly cited papers. We all know about this, right? It's in our limitation sections. And the bottom row is my favorite. That's adversarial pixel. So it's a 1-pixel attack on an image. So state-of-the-art neural networks think that that ship is a car, that horse is a frog, that deer is an airplane. And this is all funny and cute for us to say here because we all know that that ship is not a car. And so when we ask the model to explain itself, let's make this interpretable, right? It says, oh, I thought that this husky was a wolf because you put it in snow. You never showed me examples of dogs in snow, right? It's got to be a wolf because I've never seen this context, right? So there's the snow, that's my explanation. But this is okay because we are all natural-born experts in vision, in speech, in natural language. We are not natural-born experts in medicine. In fact, you have to go to school for a decade, right? To be able to interpret images like these. And so when you have an attack that turns these images into something, it's harder to detect. So I do machine learning for health, and I focus on 3 broad categories of things. I'm going to quickly cover some recent research and some past research, and then give you some sort of motivating examples for the rest of these talks. So the first thing I look at are what models are healthy? What kind of models should we be building in machine learning? I use predominantly the Mimic3 ICU data for a majority of my research. And I point this out because in a prior session, people have been talking about all the data that they use, what's available, what can researchers get access to. This is the only vetted use data set that's available with EHR data, de-identified, for researchers like me to use in benchmark situations. And it's data sets like this that move the field forward. This is our ImageNet. And you still have to go through access usage controls to get access to it. But it's available, and it's available on a timeline that makes sense for machine learning research. So if I take this data, the things that I could do are look at hospital decision-making or care planning, observe data, and then ask, can I predict in real time a drug, mortality, some sort of condition by some gap time before the doctor acted? The way you would translate this to a machine learning student is predict something important in healthcare. So that's objective number one. The first paper out of my PhD was looking at predicting mortality with clinical notes. Prior to this, people used labs and vital signs. They did feature engineering. But all of my colleagues at the hospital looked at their notes, which looked like this, which is why machine learning people hadn't used it before, because these notes are terrible. Everything fails. All of the state-of-the-art natural language processing just dies when you try to give it clinical notes. It's not like a Yelp review. So once you take this data, we use some machine learning techniques called topic models to model 500,000 notes from these, at the time, 20,000 patients. And this is cool because it's a generative model, right? You don't say, learn a model that's going to predict mortality best. You say, learn a model that explains the variation in the words that I see and the notes that I observe. Once you make that model, you then look at whether the latent states you've learned are correlated with the thing you want to predict, just first pass gut check. They are. It turns out you have increased enriched mortality for things that look like respiratory failure, and you have decreased mortality for things that look like cardiovascular surgery, which both make sense. And then you put it into a supervised, regularized prediction algorithm where you try to predict mortality in real time 24 hours before it happens in the ICU. And so it turns out for us that using the state of the art at the time, right? So these are the gold standards, SAPS and SOFA acuity models with gender, time of admission, things like that. That's the blue line, and that gets worse and worse over time. It makes sense. Those risk scores get stale. But using the notes, that's the red line, gets better and better over time. And when you combine them in green, you do best of all. That's great, but that was in 2014, and it is now 5 years later, and that AUC has not gotten higher. So the state of the art right now, if you look at the publications in my field, use GRUD, which is the last row in that table. It's a gated recurrent unit neural network that uses variable-specific time decays to deal with missingness. So maybe more complexity is not automatically better in medicine, right? Which is a hard lesson for machine learning people to absorb. And so the next thing is, maybe we need to predict something actionable in healthcare, right? Try number 2. So the next thing we looked at is, okay, forget about just using notes. Take it all. Take the demographics, take the vitals, take the labs, take the notes, process them the same way, turn it all into matrices, concatenate those matrices. I now have a matrix per person, which means I have a tensor across a hospital. That's great for a machine learning person, because with a tensor, you can do many different kinds of models. We can learn switching state autoregressive models. We can learn recurrent neural networks, long short-term memory, or convolutional neural networks. And when we tested this on trying to predict the need for interventions, like vasopressors, ventilators, non-invasive ventilation, and different kinds of fluid boluses, the neural networks improved performance. So using all of this data in a high-capacity model gives you better prediction, which is fantastic. But, they always ask you, can you interpret that? Which, from my previous example, you should know how I feel about that. Yes, you can. You can always create post hoc justifications using high and low capacity models, right? So we have good methods for doing this, feature level occlusions, or doing short-term trajectories with maximal activations. But the question that you should be asking is this really interpretable? Would a doctor really use this? I don't know, would you? I mean, most of the doctors that I worked with told me, no, I wouldn't really use that. So maybe the next thing is we should create something that's actionable in a healthcare setting, not just predict something. And so the last thing that I'm going to tell you about for research is we recently created human-readable radiology reports from clinical images. And this is cool because you're now getting an unseen image and generating the readable radiology report that somebody would like to have, because that's not something a doctor would like to spend their time on. You're actually working on a process that a doctor doesn't want to do themselves and freeing them up to do other things. And so we looked at all this. We had quantitative checks. We outperform state of the art. We have better readability and accuracy in 12 different categories. That's great. The last question that we asked a clinical collaborator about was quality check. And he said, it's right on most of these things, but some things it gets wrong. I worry about what it could get wrong. And so now the last thing I want to talk about is we're all going to rah-rah machine learning and health and precision medicine. And my my advocacy with machine learning students when I teach them, right, the computer scientists who I teach, is there are questions beyond the obvious here that you need to think really carefully about. So remember that first paper that I did in 2014? There are biases in data that reflect the biases of society. This is well established. We know that this is true. So I had a friend ask me, can you go back and check that that original paper that you did performs equally well across different categories of people? And I said, well, I put those data into my model. Of course they do. But I checked, and they don't. So really what we need to do is create actionable insights in human health. Because if you go back and take somebody who has a PhD in computer science, who does machine learning, and who wants to make a huge impact in this field, there is topic heterogeneity across groups in that original model. And importantly, there are unfair accuracies. We predict important clinical things worse for some groups using state-of-the-art models with the data that we have available. And because most of life happens outside of the clinic, these problems are not going to get smaller when we use passive data, self-reported data, search data, imaging data. They're going to get larger, right? And so it's important that people who are really entrenched in the technology and the data are aware of these issues so that when we're making tech, it works better for everybody in all settings. Thank you very much. And I think I hand this to you. All right, thanks everyone.
All right, thanks, Marzia. It is my pleasure to next introduce Matt Lundgren, who is an assistant professor here at Stanford of pediatric radiology. He is also the associate director of our new Stanford Center for Artificial Intelligence in Medicine and Imaging, and is going to share some of his work in bringing AI to imaging. And I'm very excited that he's doing a lot of that in the pediatric setting. So welcome, Matt.
Thanks. Hi, how's everybody doing? I'm going to start out with a question. This is a tough one. Who had a hit song when the first automated radiology paper was published? Was it Elvis in the 50s, Billy Joel in the 70s, Vanilla Ice in the 90s, or Taylor Swift in the 2000s? Now, bonus points if you know that Vanilla Ice's real name is Matt Van Winkle. The answer here is Elvis. In 1955, the first paper was published on using computers to make diagnoses in radiology, and that's Dr. Lodwick. He was a radiologist and a computer scientist, and he was the first, again, to describe this. He actually received a Nobel Prize nomination for this work, but you've never heard of him. And this is one of the reasons why. This is a 5-megabyte hard drive in 1955. It's hard to believe. It's just hard to believe. And so clearly the technical things that he needed to do what he knew was possible, they weren't available. But times have changed. We now have GPUs. We have powerful neural networks. You all know the drill. And now computer scientists are amazing. They can do things like tell the difference between parrots and guacamole and blueberry muffins and chihuahuas. It's incredible what they can do. But those of us in imaging, we sort of ask ourselves, why can't we do this for medical imaging? And can we do something that's a little bit more meaningful and impactful? There's a lot of reasons why we want to do this. There's a lot of errors in medical imaging, and clearly that's a problem. It causes patient harm, and deep learning can address that. And also, 2/3 of the world's population, we keep losing sight of this, 2/3 of the world's population does not have access to medical imaging. That's over 4 billion people. We can use deep learning to potentially address this, and that's what we try to focus on. So medical imaging isn't easy. It's a little bit harder than cat pictures. Most of the pixels in that image will tell you there's a cat there. But most of the pixels in the other image actually tell you this person's healthy. And it's only that little area indicated by the arrow that tells you that person actually has a deadly lung cancer. Making a mistake here is kind of a problem, right? So we need to get it right, but the question is still valid. Can we use these tools to make diagnoses? And if so, will they ever be as good as human experts? So that's really the question that kicked off what was my first collaboration with a computer scientist about 1.5 years ago, and that's with Andrew Eng and Pranav Rajprakash, who's his PhD student. And we looked at 400 x-rays. We gave them to 12 radiologists and said, here you go, make all your diagnoses. And then we also had a computer model. And we compared the performance between the two groups. And what we found was that the computer model did just as well as our human experts, 12 of them from around the country, which was incredible. And what's more is it only took the model 60 seconds to go through 400 x-rays, whereas it took our human experts almost 4 hours. So we knew we kind of had something on our hands, something pretty exciting. So we've spread out. We do things in neck CTs for the emergency department. We're looking at neonatal brain MRIs for congenital abnormalities. We're even finding cancer cells on pathology slides. And thanks to all of the projects that are going on around Stanford and collaborations with others, we've sort of formed a home base known as AMI, the Artificial Intelligence in Medicine and Imaging Center. This is led by Kurt Langlotz, and this is actually an old slide. We have 80 faculty now across 9 departments and 3 schools, and it's just continuing to expand. It's hard to keep up. We actually just finished the first in the world multi-center prospective clinical trial for these tools in the clinic, and that's actually led by Packard Children's Hospital by Dr. Halabi. But the interesting thing that we keep finding is that a lot of radiologists and pathologists clearly want to use these tools, and we get it. But we're getting a lot of interest from clinicians that don't normally interpret images. And here's what they tell us. So they have a patient, they're working them up for maybe pneumonia, and then they're waiting. They're waiting for a result from the radiologist because the radiologist's busy, right? They have a lot of things to do, they have a lot of things to prioritize, and they get overwhelmed. There's a lot of deep learning companies and projects that are focusing on making that radiologist more efficient, and that's great. But we've been wondering, could we potentially make the clinician more efficient? And could we give them the power of these AI tools to make diagnoses on their own in the clinic? And so that's the question we've been asking scientifically. We take primary care docs, surgeons, even nurse practitioners, and we randomize them into 2 groups. One gets AI assistance, one does not. We have them go through imaging studies. We do a washout period. This is kind of a classic crossover control trial setup. And then we switch the groups. So this way they kind of provide their own internal control. And we started with orthopedic surgeons. They tend to like to read their own imaging anyway, so we figured why not. They're very good at knee MRIs, and so we figured that would be a nice place to start. We gave them 120 knee MRIs, and we had a deep learning model trained on 1,500, which, by the way, we have released publicly, and that you can use to build your own knee MRI classifier. And we published this last year as well. Another project led by Andrew Eng's team. And what we found was that the clinicians were pretty good at baseline. If you compare that to human expert performance, they do pretty well. But when they get the AI assistance, they do even better. And they do even better across these categories. In fact, in ACL tear, they reached the level of a subspecialist expert radiologist performance, which was exciting because this could mean potentially less false positives, less people shopping around for healthcare because they're not getting the answer they need. So we do a lot of these other projects, but I just wanted to highlight this one in particular for the purposes of my broader talk here. And this is a really exciting project. We had contact from pulmonologists and infectious disease doctors from the University of Cape Town. They have a clinic where they treat HIV-positive patients and they work them up for possibly having active TB. Clearly not something we deal with in Silicon Valley, so we don't have the expertise here to help them. So they gave us lots of data, and we said we'd work together to try to create a tool that would make them better at making those diagnoses. So this is called ChecksAid. Pardon the name, it's just the best we could do. But we developed a tool now that can take some of the clinical data about these patients and the pixel data and help the clinician at the point of care make a decision. Do I think this person has active TB or not? And we base this, or the model was trained on using ground truth of sputum cultures, which is the gold standard. So if you look at their baseline accuracy, it's okay, it's modest. This is where the experts are. So this is clearly a very difficult task. This is about as good as it gets. And with our AI tool, they actually exceeded the experts in their own center, which was a pretty surprising result. This paper is currently under peer review now. We're excited to sort of release this. But just to give you a sense of how hard this is, I tried it. And this is where I fell. Unfortunately, it's a coin flip. It's really a difficult task. We don't see a lot of these patients here. And so this is a great opportunity for these clinicians. One thing you may have noticed was that in the one side, this is a modern healthcare system with advanced imaging. And on the other side, we have this sort of plain film, maybe heterogeneous infrastructure. This vast difference is really going to create a problem for deployment, right? How are we going to give these AI tools to assist these clinicians in these completely disparate situations? You might know where I'm going with this. We're going to use the smartphone, right? Okay, so this is the thing that's in everyone's hands right now. Some of you may be looking at your smartphone. It's okay. I do it too. But we know that more people have access to smartphones than they do to clean water. And so if we can leverage this to deploy some of these tools, we can potentially get closer to that thing I talked about earlier about addressing some of those disparities. So we developed an app. This is actually not me. This is actually done by Amir Kiani in the Andrew Yang lab, where you can take a picture of either a screen or a film and potentially receive a diagnosis to help you make a decision about your patient. One thing you might know about smartphone cameras is that they don't always faithfully reproduce what they're taking a picture of. So on the left, there's some artifact there, right? That's called moire artifact when you take a picture of a screen. And on the right, that's glare. That's from taking a picture of a film. And this is what happens when you use smartphone photos to work with your model. Your performance goes down. And this performance is too low for us to really use in the clinic. And so we've been working now on a project that's wrapping up using different techniques to improve the performance of the model, such as synthetic perturbations, specifically focusing on moire artifact and glare artifact, to address some of these shortcomings. This project is wrapping up this quarter. I'm working on, I'm at a university, I've got to work on the quarter cycle. So this will be coming up very soon, but we're very excited to see that our trend line is going back up. We're getting to the place where we can use these tools on a smartphone, and we're very excited to try this out in a clinical trial. And that might look like this. You go and see your doctor, you have a cough, the doctor takes an x-ray, is able to take a picture of that, confirm their suspicion of maybe you have pneumonia, and is able to treat you and send you home. Now, if you're at an urgent care clinic and you're a nurse practitioner, this could really enhance care, right? It could potentially provide some big advantages. But if you're in a different part of the world where you're using film or you don't have the same efficiencies, this smartphone platform would still work. And the idea here is that it's scalable, and we get to a place where we can, again, do some of the things that we set out to do at the beginning. So this is the tagline, radiologic expertise in a smartphone. Clearly has all the packages here. But I do want to thank the team. This is really just a small snapshot of the people involved in these projects I've just talked about. I'm very fortunate to be a part of it, and we're looking forward to continuing our work. That's all I have. Thank you. Am I supposed to walk back? Or? Oh, okay.
Thank you so much. Thanks, Matt. All right, wonderful. Okay, so moving right along, our next speaker is Jonathan Wilt. He is the Chief Technology Officer of Innovation Ochsner, an innovation lab and accelerator founded by the Ochsner Health System in 2015. He leads the product development team and is responsible for overall technology strategy, analytics, and data integration. Welcome, Jonathan. There you go.
All right, thanks. So like you said, I'm from Ochsner Health System, and I'm trying to give you a little perspective about what we do on the health delivery side. So I have some examples of models we implemented and even where we play in the space. So those of you who don't know, Ochsner's headquartered in New Orleans, Louisiana. We're growing across all Louisiana, Mississippi, Alabama. So it was a nice trip out here. It's about 90 and humid already there. And I want to show you this very complex slide about our IT strategy over the last 10 years. It took me a while to make this. And the reason why I put this up is because for us on the health delivery side, we do have really low margins. And as we grow, Ochsner's growing. We take over a couple of hospitals a year and partner up. As we grow, it's really important that we maintain IT, system-wide IT system standardization. It's very difficult for you to survive in your IT department to survive if you have 5 different EMRs across 3 states. It's very complex. So as we grow, it's very critical that we keep this in mind, that we can implement things system-wide quicker if we're all using the same platforms. So we have the Epic EMR, and our goal is to get that in every single facility as we grow. That leads to speed and flexibility for all of our interventions and hopefully innovation on top of that, which is part of the reason why the innovation department can exist is because we've done a fabulous job keeping system-wide standards and we can build on top of those, which led us into an AI strategy, which is nothing shocking here, but for us, we have a really great competitive advantage because of that system-wide standard. We can acquire a data set across every facility because we're on one EMR. If we're talking about nurse scheduling and we want to do capacity predictions, everybody schedules in one system. So it really decreases the complexity and allows us to take all of our data across all facilities and really quickly create models off of that. It actually gives us more time to shadow our end users and figure out the real workflows that are going on in the facility. Just because there's a flow sheet inside of Epic that's supposed to be documented in this workflow doesn't mean they do that. So the cleanliness of your data is very important. And because we have one system across everywhere, we get to spend time shadowing end users and developing the real workflow and extracting that data meaningfully. It also gives us extra time to keep up on research and then really brainstorm what can we do with this, making a clear intervention that can be distributed across all of our facilities. And in fact, it's actually probably the most important thing for us to do is create models that can affect outcomes. So pretty much the entire process for us starts with, if we knew this would happen, what would we do with it? And if we can't figure out what we would do with it, we kind of put that on the shelf until we do. So everything pretty much starts out, what are the outcomes we're trying to affect? How can we get there? And then we'll go through the process of extracting data and creating models that can facilitate that intervention. So where do we, Ochsner Health System, kind of play in this field? So don't be offended by anything on here. This is a representation of where, like, I personally fit into this and what we think we are the best at and where we're going to play. And a lot of it has to do with how transferable are models. So if it's quite transferable and I can buy this, in the bottom right corner, let's say I want a flight risk model where it's kind of low complexity and there's not a lot of variation state to state, and I can buy something like that and it's going to work well, I'll go ahead and buy that and I'll implement it right now. And there's really, it's as simple as that. I'll buy it and implement it. Medical photography, I'm not going to compete there. A small health system in New Orleans, Louisiana, I'm not going to compete there. Also, you don't need my clinical expertise to interpret and label this. You need some physicians. So I don't really play in the medical photography space right now. I don't have the most images, and I have lots of great workflow experience, but a labeled image versus all the new techniques we're developing doesn't fit with a health system. And then non-transferable models, let's say on the top. I would say the Watson cancer, trials that have been widely publicized, there wasn't really clear interventions. And so those are the things that we're going to wait to see if others can pull that off before we implement it. And then I play in the upper right-hand space. So where is there lots of clinical variability, lots of room for interpretation for the data that would make workflow experts and care delivery organizations experts? That's where we play. So one of those examples is predicting hospital-acquired C. diff in our organizations. We probably can't buy that model, and a lot of non-healthcare experts probably can't make those models in the interventions. So this is where we're playing right here, and I do have a couple examples of models we've created ourselves in the interventions and hopefully the positive outcomes that we can drive. So first one, it's not clinically related, but it does really affect our access in our specialty clinics. Sometimes there's long lead times, and patients not showing up for those appointments can hurt other patients and also cost the organization money. So the very first model we created 3 years ago was to prevent no-shows. So we started with the intervention. If we knew somebody wasn't going to show up, what would we do about it? And ultimately, we want the patient to commit to the appointment or cancel the appointment as early on as possible. Also, I can't afford to hire 50 people to call these people. I need existing staff to do it. So part of the challenge was, how do I educate my staff about what machine learning is, and then also make the calls every morning? And if you're making calls to everyone, stop making calls to everyone, only make calls to these 2 patients. So it was a great introduction, not just for us, but to the entire organization about what machine learning can do, what it cannot do, and then also different deployment strategies about how effective and costly is it to hire an entire team to do it, or train 2,000 nurses. So I didn't have the money to buy a whole new group, but we actually split tests right beforehand if I would call the patient versus their nurse. And we actually learned that nobody cares if I call, they care if the nurse calls, and they're more likely to show up. So it kind of justified getting the individual nurses to make the calls. It was our first foray into this, and how did we go about training? I drove to every single clinic over the summer and educated every single person. It was the first one. Nobody even knew much about machine learning. It was very, I would say, time-consuming, but it actually helped us learn about the culture that exists, and then how we can change that culture to make sure we're doing things smarter. We embedded all the tools directly inside of Epic. We didn't want to have a separate portal where they log into, so it's very important that it's right inside of their day-to-day workflow. So we created a little dashboard. For people calling everybody, stop, only call 2 or 3 per physician. For people calling nobody, please start the first part of your day making those calls. And so some of the outcomes. We used a couple million visits in our database. We evaluate the model right when the appointment is scheduled, and then every day leading up to that appointment, starting about 7 days out, because things can change. As you confirm the appointment, obviously, 2 days before, your risk can go down, or if something else happens, your risk can go up. If you're admitted a week before, your risk of no-show goes up because you might not even be discharged. And then our intervention was start texting those patients 7 days out. Get them to, our idea was cancel. If they already know they're not going to show up, cancel at least a week out so we can fill the appointment. And then if they're still on for the appointment, have their individual nurse call them the day before and get them to commit to it or cancel that appointment. So I think this is very obvious. Our success was determined by if you make your calls or not, and it's pretty proportional. You make your calls, no-show rates go down. If you don't make your calls, they stay the same. So we're lucky that with these learnings over the last couple of years, we've driven down our no-show rates about 20%. And that's super important, not just for us. It saves us a lot of money because we're seeing more patients, but our lead times for appointments are actually getting shorter. And with that, we actually created a program where we can text out waitlist offers. We had a huge drive that if we're going to get people to cancel their appointments 3 days out, we want a better way to fill them. So we're actually send out a couple million texts a year to get people to fill those appointments that are being canceled. Up into even 90 minutes before the appointment, we're sending out texts saying appointment's available, you can come right in. So it was kind of a combined thing. If you're going to get people to cancel more, you need a way to fill them too. So not just no-show rates going down, because you can just cancel them all and then not fill them, fill the appointments too. So that was a pretty good introduction for our organization into machine learning. And then this last year, we actually started a program to prevent hospital-acquired C. diff, and this is a very fun program for us. We started with the intervention, and this is going to be interesting, so remember this. We wanted to do an antibiotic review by pharmacists. So let's filter out 95% of the patients in the hospital. Who are the ones that are most likely at the highest risk of developing C. diff that are in here? Let's have pharmacists review them, do a med review, discontinue any antibiotics, that's what the literature shows, do daily reviews until the risk goes back down, and then furthermore, let's have staff just use soap and water and not sanitizer and really wash their hands really well. So we thought this probably has legs. We could probably drive down C. diff rates. Let's go ahead and make that model. So we pulled a couple years worth of admissions. It's not that much when you're talking about a lot of data, but it was enough to get a pretty good model. But one of the most interesting things was the feature importances for this model was actually quite different than the literature. It showed that PPIs and H2 blockers were 3 times more important to discontinue than the antibiotics. So the intervention changed really quickly. And I didn't have to drive to every clinic. There was only 3 pharmacists, so it was really quick to implement immediate results, and we're down about 40% over the last year just by really focusing those interventions on the patients who really need it. And that's kind of our goal, to have models filter out as many people as possible and do a more intense intervention on just the ones who really need it. Further examples, our rapid deterioration model. About 2 years ago, we implemented a new model to predict rapid deterioration. So vital signs labs are all kind of ticking their way down, and then what's the point where we really want to have somebody come out there? And we focused it about a 4-hour warning. We had a rapid response team who responded to codes, now respond to kind of pre-code alerts. So these are the people most at risk for having a cardiac arrest on the floor. And this has been wildly successful, lots of learnings in the hospital too. And at the facilities who are using this, we've actually driven down cardiac arrest on our floors by 25 to 40%. And we're actually continuing that, changing interventions as we go, as we get feedback. And this is kind of a progression of incorporating more people, more nurses, and the intervention has changed actually quite a bit over the last 2 years. Also, our CFO's favorite project that went live this year was more accurate at claims coding using artificial intelligence. So a lot of our coders would go through and review every single note and claim and then code that claim and make sure it was accurate. And if you're looking for different HCCs for your Medicare Advantage population, 95% of those could have absolutely no opportunity and you're just wasting your time. And as you hire more coders, it's more and more expensive to do the same exact work. It's not really value add. You're not hiring more doctors. You're just hiring more people in your corporate world. So we actually created language models, and they were very difficult. Like we said previously, word embeddings didn't even really work on this. We're actually using one-hots for our word embeddings, which was surprisingly more accurate than using anything right now. And we're actually filtering out 98 to 90% of claim reviews and really only focusing on those 1% to 2%. And we're getting really great sensitivity in there, and the coders are massively more efficient. So instead of having 20 coders review 50,000 claims, we're having 2 review 2,000 claims. So our CFO is ecstatic for us doing this, So again, not much time, but that's one example. One thing too, as a health system, I get to create data sets too. So for this, we had a moonshot. One of our things was, well, we have a heart failure program. We want you to step on a scale every day. If you gain weight, we'll tell you to double up on your meds. And the problem is, a lot of people refuse to step on the scale. So what if we could create our own data set of voices? New research shows that your voice could maybe show signs of heart disease. What if it could show signs of edema? And there is no data set. But as a health system, we actually are starting to capture a voice data set and marrying those up with actual radar measurements to get exact fluid levels inside of your lungs to see if we can do some research that can match that up. And then you have a completely passive intervention at home where somebody can sit on their couch and talk to each other, and then you're actually measuring, is there a risk right now of readmission? I don't know if it'll work, but again, as a health system, I kind of want to point out that we're not, locked into the data that we have in our EMR. We get to create our own data sets. So this is just a super exciting project that we're working on, and I am out of time. Thank you very much. Sorry.
Thanks, Jonathan. All right, and my pleasure to introduce our final speaker on this panel, Serena Young. She's currently a fellow at Harvard in their Technology for Equitable and Accessible Medicine program, but she previously did her PhD here at Stanford, working with Fei-Fei Li and Arnold Milstein, and we are very excited that she will be joining us back at Stanford as an assistant professor coming back this summer. Her research has broadly focused on the area of computer vision, machine learning, and deep learning with applications in healthcare. Welcome, Serena.
Thanks, Natalie, for the introduction. So today I'll be talking about some of my work on ambient intelligence in AI-assisted healthcare spaces. I'd like to start first by talking about a major problem that's happening right now in healthcare: burnout. Burnout of our healthcare providers. As our aging population continues to grow, and as healthcare continues to get increasingly complex, burnout in physicians and in nurses is becoming the new normal, affecting 78% of physicians and 62% of nurses. This can have severe consequences in environments like hospitals, where highly complex care takes place. Studies show that burned out doctors are 2 times more likely to make medical errors, and overworked nurses are associated with a 40% increase in the risk of patient death. I believe that artificial intelligence, AI, has the potential to make a big difference in tackling this problem. If we look at other industries like driving, we're already beginning to see the potential of AI in providing constant awareness and untiring assistance to fatigued humans who are susceptible to error. And so this naturally leads to the question, can we leverage AI to provide much-needed assistance to burnt-out physicians and nurses? I believe a key piece of the answer lies in the physical space of healthcare delivery. If we look at these physical spaces where healthcare is actually being executed, our hospitals, our clinics, our assisted living facilities, these have remained largely unchanged for decades. And so the goal of my research is to endow these healthcare spaces with ambient intelligence. In other words, to turn them into intelligent environments where AI can be used to assist with complex care. So first, what exactly is ambient intelligence? Well, this term was first coined by Roll Piper of Philips in 1999, where he described it as following. The future will be one where our environment satisfies our needs, mostly without our having to think about it. The intelligence is ambient, much like the light in this room. And if we think about an environment like a hospital, we can see ambient intelligence as being provided through visual sensors that are embedded in the environment and that can perceive and interpret what's happening across a hospital at every moment in time and use that to assist with clinical care. Now, what's needed to achieve this? Well, the first step is to actually build this sensing capability into environments like hospitals. Hospitals now are simply not equipped for ambient intelligence. They're not capturing the visual data that would allow automatic recognition of the activities that are happening. And so to begin, we need to add visual sensors to a hospital that can provide this sensing capability. Second, once we've done that, we need to tackle the main technical challenges of developing the computer vision algorithms to be able to recognize all of the activities that are happening. A key ingredient of this is visual understanding of human activity, being able to recognize and to interpret what people are doing at every moment in time. This is a core problem in the computer vision community more broadly, and it's also the main technical focus of my research. So over the course of my PhD, which I also completed here at Stanford, we implemented this vision for ambient intelligence sensing and practice at 2 partner hospitals, at Lucille Packard Children's Hospital at Stanford and at Intermountain LDS Hospital in Utah. And in each of these, we equipped a pilot hospital unit with about 50 visual sensors in both patient rooms and corridors. Our first collaboration was with LPCH and started in December of 2013 at the beginning of my PhD. It took about a year to set up the project and to get the necessary approvals. And then once the sensors arrived, it took about another year and a half to go room to room and to physically complete the installation. At our second site of Intermountain, we were able to leverage the precedence of the first site in order to achieve a much faster installation at just over a year in total. So these are some photos showing examples of the sensors mounted in our pilot installation units. And we chose to use privacy-preserving depth sensors, which collect these silhouette-looking images that are based on distance to the sensor, such as this example shown here on the right. And here are some examples of the depth data streaming in from across the unit at LPCH. Now, in the remainder of this talk, I'd like to briefly highlight some pilot studies of ambient intelligence that we've pursued with our collaborators. The first of these is monitoring hand hygiene protocol compliance, which is an important factor in the prevention of hospital-acquired infections. And this was joint work with our collaborators at Stanford, LPCH, and Intermountain. So in this study, our objective was to be able to recognize when people are performing hand hygiene, in other words, when they're using the hand hygiene dispenser, and also to be able to recognize when they're doing it, whether they're doing it when they should be. And so in order to do this, we took a deep learning approach and trained a convolutional neural network to recognize instances of the hand hygiene action in depth images. But there were some additional technical challenges that we needed to consider. The first is that these depth images can capture the scene from very diverse viewpoints due to physical mounting constraints of mounting these sensors. And so in order to address this, we used a convolutional neural network model for recognition, but importantly, we extended it to be able to be robust to these diverse viewpoints. A second challenge is that what we ultimately care about is actually compliance, whether people are performing hand hygiene when they should be. And we can define compliance here as performing hand hygiene before entering a patient room. But the act of hand hygiene itself doesn't need to happen right next to the patient room. And so this requires being able to track across sensors. And so in order to address this challenge, we combined our algorithm for hand hygiene detection together with a method to track people's movement across sensor views. And what we found was that our algorithm for hand hygiene detection works very well in practice. I've shown here a 2-hour window of time and the hand hygiene events that are detected in one hospital unit. And what we can see here is that our algorithm in the 4th row is able to perform very close to the ground truth at the bottom. And also that it takes up to 4 or more human observers to be able to match the algorithm. Now, using our method for tracking human movement, the tracks around a unit look something like this, where you can see people moving in and out of patient rooms. And so now putting everything together, we can tag a person as being compliant, the example on the left, if they use a hand hygiene dispenser here before entering the patient room. Whereas on the right, the algorithm tags this person as being non-compliant because they walked directly into the patient room without using a hand hygiene dispenser. So we've seen how ambient intelligence can be used to monitor hand hygiene in a way that's 24/7, that's untiring, and at essentially no human cost. But now, how can we expand from detecting this single action to being able to recognize the many clinical activities that happen in complex environments like the ICU? And so this leads to our second pilot study, recognizing patient mobilization activities, which takes the first step in this direction. And this is joint work with collaborators at Stanford and Intermountain. So in environments like the ICU, nurses will periodically perform patient mobilization activities for patients who are able to start moving around a little bit. And this can include things like getting a patient out of bed, transferring them to a chair, moving them back into bed, and so on. Studies have shown that early patient mobilization is important for preventing complications like ICU-acquired weakness and prolonged hospital stay. And so in our work, our goal was to develop an algorithm that could automatically recognize these patient mobilization activities in depth data. In order to do this, we can take a deep learning approach as before, but here we have this additional challenge of how can we distinguish between multiple fine-grained activities that can look visually very similar. This requires rich temporal modeling of the depth data over time. And so in order to address this, in my work, I've also developed deep learning models for video recognition that address some of these challenges, but I won't go into detail about these today. Instead, what I'd like to show you is that using our algorithm, we're able to produce temporal detections and timelines of activity that looks something like this, where you can see the patient being helped out of bed, helped into a chair, and here someone being helped back into bed. And one thing that I want to point out here is that we can use these discernments for things like making sure that protocols are being followed. But it also is just a really rich source of data that we can use to study at scale what's actually happening in hospitals and how this can correlate with things like outcomes. And we can also see that using computer vision, we're able to recognize not only that an activity has happened, but also richer characteristics like how long the activity took or how many people were involved. This is another example here of a slightly healthier patient who tried to get out of bed, changed their mind, got back in, now is getting out of bed again, and is going to walk out of the room. And this might be something that would be good for nurses to know had happened. Okay, now finally, I'll briefly describe a third pilot study, this time in a different type of healthcare environment, assisted living facilities. So in this study, we investigated activities of daily living that are important for senior well-being. And this was a joint work with collaborators at Stanford and Unlock, Senior Home Center in San Francisco. So here we studied these activities of daily living, some of these shown in the table here. And if we look at these, we can see that visual data can actually be very informative for many of these activities. And so in our collaboration, we collaborated with Unlock to install both depth as well as now thermal sensors in some of their rooms. And here, thermal sensors, these provide a complementary type of image data to the depth sensors that also obscures identifiable information. Here are some examples showing the multimodal sensor data that's captured, where on the left here we have depth images and on the right is thermal. So now using these sensors, we've developed computer vision algorithms that can produce long-term analytics of things like what is the distribution of time a patient is spending across different types of activities like sitting, standing, walking, sleeping, and so on. We can also investigate a particular activity in more detail. For example, how many hours of sleep each day a patient is getting. And we can produce visualizations like these spatial heat maps that show where in a patient room the patient is tending to spend most of their time for particular activities. And this can be useful for things like detecting loitering near a window or a door, which may be a warning flag for depression or delirium. Okay, so in today's talk, I've briefly described our pilot implementations of ambient intelligence and some initial studies that we've pursued with our collaborators. But we're only beginning to scratch the surface. And so moving forward, my goal is to be able to develop the computer vision and AI capabilities to enable us to fully harness the potential of ambient intelligence broadly and deeply across a wide spectrum of clinical care. And I envision a future where ambient intelligence is going to become a core component of systems that can provide real-time assistance to overburdened nurses and physicians. And it can be a constantly aware and untiring assistant that can watch for error during complex procedures, monitor patient status when doctors and nurses are not at the bedside, provide automated documentation of patient care activities, and more. And finally, I'll conclude by saying that as we approach the 2030 problem, which is the year when the entire baby boomer generation is going to become senior citizens, our ability to deliver quality healthcare to this aging population is going to become a serious challenge. And I believe that an important part of the solution is going to be AI-assisted healthcare spaces, where ambient intelligence fused into the environment is going to become invaluable assistants and partners to clinicians and caregivers. Thank you. So I think
Great job,
come
Serena.
back out.
So go ahead and have a seat, and I'd like to invite all of our panelists up to the stage for a Q&A session. All right. So while people are making their way up to the microphones, I'll just start with a kind of broad question. We've got many different perspectives here from the machine learning, data science world and the clinical world. What are some of the challenges that you see in bringing these two worlds together and meaningfully transferring data science, AI into the clinical setting?
Well, I can start. Definitely from the health system side, we want to incorporate as many things as possible, as quickly as possible. We still see cost as a barrier where we have a lot of cool technologies, but the cost to implement them and ultimately track them over time, just from a people perspective and change management, is really high. So I know this is something we're very aware of, that the projects that we choose and the technologies we implement have to be manageable long term and not just through a pilot phase.
Absolutely.
I think I'd like to see much more robust human factors considered in all of these deployments. I was telling you, I trained this fancy model, and I had several hospitals say, "Can we deploy that?" And my response was, "Well, when? At morning rounds, or do you want me to text it to you? And colors, pictures, like what?" Actual text. These are not questions that a machine learning researcher or a machine learning model should be tackling. There's a whole robust, deployment science space that needs to be investigated, because when I asked the collaborator, what AUC do you want? What accuracy do you want? What positive predictive value? He said, well, I can look at two things in the morning. You just pick the two things, which is a very different objective function, I think.
And from my perspective, I think that one of the things that contributes the most to success in some of these projects is really deep conversations between clinicians and machine learning researchers. I think I've found for myself, just the more you really, understand deeply about a problem, not just, okay, this is the data set, this is the initial clinical problem, but I want to understand, how is this going to be used? What are the weaknesses now? Also, I want to understand what are related problems and to be able to synthesize all that together, which informs how we actually want to design these algorithms. I think that makes a big difference from my perspective, and I think that also from the clinicians we've collaborated with, I think their finding has also been that the more time they spend understanding how machine learning actually works, what are the capabilities, it can also help them think more clearly about how should we tackle this space of problems, what should we do first, what are the challenging cases and problems that we should discuss in more detail and convey to the machine learning researchers so they know how to tackle those.
Absolutely.
Yeah, we spend a lot of time in teams as part of the center, and I think that's one of our strengths. We have clinicians, we have computer scientists, but we also have law students and business students and others. I think that really helps us sort of think about the comprehensive work that is required. I mean, the last mile is obviously the hardest. I'm sure that's been said many times. And getting these things deployed and having them used and then evaluating them in that setting is not trivial. And the more we can get computer scientists and other experts from around the university and certainly around industry to join us and work with us on those problems, it makes everything better. And so that's what we've really found is, multidisciplinary teams are key.
Absolutely, yeah. And I think, really having the experts in the change management and the deployment and the implementation science, clinical informaticist is key. And I think one of the things that you guys have touched on is it's important to understand the quality of the model, but then also thinking about what is the intervention piece, and is it worth doing that intervention, and how do you set the cutoffs for that model?
Just to kind of add on to what Serena was saying, just have an example of failure from our side. Right. We didn't communicate well enough with our physicians on our deterioration model. We wanted to send real-time alerts to doctors who are rounding, interrupt their day and say, go immediately to this person. And we thought it would be the model would be the best if it could predict it as early as possible, which turned out to be wrong, as a wrong assumption on our part, because we didn't really have those conversations. We kind of just assumed, obviously, they'd want to know earlier. That's not the case. They wanted to know at the sweet spot where we know that they're deteriorating and I still have time to do it, but I don't want to know 12 hours beforehand because I'm going to show up and just kind of shrug my shoulders. Mm-hmm. So that was a failure on our part, not having those conversations and involving those physicians early enough on, where we trained the model incorrectly. And we had to go back, redo the model, and then tailor that at the 4-hour mark. And then after that point, they started liking it, and then they embraced the model a little bit more and worked with it better.
Good example. All right. We'll take our first question from the audience.
Thank you. So I have a question. I'm a biomedical engineer, also working with patient health data, and I'm very concerned about two things. First of all, is when I design a machine learning algorithm, I would like it to be used in a hospital, but I don't know if there's any strategy when it comes to if it needs any FDA approval, or if it can be legally used in a clinic. And secondly, I don't really know how physicians feel about using algorithms, especially when it comes to diagnosis. Are they reluctant to use it? Are patients also, so what do patients feel being diagnosed by an algorithm rather than a person?
Matt, do you want to?
Sure, yeah. I mean, to your latter question in terms of how patients feel, I think, we're in a Silicon Valley, so it makes our, sales job a little easier in terms of is this a good idea or not, right? But that's not true everywhere. I think that there has been plenty of discussion regarding the interpretability, and we've talked about it here as well. Not every physician needs to see that it's interpretable. We use scores all the time that we have no idea the logistic regression, that even the data sets that they're based on. In fact, the Wells score, for example, for determining whether someone is at high risk for a PE, did you know that was a small group in Europe that study was based on, and yet we apply it to everybody, right? So we don't know a lot of the things that we claim to know, and so I think that the interpretability might be slightly overblown. But in terms of physician adoption, I think what is important is having a physician in the loop or a clinician in the loop. And you may have noticed from some of the things that we've talked about, no one is saying we're going to completely eliminate the need for radiologist or whatever that whatever function that model may perform, you have a physician in the loop that knows, right and wrong and can have some clinical judgment. And that's critical, I think, for deployment. I think ultimately that'll be critical for how these models will be used. And there's plenty of precedent for that. Just it didn't have the term AI used when it was put into clinic.
So one thing that Serena pointed out that I really liked is, burnout is real, right? There are extraordinary demands on a clinician's time, and often we're demanding that they interface more with medical record systems or devices than with the patient. They're not incentivized to spend any time with the patient. But there are many really nice papers that have come out recently that have shown pretty robustly that compassion is a really strong explanatory variable in patient recovery, right? So I gave a talk a couple of weeks ago in front of a mostly tech audience, and one of the questions was, so you're saying that you can improve medicine, you can make more doctors like Dr. House. And I was like, did we watch the same show? He was a horrible person. He's a drug addict. So no, I don't think that the goal is to make more doctors like Dr. House, right? It's the opposite, right? If you have tools that can improve some of these tasks that we know are really bad, right? We know that they are cumbersome. We know they take a lot of time. We know that they don't allow you to provide the same attention to compassionate care. Then maybe we can actually improve healthcare in the clinic.
All right, next question.
Thank you for the talks. And I have two questions for Matt. And the first one, when you say we can use the CT scan images for diagnosis, and I'm wondering if you also include the clinical information, like the characteristics for the patients, can you make an even better diagnosis? Do you have a conclusion?
Great question. That's actually something we're doing right now. One of the many projects is, I think what she's asking, is, if anyone didn't hear that, but it's to use clinical information as well as the pixel data together to make better decisions. And clearly that's what radiologists do, right? What you've just said. The other piece I'd add to that is using priors, right? So a lot of radiology is saying what's changed from the last time to this time, but having that clinical context is exactly what we're working towards. And we sort of touched on that with the TB model, as you saw. That's such a difficult problem that chest x-rays don't give you all the answers. We found when we have ground truth, the chest x-ray can't tell you everything you need to know. You also have to know how that HIV positive patient is doing with their HIV, because if they're incredibly immunosuppressed and there's an opacity in a suspicious region, that's highly likely to be pushed towards one diagnosis over another. And so that clinical information is critically important. Now, in terms of CT scans, one interesting thing that we found, and I don't know if a lot of people know this, but you see a lot of these models that are able to detect intracranial hemorrhage, for example, right, on head CT. One group tried to use age to improve the performance of the model, and what do you think happened when they used age? Nothing at all, because if you show a model enough examples of someone's head at all these different ages or whatever, it's already taking that into account, right? Because as you age, your brain shrinks a little bit, you get calcification, there's all these things that happen to you, so the model already knew how old you were, whether you told it or not. And that was a really interesting finding. So I think having the clinical context and what we're trying to focus on are things like absolute change in labs or vitals or other critical things. We're specifically thinking about PE in our lab for this project, but that's a great question.
I have another question. When you say maybe in the near future we can use this, or the doctors can use a smartphone for using deep learning models for diagnosis, but I'm wondering the current smartphone can hold so many layers in a model. What's your plan to boost the DL model in the smartphones?
Right now, it still runs off the cloud, and that's the one limitation. You'll need some internet connectivity. That's a good point. When doctors are using this, the target audience, at least at this point, for some of the trials, actually not as much in the Stanford setting, or actually in other healthcare systems that I'll, the moment leave unnamed, but they actually have to wait sometimes 2 to 3 days for a decision. They're in an urgent care. And so they actually just need to confirm what they believe is happening. So these are more modern healthcare environments. But to your point, we'd love to get to a place where we're at full edge deployment, and that's still an ongoing effort. I mean, everything I showed you is very, very new. Yeah.
Thank you. I have one more question for Serena. Sorry. Okay. In your pilot study, in the hospital, you use a sensor camera to catch activity in the hospital. Also, in the later, you use the real cameras to catch other scenes. I'm wondering in which case the sensors are better than videos, or if you use the videos at the beginning, whether the challenges around the sensors can be tackled.
So I think if I understand, your question is, how does our choice of, for example, depth sensors affect our recognition ability of our algorithms as compared to if we were to use standard color cameras? Yes. I think that there are different modalities, right? So with color, you can obviously get a lot of appearance information. You get typically also very high resolution information if you'd like. With depth sensors, they're typically a lower resolution, and you don't have that appearance detail. And so these are advantages where color has benefits. On the other hand, depth does have some advantage in the fact that because you have this distance information, it's very easy to segment people and objects to know that someone is standing in front of another person or where an object is without needing to reason on the appearance of these. So there are some benefits with depth as well. I think overall, it is still typically easier to recognize things and to achieve good performance using color data, but you can certainly do a lot with depth already.
Okay. Thank you for the answers.
Thank you. I think there's a question in the back.
Hi. So my question is, how do you grapple with adversarial perturbations with regards to the CT scans? Like, do you ignore it because of the implausibility of that data being injected into your system? Or do you regularize your models? And were they considered when you looked at the, when you're showing the bar plots? The radiologists were not susceptible to those adversarial perturbations, but the ML algorithm surely was.
Great question. I think we haven't spent a lot of time, concerned with all the different perturbations that you can create to fool the model. I think we talked about, what we're less concerned about some. Again, not that we're not concerned at all, but a nefarious character trying to, fool into saying there's a hemorrhage or not hemorrhage. But one thing that is real, and one thing I should have mentioned about the knee MRI project, we didn't, cherry pick the test set or the training data. We didn't take out all the ones that had motion or, knee replacement surgery, right? These are real world situations that break models all the time. And if you haven't taken those things into account, so I would actually focus more on, real world problems. In fact, we had, again, going back to the concept of a hemorrhage model, pretest probability is higher if you're seeing a lot of motion artifact on the head CT because the person's probably got a head bleed and can't sit still, right, and they're being scanned. So, there are things like that, but I would put more in the bias category. But in general, though, it's really important to see how these models actually perform on real-world data. So we tend to try to take prospective straight off the scanner. We don't try to, again, cherry pick because I feel like that, as you're suggesting, will end up causing more problems than they'll solve. But no, we haven't spent time specifically looking at how to avoid, hey, I want to screw up this guy's model and say everything's hemorrhage or whatever. Yeah.
Next question, thanks.
A single question here. Ross Vienna, Vaccine Safety Initiative. I just wanted to take the opportunity that so many of you have experience in pediatrics. And I find that particularly interesting, being a pediatrician myself. And then we had the previous session where we were talking a lot about patients taking ownership of data. I think you see where I'm going with this. So we had a lot of top-down solutions, but many of you gave some refreshing ideas about what patients, how they could benefit. But I'm really interested in how we could tackle this, get some more pediatric ownership of data or helping children grow into the world of medical AI, understanding what is being done with the data? You know, I don't know, are you evolving the child life service? Where are we headed with this? I think it's a fascinating question. I'm always stunned how kids understand much quicker if I'm trying to get an informed consent than the parents, and then they explain to their parents.
All right.
So where are we headed with this is my question.
Jeez.
I'll take a stab at, this is actually one of my areas of intense interest. So I think pediatrics is particularly challenging for multiple reasons, and Rebecca got to a little bit of the issues of the patient privacy in pediatrics. So you have to think both about those unique privacy issues of both the young children and the adolescents who do have access, depending on the state, to certain information that their parents don't have access to. And on top of that, there's questions about what should their parents be able to share when they do have access. So I think there is so much discussion that we need to have in pediatrics about giving patients and children and proxies control of their data. But I definitely agree that the world is changing, and I think it's going to become incumbent, it's going to become the role of pediatricians to train young, teens and adolescents and prepare them for taking care of their own health as young adults by training them on what data do you have access to, what are the tools that you should know how to use, how do you keep that safe, what is privacy, and how can we help you transition into young adulthood. This comes up often for complex pediatric patients, with complex health disease, but I think it could be even more fascinating for your healthy adolescent who is about to go off to college and about to be on their own for the first time, and how could we send them off with their own data, with their own set of tools to help them start an early, healthy adulthood. So I think there's a lot to be done here, but there are so many complexities that we really need to talk through as a nation.
Maybe next year, a whole session on that.
Exactly. Happy to do that one. Yes, definitely my interest. All right, we've got another question in the back.
So I have a question on intellectual property and how you can do some public good. All of you on the stage are doing public good in many ways, right? But it's in a silo. So how can data and algorithms be shared so that we can get most out of it, but how can also we can protect intellectual property?
I think one thing to maybe distinguish, right, is what space you're talking about, right? So often if you're an academic, right, you write a paper, it is increasingly common now in the machine learning community that you open source your code, right? At least the modeling portion of your code is open. And there is an increasing push in the machine learning for health community that data comes with the code, with vetted access when appropriate, right? So the MIMIC data set has vetted access. But if I write a paper on MIMIC on predicting septic shock in the MIMIC data set on those 40,000 patients, any other researcher in the world can apply for access, and within a week, they can download MIMIC to their GPUs, they can download my code, and they can run my model and verify that I did what I said I did, and then try to deploy it in their own data or in similar data, right? And the Checkspert labeler, I think, is a similar example of, there was a great paper, there was a data set released with that paper, right? And there was a labeler released with the paper as well. So you can do this now on your own data set as well, right? And so I think examples like that are hugely motivating. And I think a lot of us within the community are pushing for more examples of data that is open to vetted use, that's been de-identified appropriately. I think the question you ask about IP is harder when you have, we are in Silicon Valley, right? When you have, sort of companies and maybe other interests at play.
I guess from my perspective, we don't even, the space that we're playing in right now, I don't even know is really transferable to other organizations. The clinical variation just among our hospitals, even our no-show model, when we initially rolled it out, it didn't even work well at half of our facilities, and we had to make custom models to them. So the intellectual property from the actual model itself might not be super relevant, but maybe the process in which you create the model and can train it on local data, you might want to do something around that. But most everything we've done, we have no real interest in protecting, and we share it. And if I gave it to somebody, I would warn them, please don't implement this, do what we did on your own data, take what we, because I don't expect it to work at your facility. I just really don't.
I also want to add that, in some of my work working with, very sensitive data that's never going to go out, for us, we will share, as Marzia was saying, our algorithms are things that we want to put out there. We want other people to be able to benefit from these, in terms, and possibly, at some point, models that are trained and can be directly useful in some applications as well. In terms of the data, obviously this type of very sensitive data is not going to be shared, but I am very interested in finding ways to enable other researchers in this area to also work on these problems and contribute to making progress on this together without necessarily having to build their own implementations or go through the same infrastructure types of challenges we did. And so, I'm interested in trying to figure out ways, whether through taking what we do have from our data, being able to generate other types of synthetic data or other ways in which people can still train models and for these types of applications, but without having access to, for example, our data that we work with exactly. And so I think this is still a very open problem. It's a research area in itself, but it's something that I'm very interested in.
Yeah, we've pushed hard, as you may know, to release as much data as possible, as much labeled data as possible. It's been a learning process for us. I think that we've learned that to benefit the research community as a whole, and to sort of have the moral high ground, so to speak, in terms of the work that we're doing and the reproducibility and transparency. We release the data, we release the model, but it's so difficult to do that we are definitely exploring. We worked with the folks from Mimic as well, tried to get that co-release, get 500,000 X-rays out there. We think that the field's going to move forward because of that effort, hopefully. We learned a lot of lessons via the CS community with ImageNet, and we'd like to try to get there with medical, images or other data. But it's increasingly looking like, as those of you out there are building the tools to help large healthcare systems put things in the cloud and make things movable, that we can get to a distributed model where we have partnerships with, say, Duke or MIT or Brigham or wherever, and we can move the models around, training on those data and just moving the weights. And that sort of helps us avoid a lot of the pain and suffering that go into releasing data the way we have. But on the other hand, it still doesn't let the little guy succeed. And what we want to see is the people that are, they're learning on Andrew's course on YouTube, and they want to get a data set and they want to get into the field. It's hard to do if you're just locking it down and making it federated only. So I think that there's two approaches that we're really excited about. And you notice that I didn't say IP at all. And that's not something that at least we're focused on. I think that there will be, certain pieces of this that will ultimately be owned by Stanford in some way, and that discussion will move forward. But I think that we haven't made that a singular focus of, frankly, any of the work that we've done, which has, maybe been good, maybe not, I don't know. Maybe the jury's still out. But it's something that we believe strongly in, again, is sort of the open source approach.
I think it's also important to note that this is a choice that this community gets to make, and it will inform the future of this community, right? So all computer science departments hire vision people, right? Like I trained at MIT, I am at University of Toronto now. You have your general ML person, you have a vision person. It's a subspecialty that people hire for. It has its own academic conference, right? So Vision made a choice, right? Fei-Fei Li created this ImageNet data set, right? And many additional data sets have come out. And these data sets have sometimes a little bit more restriction to get access to them if it's slightly more sensitive. But fundamentally, Vision made a choice that they were going to make these large public access data sets. And that is what has allowed state-of-the-art research to happen in universities and public institutions in Vision. That's why we hire from Vision, right, in universities. Speech is owned by companies. Computer science departments don't hire speech people. Why? Because you cannot train students in a public setting to use state-of-the-art models in speech because those data sets are private. And so if you want to do state-of-the-art speech, you go to a company. And so as a community, we need to make a choice about whether we're going to be like speech. If you want to do state-of-the-art machine learning for health, you have to be at Google or Microsoft or Apple, or it's a choice, right? Or we're going to be like Vision and empower state-of-the-art research to happen in a research sector.
Thank you.
Can we applaud?
Great answer. So, so we'll do one last question, and it's just talking about. We've talked a lot about how the algorithms are tested and vetted, but I think we've had some interesting experience here in the clinical trial portion, the translation of that, and thinking about when do algorithms need to have that official clinical trial, and what are some of the unique considerations in making that happen?
All right, I'll start. We just did a trial. It was a learning experience for sure. I think that we picked a very, what we call low risk, low volume problem. We picked bone age to start, which is, I don't know if you guys know what bone age is, but it's something pediatric radiologists do. We don't particularly like it, but basically it's, you take an x-ray of a child's hand, if they're having sort of questions about whether they're having advanced puberty or not. And you could tell the age of a patient, the skeletal age of a patient, and you compare that to their chronological age, and you say, well, you're advanced, you're not. Okay, so not a very common problem, but still important, and something that a machine is really good at doing, as we've found with the challenges we've hosted in the public data sets we've released in the past. But that doesn't mean that implementation as parts of trials is rubber stamped. It's not straightforward. And I think we had 9 institutions as part of this trial. And every one of them had, different infrastructure. They had different reporting schemas, different things the clinician wanted to see and didn't want to see. And so whether that needed a full clinical trial or not is, still subject to debate. But I think we've learned a ton. And imagine trying to do something that's even higher acuity, something like brain hemorrhage, right? If my model is giving way too many false positives at one institution or another, when do you call it off? When do you make the decision as to whether this is just not suitable for use yet? And how do you go back and retrain it? So, but the trial is a trial. So, it's very regimented, very protocol driven. And that is something I personally believe in. I think that I'm concerned about the, relatively rapid implementation that's going on maybe in other settings. And as a clinician sort of in this community, I feel as if it's my job to make sure that things are vetted just like a new drug. In the same kind of very rigorous manner, and not letting this get out there and potentially hurt all of us if it's not vetted properly and doing what it said it needs to do. So, yeah.
Great, thank you, and we are out of time. So please join me in thanking all of the panelists. Great job, you guys. Really appreciate it. And we welcome our next panel on sleep. Thank you all.
Now? We start now? Okay. Okay, so hi everyone. I'm Professor Ada Poon, a faculty in electrical engineering. So today we are talking about a very important topic, which is sleep. So every day we spend a quarter to a third of our time sleeping. So sleep is quite essential to all of us. And today we are very fortunate to have a group of wonderful speakers who will share with us their work on this important topic, sleep. And our first speaker is Jonathan Barrett. He's a director at Google Earth. He involved in the founding or starting of a few startups, including one that specializing in the detection and induction of REM sleep. So welcome, Jonathan.
Thanks, Ada. Good to see you.
Good to see you.
Okay, so how many of you saw the series finale of Game of Thrones on Sunday? I can sort of see. Okay, hands down. How many of you thoroughly enjoyed it? Like this was the best series finale ever? A lot less hands. So I prepared this theme before I saw the finale. I'm not sure that I would have picked it if I had seen it first. But let's say these two things. One, if you haven't seen it, don't plan to see it, don't worry. You can still hopefully enjoy the talk, appreciate and understand it. And if you did spend about 80 hours of your life over the last 8 years, well then this can be a little bit of group therapy, okay? So I'm Jonathan Barrett. I'm a director at X, which is the moonshot factory of Alphabet, i.e. Google, and I focus on wearables. And today I'm going to distill down about 15 years of testing consumer wearables and share some findings and also talk about where I think the direction of the space is going. If you go to the next slide. I guess I can do that. Let's see if that works. Great. So given the short amount of time, I'm really just going to cover the two topics to make it a little bit enjoyable and hopefully memorable. I will connect it to the kings and queens of Westeros, which is Game of Thrones, and do that in the sense of the challenges. What are those that are challenged to really be a dominant player in the space of sleep wearables for consumers? And then we'll prognosticate a bit and say who might actually come up on top. So, without further ado, King Tommen. So King Tommen, all you need to know, he was young, and he was a little bit early to rise to the throne, and so was Zio. Anyone have a Zio from 2004? A few hands there. It was actually quite a cool device. And in fact, there's things about it that I miss today in today's wearables. Essentially, you put a band on your head for EEG, which is great that they were using that as a measure. Another thing that I really liked about it was it had a great form factor. You don't see it really right now in consumer wearables because everything's trying to be miniaturized, but you're used to having an alarm clock. And so you just had to take it out, put it there, and you would instantly get that gratification of seeing what was your hypnogram and a sleep score. So that was kind of nice. Now, I think they were before their time, a good 8 years before really the wearable revolution took off with the Fuel Band and Fitbit and things like that. And unfortunately, while they did a lot of things right, I think they anchored the market for over a decade on a fairly meaningless score, which is the sleep score. No thank you for that. Next up, King Joffrey. All you need to know about him, he was cruel to the bone, and unfortunately, the Basis watch. Lots of promise, actually fairly robust in clinical validation, 92 to 93% correlation with PSG, the gold standard in sleep. However, it started to burn people. So not good for a sleep watch, not good for any watch at all. And that was a real disappointment. I had probably half a dozen of these and was having various people track it. And so that was a disappointment. Now we come to King Robert. So Robert Baratheon, great soldier, excellent fighter in the field, didn't want to be king, wasn't really fit to be a king, and neither was Fitbit. So Fitbit, great for tracking, not so good for tracking steps, not that good for sleep. 2015, there was a lawsuit filed that it was over-tracking sleep by about 60 minutes. And this is a real challenge today. This is probably the primary challenge of the many devices that are out there. I did just an observational study myself last week to test some of the state of the art. And the best machine that actually a consumer can get their hands on that does sort of clinical grade EEG is the Z machine. And it comes at a cool $3,500. So it's not really a consumer device. It's really meant for something just leading up to a sleep study. But I use that to verify the Apple Watch Auto Sleep, which is a nice feature, or it's a nice app on the Apple Watch because it just automatically knows when you're sleeping and records it. And against the Aura Ring. So an interesting form factor is just a ring. And it's just like this and has PPG sensors to measure primarily the heart rate. So and you can see there over just 3 nights, again, very observational, not drawing conclusions, but there was a lot of variance in both the total sleep time and then especially the deep sleep and the REM sleep. Now, a couple nights did actually correlate fairly well with the Oura Ring, and I have a pretty tight fit. In fact, I can't really take the ring off that easily, so maybe that helped. I did look at the literature review, and some of the studies on the Oura Ring show that it actually didn't have that high of correlation with deep sleep and REM sleep, only like 50%. My hypothesis on that is, again, the challenge is the fit. If you have a nice snug fit, you're probably going to get a more accurate reading. So accuracy, a huge challenge for the market right now. King John, fan favorite and hopeful. Somebody in the green room said they hadn't seen the final, so there would be no spoilers here, but lots of people think he'd be a good king. And the trouble with John is he's not comfortable with being a king. And unfortunately, some of our best options really aren't that comfortable. But let me talk about some of the positive sides. So you've got the Rhythm Dream, and you have the Philips Smart Sleep, and then you have the Sleep Shepherd. The good news is they are using part of the gold standard, EEG. Now, you need to add a few other things like EMG, muscle tone, but they're doing those things right. It's just that when you try this, has anybody tried one of these? I would be surprised. I can't see the hands very well. Maybe a couple in front, yeah. It is a little bit tough to have something that bulky on your head. Now, Rhythm Dream is coming up with a new version. I expect that to be trimmed down a little bit, but that is the primary challenge. I've passed these out to numerous friends and family members who really have trouble with sleep, and this has the promise of helping with insomnia, staying asleep and falling asleep, and I think the main challenge is it feeling comfortable on the head. So, no lineup of would-be kings and queens of Westeros would be complete without Queen Daenerys. And however, the cost is very high, and she pays a high cost. Let's just say that, so we won't spoil anything. But I looked at the average price, and I didn't even, of course, include the Z machine at $3,500. But these are just some of the top trackers out there. And it's expensive. I think this is an expensive list, and especially if you look at the ones that are going to most likely provide the most value, you're in the $400 range. And so I think this is a huge challenge and a barrier. You also have high expectations when you pay for this much. So who's going to rule? Well, it's no surprise, I'm not going to crown any of those, but I will talk about 4 rules of law. Like, what do I think somebody that is going to do very well in the next 2 to 3 years, what will be true about them? Oh, this is, I think, an earlier version, but there's actually 4 rules. We'll see if there's a magical 5th. First, most important, remember, we sleep in order to be fully awake. We do this, we have these nights of sleep, and we want to feel rested and most present during the day. And I think that's where this idea of a sleep score at night is less relevant. What we really need is a daytime score. And if you think about how we are using our smartphones on average about 50, 60 times a day, some a lot more than that, and about 200 minutes, fortunately we have a lot of data to actually derive some interesting statistics from it. There are people at MIT that have done this for mood and arousal. I talked to Jamie Zeitzer from Stanford, and he did some work with Bing and Nike Fuel, and he saw a correlation between query response time on Bing and fatigue and sleepiness. So I think this is an interesting change that I think we will see. You're starting to see the beginnings of this with like the Oura Ring. It'll talk about a readiness score for that day. But I think that going a step further, we need is an actual daytime score based on your smartphone usage, and that will be key for the next set of sleep wearables. Comfortable form factor for clinically validated measurements. So we need sleep-friendly EEG. I think that is very important. Without the EEG, I don't think we're going to get the correlation we want. There's been lots of work, lots of algorithms, machine learning thrown at these data sets, but I do think unless you had a calibration phase, perhaps if you had a calibration phase, then some of these non-EEG metrics would work, but I think they'd have to be calibrated on an individual level. So I believe it's going to have to be sleep-friendly EEG for it to be effective. I didn't give the Rhythm Dream and the Philips Smart Sleep its due. It actually enhances sleep, not just tracks it. What do I mean by that? So there were some studies done, replicated in several different labs, where if you stimulate with pink noise at obviously a low enough volume during deep sleep, you can increase the amplitude of the slow wave. And they actually show some effectiveness of that, not just on the EEG measurement, but in memory tests the day after. And these are double-blind controlled studies. So it's very interesting to think about sleep enhancement as a place that I think people will be going towards. And here's perhaps the most controversial one that I'll throw out there today, is I think all this really should be free. This should be a basic right. If something is clinically validated, who would have an interest in making sure that you're sleeping well? Car insurance. We have great data on fatigue and sleepiness, sleep deprivation and accidents. And then there's all kinds of health-related concerns due to poor sleep. So I think that somebody, a company or startup that pursues that with that end in mind, hopefully can get the funding they need in order to do the hard work of the clinical study. So in summary, there is no king and queen of sleep wearables yet. I think machine learning will be applied to daytime and nighttime scores for there really to be a closed loop system. And then finally, sleep tech should be free for all. Thank you very much.
So thank you, Jonathan. Our next speaker is Julie Christensen. Julie is a clinical associate professor from Tellico University of Denmark. Her research focuses on analyzing sleep by developing algorithm and data-driven models to analyze sleep by introducing objective and quantitative measures. So welcome, Julia.
Thank you. Thank you for the introduction, and thank you for the invitation. I've been looking very much forward to give this talk about data-driven methods for sleep analysis. And I don't know how familiar you are with the way sleep is analyzed today in a clinic, so I start with this brief introduction. It is done manually, and it's based on the identification of certain characteristics that you can see in the polysomnographic signals. These signals are mainly the EEG, as we just heard, maybe also the most important one. The EOG, that measures the way we move our eyes during sleep, and the EMG that measures the muscle activity. And for each 30-second window, you divide sleep into wakefulness or sleep station on REM 1, 2, 3, or REM sleep. And this is done based on what you see in the signals. And you'll end up with a hypnogram, which is shown at the low right corner, which illustrates the sleep architecture through the entire night. You can see that you go down to non-REM sleep and then up to REM sleep, and then you have these characteristic cycles. As said, sleep is characterized discretely in 30-second time windows. That means that you basically cannot switch within a window of 30 seconds. It uses standards that are based on how normal and healthy sleep looks like. It treats the brain as a whole phenomenon, or a global phenomenon, not covering regional changes in the brain. And it's done manually, so therefore it is subjectively and therefore prone to inter-expert variability, in specific when we look into pathological sleep. So what am I doing? I'm trying to develop data-driven methods that can help advancing sleep analysis. Traditionally, this is done by developing automatic detectors for these characteristics that we are looking for. That could be to detect sleep spindles automatically, eye movements, slow waves, muscle activity or arousals, or develop a detector that can just do the sleep staging for us that is done manually now. Another approach for my research is not to develop these automatic detectors, but to try to challenge the gold standard. So this is done by, for instance, developing methods that can identify segment boundaries not limited by the 30-second rule. It could be to provide indiscrete labeling of sleep stages, so you actually allow several sleep stages to occur at the same time. It could be to provide certainty scores for sleep labeling, so without saying it's only in wakefulness or in non-REM1 sleep, you can say this is a certainty score of 80% or 60%. Or finally, to allow different sleep stages to occur simultaneously across different regional brain areas. I'm going through two examples of how we challenge this gold standard. This is one example. This is where we try to challenge the discrete staging of sleep. So the aim for this research topic is to analyze sleep automatically by using what is called a topic model approach. For those of you that don't know topic modeling, it's a statistical model that is normally done in text document, and it can see, based on the occurrence of words, which topics this document is about. And relating this to sleep analysis, you can say that a document is a sleep epoch of 30 seconds. You can say that a topic is the different sleep stages or vigilance stages. And you can say that the words are structures in the EG or EOG that is indicative for these sleep stages. So what we need to do here is to transform the raw data into words that can be put into a sleep or topic modeling approach. And this is done in this way. We have the raw EEG data up in the left corner. We do some bandpass filtering into the standard clinical frequency bands. We do a power calculation for each 1 second of data. We categorize these into 5 categories, going from very low power to extreme power. Now we categorize them into letters. Then we define words for 3-letter words. So the first word here is VLL, the next one is LLL, and so forth. And then for each 30 seconds epoch, we now count which words were in that epoch. So now we have a word distribution for each 30-second period, or each 30-second window. On the right-hand side, we compare this word distribution of one epoch to the topic modeling. A topic model has learned the typical word distributions of 6 different topics illustrated in colors. So in this given example, this epoch is most likely to belong to topic 2, the blue one, because it has a probability of around 49%. We do this for all the epochs throughout the night, and what we end up having is a topic diagram in the bottom right corner that illustrates the entire sleep structure throughout the night. Comparing this way of analyzing sleep to the traditional way, we can see that the overall sleep architecture is captured using this method. We can also see that there's a huge overlap between, for instance, the orange topic and REM sleep, the dark blue topic and non-REM 3 sleep, and so forth. But what we also can see is that this method actually comes up with much more details than the traditional way of analyzing sleep. This was one example. Another example is that we want to challenge the gold standard looking into this constant epoch length of 30 seconds. So in this research area, we try to use adaptive epoch length. We do that by using adaptive segmentation, which basically compares 2 windows, a reference window and a test window. If these are alike, the test window is put into the reference window and a new test window comes up. This is also alike in this example, so the reference window will grow once more. When the 2 windows differ, a boundary is set and the procedure is started all over. This means that we actually set boundary when abrupt changes are seen in the signal. Comparing this to the manual scored hypnograms using different start window length of 3 seconds, 10 seconds, and 30 seconds, we can see that the overall architecture is still captured. But we could also see that when we allow more changes to occur, more changes will also occur, but it's not equally distributed throughout the different sleep stages. We can actually see that it is in specific in REM sleep that we see much more changes when we allow changes to occur. So why should we do this? Why should we go away from the gold standard? This is an example of us that have applied the topic model on data from patients with Parkinson's disease patients, and also patients suffering from a sleep disorder, where you have found out that these patients are at high risk of developing Parkinson's disease. And what we can see here is that there's some stability measure that we defined based on the automatic labeled epoch using the topic model and based on the manual labeled epoch. And you can see that there is a clear tendency when we use the automatic labeled epochs, which were not captured using the manual labeled epochs. This could be a potential biomarker for Parkinson's disease. We also applied the topic model on insomnia patients. And we found that insomnia patients have much more of the T4 topic, which was related to light sleep. We also found that they had, in their deep sleep, they had much more light sleep related features, which makes sense for this disease. And we actually found that this feature was correlated with the insomnia subjective complaints. And finally, we found that the transition patterns between these epochs were significantly different between control subjects and patients with insomnia disorder, or insomniacs, they also call that. Last slide here. When we go away from the gold standard, a lot of challenges arise. First of all, it's very hard to validate these kind of models, because when we allow short segmentations, and the manual gold standard only uses 30-second epochs, it's hard to validate whether we actually found abrupt changes that should be there, or it's changes that are just based on noise. Also, when we allow shorter segments, is there then only 5 sleep stages, or should we allow much more, and how to validate that? And lastly, when we allow that sleep stages can occur simultaneously, and we have no idea what the manual scorings will say, or the manual scoring only have discrete labeling, how should we validate that one? And then lastly, if we go away from this manual way of scoring sleep, we have to translate all our experience done using this approach. So for instance, we have to translate diagnostic criteria, such as a SORAM for narcolepsy or REM sleep without atonia for IRBD, that are experience made based on the manual scored hypnograms or the manual scored analysis of sleep. How should we have to translate these if we change the way we analyze sleep today? These were my 10 minutes. Thank you for listening.
Thank you, Julie. So our next speaker is Jennifer Kennedy. She is a clinical innovation lead in big health. Her work focuses on the development, implementation, and evaluation of sleep interventions, particularly event-based sleep interventions, with a focus on behavioral therapy for insomnia. So welcome, Jennifer.
Hi, thank you for having me. Mental health conditions are incredibly prevalent, and approximately 1 in 5 Americans will be diagnosed with a mental health condition in a 1-year period. Some of the most common mental health conditions include mood disorders, which have a 12-month prevalence estimate of around 10%, anxiety disorders with a 12-month prevalence estimate of around 18%, and insomnia with prevalence rates as high as 22%. The consequences of having mental health conditions can be incredibly dire and can significantly impact a person's quality of life and functioning. Therefore, it really is of utmost importance that mental health conditions are properly treated. To date, the mental health care landscape has been largely dominated by pharmaceuticals. And really the reason for this is the fundamental qualities of pharmaceuticals themselves. Drugs are really appealing because drugs are scalable, affordable, consistent and standardized, and have a strong evidence base, with one important disclaimer: side effects. In the last several decades, there really has been no other healthcare option that has exhibited these same appealing qualities. That is, until digital medicine. The goal of digital medicine is to transform evidence-based behavioral treatments, things like cognitive behavioral therapy, into digital platforms that can reach and benefit millions of individuals. Research shows that behavioral treatments are just as effective as pharmaceuticals at treating the symptoms associated with mental illness. However, some of the problems with these behavioral interventions is that, first of all, they're not always easily accessible. Not everybody has access to providers that are skilled in this kind of care. And second of all, they're not always affordable, as health insurance doesn't always cover this type of treatment. And so that's really where digital medicine comes in. And digital medicine is the first true alternative to pharmaceuticals, because just like pharmaceuticals, digital medicine is scalable, it's affordable, it's consistent, and it has a strong evidence base, with the added bonus of not coming with any of those pesky side effects. Our mission at Big Health, the mission that really drives all of our work, is bringing millions of individuals back to good mental health through digital medicine. Partnered in this mission are the different systems and companies that you're seeing on this page. So we distribute our programs throughout the United States and the United Kingdom. In the United Kingdom, we distribute through the National Health Service and have covered 10 million lives. In the United States, since we don't have national health care here, we found that the best way to reach a large amount of individuals is to actually go through large self-insured companies who are motivated to cover their employees. And through this process, we have covered 2 million lives. Our first product at Big Health was a product called Sleepio, which is a fully automated yet highly personalized program for insomnia that is accessible via application in the web. The structure of Sleepio looks very similar to the structure of traditional in-person CBTI, in that it is personalized using sleep diary and self-report measures, and the user has weekly sessions with their sleep coach, a gentleman named the Prof, who is very entertaining, very knowledgeable, and during these sessions, the Prof will actually teach the Sleepio users evidence-based tools that the user is then expected to implement in between treatment sessions. Some additional benefits of Sleepio is that the user then has access to these tools via the user dashboard. Via the dashboard, the user also has access to a library of information about sleep and can also access the Prof in between sessions. The user also has the opportunity to, problem solve, talk about barriers, questions, comments, and concerns with other members of the Sleepio community. And they also have access to sleep experts via the live chat feature. So without further ado, I would like to introduce you to the Prof.
Hello there, Jen. I am the Prof, and I'm here to do everything I can to help you sleep better. Now you may be thinking, why should I trust you to tell me what to do? Well, everything we do here at Sleepio is rooted firmly in scientific evidence.
Thanks, Prof. You're absolutely right. Everything we do in Sleepio is firmly rooted in scientific evidence. That's very important to us because the fact of the matter is, despite how entertaining Sleepio is, and it very much is designed to be an entertaining program, and despite how charming the Prof is, he actually has a narcoleptic dog, Pavlov, who helps him. Very cute. But despite all this, if Sleepio doesn't work, then it's useless. And so let's talk a little bit about the evidence. The benefits of Sleepio have been established with 8 published randomized controlled trials and in over 12,000 participants across all of our various studies. And as an interesting side note, this is actually 4 times as many participants that have been used to study the efficacy of Ambien. The benefits and evidence base of Sleepio is so compelling that the American College of Physicians actually recommends Sleepio as the first line of treatment for insomnia. In our very first RCT, we found that following Sleepio use, 76% of Sleepio users achieved healthy sleep. And this improvement rate is actually comparable to what we see in in-person CBTI sessions. And importantly, this improvement rate was also significantly greater than treatment as usual and was greater than a digital-based placebo-controlled condition. In another RCT, I believe the RCT, or the largest RCT to ever examine a psychological intervention, results from this RCT demonstrated that compared to treatment as usual, Sleepio resulted in significantly greater improvements in sleep. And this was a sample of college students in the UK. And these treatment improvements were maintained at a 3-month follow-up assessment. In the same study, researchers found that not only did Sleepio improve sleep, but Sleepio was also associated with significantly greater reductions in paranoia, hallucinations, depression, and anxiety symptoms. Another RCT I want to highlight is an RCT that was done in collaboration with the Henry Ford Center in Michigan. And this was an RCT that aimed to examine the efficacy of Sleepio across a wide range of demographic groups. What this RCT demonstrated was that compared to an online sleep education course, Sleepio resulted in significantly greater reductions in insomnia symptoms, and also resulted in significantly greater reduction in depressive symptoms. And interestingly, the effect size for the reduction in depressive symptoms is actually a little bit larger than the effect size that we see for some common antidepressants. And then the final RCT that I want to briefly highlight, this was one conducted by Colin Espy, who's one of the co-founders of Sleepio. And what they wanted to look at is whether or not Sleepio was also efficacious for improving daytime dysfunction that you commonly see in insomnia. And so again, compared to an online sleep education course, results demonstrated that Sleepio improved overall health, psychological well-being, and quality of life related to sleep disturbance. So taken together, these really compelling results demonstrate that not only is Sleepio effective for improving insomnia, but Sleepio is also effective for improving daytime impairment, typically associated with insomnia, and might be a really nice avenue for improving quality of life and functioning across a wide range of individuals. At Big Health, continuing to conduct research is really important to us. And so what you're seeing on this page are our research objectives. First of all, we're very excited to continue to pursue our own line of clinical research in order to answer questions that will advance the field. And then we're also very passionate about collaborating with external investigators. And really, a lot of the most significant and high impact results have come from these external collaborations. What you're seeing on this page is a demonstration of how excited we are about research. This is just a sub-selection of the ongoing research projects that we have going on at Big Health. To give you a little bit of flavor about what some of these projects are, for example, we're currently looking at whether or not Sleepio improves cognitive functioning. We're also interested in examining the efficacy of Sleepio across various medical and mental health conditions. For example, PTSD, postpartum depression, HIV, and sleep apnea. Because our insomnia program was so popular and so effective, we're really excited to branch out into other domains. And so we have our anxiety program launching later this year, and then we have a depression program launching in 2020. Thank you very much for your time.
Thanks, Jennifer. Our last but not the least speaker is Emmanuel Mayunt. Emmanuel is a professor in psychiatry and behavioral sciences. He's also the director of the Stanford Center for Sleep Sciences and Medicine. So, welcome, Emmanuel.
Hi. So what I'm going to try to do is to try to put a little bit of this different story together and also show you example of, I think, the direction that the sleep field is going to. It's a very large field, and I think the talks that we have heard, exemplify that. We can try to treat sleep disorders at home. We can do more data analysis, machine learning on data. We can, of course, have more and more device. And I think the first question that you may ask is why we should study sleep. And I think that's going to remind you a couple of things. I'm also a scientist. So for me, one of the things that is very interesting is that we still don't really understand why, when we don't sleep, we are more and more tired. As you probably know, people have had the Nobel Prize recently about the circadian regulation of sleep, which is just the timing of sleep and hormonal release in relation to the sleep-like cycle. And that is very well studied, and we understand the genes that are involved, and we know why we feel more tired at certain times of the day and why we experience jet lag. But curiously, we really don't know anything about why, if you don't sleep 1 night, 2 nights, 3 nights, and you become sleep deprived, you become really more and more tired, and it's such a biological need. So for me, that's one of the things that I'm definitely very interested. So the second reason why sleep is so important is because as you have heard, sleep problems are very common. We heard about insomnia, for example, just a talk before, and this connection with depression. It's one of the best predictors of the development of depression. But the problem is insomnia doesn't occur always alone. There are other sleep disorders that are very frequent. For example, sleep apnea, which is a disorder where people snore. And usually they are maybe the coach of sleepio has sleep apnea. So it's typically a slightly overweight man. Even so, it's not always not always that. But people snore and then they stop breathing, and then the oxygen drops, and then they wake up. And of course, if it happens a lot, your sleep is very fragmented, and you are very tired during the day. And the second consequence is that you have a cardiovascular problem that develops, especially if you have recurrent drops in oxygen. In fact, it has been shown that sleep apnea is one of the major risks of high blood pressure and increase the risk of stroke many-fold. And there are many, many longitudinal studies that have shown that. So it's a very serious disorder that we need to treat. Then there is restless leg syndrome, and people who have this strange feeling in their legs that bothers them, and they have to move their legs during the night, in the evening, and they can't fall asleep, and then they kick during sleep, which can produce a lot of problem. And then finally, there is a whole group of people who, instead of not sleeping well at night, they can't stay awake during the day. So I don't know if we have any of here that are a little tired and are just starting to fall asleep. I wouldn't be surprised. And that's, in fact, right now, the whole field of drugs is moving away from insomnia. We used to treat insomnia with drugs, put people to sleep. And now, as you have heard, more and more it's cognitive behavioral therapy. We try to change behavior of people to improve their sleep. And a lot of the market is shifting towards stimulants and drugs. Like you all know that a lot of these drugs are used for ADHD, but for sleepiness as well, for people who are tired during the day and have this kind of problem. So there is a very big, large economic impact. I didn't talk about the fact that, of course, there is accidents. And I mean, what's very nice about working about sleep is that you can interact with anyone and you can always find an overlap. And it's a great talk in cocktail parties. But one of the things that's really exciting about sleep is that it's really at the center of many revolutions. Of course, there's a revolution I won't talk about animal models, etc., that's occurring that allow to understand better the circuitry in the brain. But also, there is a revolution we heard in hardware, with smaller and smaller devices. And you have heard that all these devices that Jonathan reviewed, they are not perfect, but we're getting there. And I will talk a little bit about that, but I think there's two big general ideas in the future that sleep is going to. One of them is the contact of non-contact sensors. The idea is that your bed is your monitoring unit. You're just sleeping in your bed. It measures your movement, your snoring, everything, and it knows what you are doing, and it doesn't touch you. Or contact sensors, which Jonathan reviewed a little bit more, where really you have things that touch your body and may measure your brainwave, how you snore, etc. And I think there's a big battle right now between contact sensors and non-contact sensors, smart bed versus, kind of a wearable. But definitely this is being more and more easy to do thanks to people like Ada and Zin and Bao that are inventing really new material. Then finally there is a revolution in machine learning that's allowing really the automatic analysis of this kind of data in a very efficient fashion. And finally, which allows a link with really what I am personally interested, which is the basic biology of what's happening in the brain, there is also a genetic and a proteomic revolution. and I'm going to talk about this. One of the problems we have really is this. Currently, this is what we use at a sleep clinic. If you go to a sleep clinic, what literally we will be recording all these different things. There will be sensors on the top of the head. I don't know if it really works, but it doesn't matter. That measures the EEG, the brain waves, because that's very important, as we heard, to see if you are, what kind of deep sleep you are in, if you are dreaming, which is very important. It's also measuring breathing because of sleep apnea. But of course, breathing is not sufficient. You also want to know if people stop breathing because it's obstructed, and they continue to fight it, that's called an obstructive sleep apnea, or if they just stop breathing because they decide to stop breathing, which is called a central sleep apnea, which occurs in heart disease, heart failure, or when you take certain drugs. And then, so you have also these belts that measure the effort to see if you continue to try to breathe when it's blocked up there. And then you have some leg electrodes to measure your leg movements. And then, of course, you have the EOG, to measure eye movements for REM sleep. So, I mean, how can you sleep with this? I mean, that's a problem, In fact, they always put beautiful people, super good looking, that are like perfectly sleeping peacefully, but practically that's not what we observe. You can only sleep on your back, which makes your sleep apnea much worse because your tongue, pushes on the back of your airway. So actually, it's not really necessarily exactly how you sleep when you're in a natural environment. And also, it's very clumsy. You can barely move. So really, the goal, and I won't have time to detail in great detail, but is go away from this very large, what we call PSG, where we have all these incredible signals of, the EEG, the brain waves, the breathing, the leg movements, the snoring. We even have a microphone, even the heart rate, and then interpreting this into sleep stages, sleep apnea, leg movements, which are really basic, very basic measures. Actually, at the end, when people, they are technician and they score this sleep study, it typically takes, they just only at the end give you a number, like what's called your sleep efficiency, what % time you spend in different sleep stages, how many times you stop breathing, that's called the HI, which is for sleep apnea, and how many times you kick your legs for periodic leg movement and RLS. So really, we take this beautiful data, very rich, and we summarize it to something really, really simple. And I think in the future, as I will argue, because the progress in miniaturization, etc., I think it's very likely, and people like Adapun and Zinan Bao are really doing this kind of work, will be able to have much better sensors that will take very little batteries, that will be remotely moving the data, and you will be able to sleep with measuring your brain waves, as well as maybe potentially other sensors. And one of the big battles actually right now is which sensors are needed. I mean, and I have a little bit of a bias. I think sound is probably one of the best sensors because snoring is actually very rich. It's almost like a melody. It's a matter of perspective, of course, but but really it's a very rich sound. And actually, if you hear breathing, stop breathing, you can know if it's obstructive or central. So I think a simple microphone, for example, can probably replace all the cannula where we measure all the the respiratory effort and the sleep apnea. Probably the EEG is needed because all the devices you heard about activity, it's a little bit of a problem. If you don't move and you're awake, you look like you're asleep. So I think activity is never going to completely replace what you really need, which is a brainwave. And right now, there is no non-contact sensors that can measure brainwave, unfortunately. That's why I think EEG is still needed. And you have heard that a lot of people are working on very simple EEG or things you can wear at home, and then all this will be transmitted and automatically. So that's an example, for example, of work we do with analyzing normal breathing and snoring. And it's really perfect. I had to put a little bit of that kind of noise. But what I want to point out is that all this kind of data is also miniaturization, et cetera, is going to be also ideal for machine learning. As you see here, for example, we did a little exactly like what Julie mentioned, except we didn't use topic modeling, we use another model to do machine learning, and really you can score sleep as well as human. In fact, the way we do it is we have all these technicians, actually we have 30 technicians at the sleep clinic currently that are working there. Most of their work is really to go through this screens of sleep studies and score every event, if people have sleep apnea, if people are in deep sleep, etc. And with machine learning, supervised machine learning, very simple model, I mean, many different types. At the end, you can really do as well as human. And in fact, you can show that you do even better than humans because it's closer to the consensus of the six scorers than, for example, any single scorer. And even more interesting, it gives you new information. Even if so, it's just supervised learning, which is very simple. You're not trying to invent anything. You're just trying to actually mimic what a human does when he's scoring sleep. But you also get some kind of confidence in your probability. So it doesn't tell you, yes, it's stage 2, it's REM sleep. It gives you a probability of each stage. And just to show you how it can be useful, for example, I study a rare disorder that's called narcolepsy. That's one of my favorite topics. And we realized that when we apply this machine learning model to people who have narcolepsy, there were cases where in the middle you see there is this part of the sleep recording where it's white, red, and black, and blue, all at the same time. So the computer cannot really tell you in what sleep stage you are. And in fact, that's exactly what a narcoleptic experience. A narcoleptic patient often in this strange period where he's half awake and half dreaming, and really actually even the automatic, the machine learning can actually detect that. And by using this kind of features, we actually fed them in another model, which is more like a lasso, a very simple statistic. And we can now actually diagnose narcolepsy just based on a night of sleep. Whereas before, you needed to have naps during the day and record if they were falling asleep into REM sleep. So for example, that's an example how machine learning not only does better than human, but also you can apply what you find to diagnose better specific sleep disorders. Another big area that I think is important that nobody has talked is the genetics and proteomics. I mean, the advantage of genetics is that it's to open a black box. And for sleep, as I told you, it's one of the last black boxes in biology. I mean, you really don't know the cause of why you feel more and more tired. And one of the exciting, and to show you that it works, for example, narcolepsy, which is this weird disorder where people dream a lot and they are paralyzed and they are very tired all the time and they go in dreaming very quickly. Nobody knew the cause of it, but if you do a genetic analysis, all the genes that are associated are actually related to the immune system. And now we know it's an autoimmune disease where actually the immune system attacks a specific set of cells that produce a chemical, which is called orexin or hypocretin, and when these cells are destroyed, you have narcolepsy for life. But by doing genetic, it immediately shows you that indeed it's autoimmune because all the genes are involved are autoimmune. So that's the power of genetics. It gives you maybe a clue to the function or to the, what's the cause of things. And for that reason, we are starting this big study. Actually, it's already started, which I think is one of the most exciting studies in the field, where we're going to, and we're doing that quickly because I think I told you this old PSG, I think it's going to disappear. I mean, there's no reason to do it, honestly. A little bit of work, we could probably replace that with sound and electrode on the EEG and then some accelerometer in the legs. However, I mean, it's such a rich data set, we want to use it before it disappears. And what we have done is we have teamed up with many, many sleep labs, and we have this big study where we're going to record sleep in 30,000 subjects. But since we know that sleep in a lab is very good qualitatively, you get apneas, you get everything, but you really don't know the sleep habits. We also have an actigraph for 2 weeks, so we know the kind of habits of people, the activity patterns every day and circadian. We have a very long sleep questionnaire about if people sleepwalk, is there a medical history. We also have an anatomy scan, because that's very useful, because for some people who have sleep apnea, it's not just obesity, it's also how your jaw is formed. If you have a very small jaw, you have an increased predisposition to sleep apnea. And then we even have, as was mentioned, sleep is important for the daytime. So we actually also have a cognitive battery to see how fast people react and how good people are. And all this data will be also associated with genetic as well as a blood sample. And we think that this will be completely available to everyone. So that's one, I think someone mentioned also in this particular venue that it was really important to put data set for the public. And we really need data sets that are like standard data sets that everyone can compare to. And because otherwise, you don't know, people are studying an algorithm on one data set and another, and you can never compare, and everybody says they are the best. and obviously there's only one. And that's a big problem. We really need common data set. And the last piece I wanted to mention is, besides the genetics, one of the most exciting fields that's coming about is proteomics. I like to say that proteomics is a little bit like cold fusion, You know, we have always said it's going to work, but it never worked. But now, actually, there's new techniques, in particular aptamer technology, that allows to measure up to 5,000 proteins in 100 microliter. And when you do that, you have a totally different view of biology. Because instead of, for example, measuring glomerular filtration, you know, for kidney disease with just creatinine, or you know, now you can study, you know, 200 different proteins that all correlate with it, and you can do a multivariate model that's actually much less contaminated by the cofactors that modulate each of the protein. And as an example, for sleep, it's really incredible because we can, for example, find proteins that are known to peak in the blood at a very specific circadian time. And by measuring up to 300 proteins now, I can exactly predict if someone comes back from Tokyo, for example, or if someone is actually living in Tokyo time, which we have people who are shift worker, or even we sometimes have people we don't know why. They are just tired all day. They can't sleep at night. Maybe it's their circadian clocks that's abnormal. We also have a series of proteins that react to sleep deprivation. So we think we're going to be able to predict with a multivariate model if people are sleep deprived. So it's a very exciting field. And right now, I think with this study and everything that's going on, I think we're really at the right area because we think we will be able to understand the neuroscience of sleep at the molecular level and the molecular component of sleep with this proteomics, and especially if you link them to the genetic, because it's always causal. That will introduce some blood biomarkers. And then at-home monitoring. And finally, as I mentioned, I think as we heard for Sleep.io, eventually I think we'll be able to act at home. You know, you measure sleep, and at the same time you stimulate to increase sleep. You may deprive of REM sleep to treat depression. I mean, there's a lot of ways that manipulating sleep and treating patients at home remotely will really change, you know, the healthcare in that sector. So I just want to thank you for your attention.
We welcome all the speakers back to the stage to join us for a Q&A discussions. So any questions from the audience? Maybe you can get some sleep consultation from our experts.
I've got one.
Yeah.
What does sleep do? And that's to you, Dr. Mignon. What does it accomplish?
So that's a $1 million question. Is really, we don't really know. I believe that sleep is a very complex combination of restorative process. That during the day, you push your metabolism at a higher level, and then it has to return to homeostasis. And it was more convenient for evolution to kind of bundle everything during the night. But that is actually an explanation that works only for non-REM sleep, because we know you decrease your metabolism. It has a lot of advantage for natural selection. But exactly what's happening in the body, in the brain and the body, we really don't know.
How about encoding memories?
Sorry?
Its relationship to memory.
Yes. So, you know, there are so many theories. Yes, sleep certainly helps consolidating memory. We know that REM sleep probably increases creativity and also consolidates certain memory. I mean, we know that sleep has many functions and many positive effects. It's very important to have a healthy sleep. But which one is really has been the driver of natural selection, we really don't know. And exactly, personally, I think that every cell in the body sleeps in some ways, has to recover. And actually, you just look at yourself in a mirror when you have not slept. I mean, you just don't look, you look bad. Even your skin looks bad. So I think sleep is not just in the brain. It's a restorative process. We don't know if that restorative process is going to be like the circadian rhythm. What's remarkable is all the same gene and proteins have been found to work on every cell of the body. For sleep, we're not sure. I'm sure there is a restorative process in every cell of the body. And in fact, there is changes of genes, of many genes with sleep, you know, in every cell of the body, including the liver. But we don't know if it's going to end up being as simple as circadian rhythm, where it's really a small set of genes that coordinates everything. That's a million-dollar question, and that I hope to find with my study.
So I have a very weird question. So on one hand, most people are of the opinion that you should not keep your mobile next to you when you're sleeping. It would disturb your sleep and stuff like that. And on the other hand, we have these wearables that we are trying to implant or use and just to measure sleep. So does this wearable, does it affect our sleep in some way, or does it emit some radiations that might be harmful? Or like from the user perspective, I feel I'm scared to use something like this on my body while I'm sleeping or something like that.
I think maybe, Jonathan, you want to answer? Or?
Yeah, so
it's a trade-off.
The trade-off, the question is, yes, the mobile device might be able to help you with some of these sleep tracking if you put it near the bed, but then also is it a distraction? I think you're wise to see that. A lot of the devices, like the Rhythm Dream and some of those, they disconnect the Bluetooth, so they know that that's a consumer, thought. Not clear that there's any evidence that shows that it actually leads to anything, but most of the good ones turn off Bluetooth, so you can feel fairly confident when you're wearing something that it's isolated. So I think that's one thing. I do think, though, that the phone itself, if you're the type of person that is just immediately checking it, then you're probably going to have less value in that. If you remember the Zeo, that's part of what I liked about it. There was just no phone involved. I mean, it was 2004, and I think that that's where things should go again. I also like, there's a few, like the Sleep Shepherd is a device that you might look at where it's just an on-off switch. It's kind of low-tech in some ways, but somehow I do think we need a little bit more low-tech so that people that do have sort of a no device in the bedroom policy, they could still take a sleep wearable and it could add value.
To also answer you, I think you remember I mentioned these two directions. There's one direction where people think of contactless sensors, where it's actually going to be your bed, your environment, that's going to monitor you without you doing anything, which is an extension of the concept we heard in the hospital. Is really, maybe with a camera, with the sound, without touching you, the firmness of the mattress, you can actually measure breathing, and you might be able to already detect a lot of things like sleep apnea, and then you might even be able to act on it. Let's say that people have sleep apnea more on their back. Maybe you can have a sound to train people to sleep more on their side. I mean, there's a lot of different options, both with a contact sensor and without a contact sensor. It's very clear that now a lot of companies are very interested in sleep because that's one of the largest. But I want to point out that it's not just poor sleep. There's also sleep apnea, which is a big problem. I mean, for example, if you have insomnia and you don't check for sleep apnea, that's a bit of a problem.
Thank you. Thank you. So this.
Yes, my question is more around the device and also the behavioral health side of it. If we look at something like studying resiliency and sleep disorders, what sort of devices, or where would you point us to say this is probably as good as it gets, knowing that polysomnography is near impossible to put in a person's home? If we're looking at resiliency, what would you recommend?
Maybe the CBT, sleep.
Sure. So I'm not entirely sure I completely understand the question. So are you asking what kind of devices might be able to predict resiliency to a sleep disorder?
If we're looking at the correlation between sleep and resilience, so what sort of devices would you recommend, as knowing that polysomnography is probably impossible to put in people's homes? And also, do you know of studies of resilience in sleep?
I mean, it's a fantastic question, and it's one that I'm actually struggling to answer. I apologize for that.
I'll add my perspective. Since I passed the baton to you, I didn't want the question either. So I think the challenge is in part of your question, you're talking about PSG. So you're kind of putting out there that we need some good biomarkers for resilience. And so I would agree. I think that's a challenge. I do think you'll see novel sensors. You saw a slide with Ada Poon and Jean Bao. I've had some interactions with them. I think they're doing some fantastic work, and so I think you'll see things. Maybe it'll just be like a little Band-Aid that you'll just be able to put over your head, and that will give you really accurate readings. And sleep does need to be personalized. How much deep sleep do most people get? How much do they need? How much REM sleep do they get? How much do they need? We don't really have good indications of that, because when you go into a sleep lab, the experiment affects it itself. So that's where if we got some of these consumer devices that had some clinical validation that were mass adopted, we might learn a lot more and we might get some of those biomarkers for resilience. The reason why I did point there is Sleepio and CBT, so cognitive behavior therapy. Like it's clear that if somebody came to me and said, what device? I would say I wouldn't go device, I would go CBT. Because that's going to help you. I remember Rafael Pelayo, when I talked to him about some of the things I was doing, I'm a self-hacker, I experiment with sleep schedules, crazy stuff, and he just looked at me and he said, people have the same sleep schedule as you, but they call it insomnia. You call it, this is amazing. And so it's mindset. And so he said, if I could change one thing for people with insomnia, I might have them change their mindset. And so that's where I think that's really not related to a device. That's just related to
Yeah, and I really actually like that point because I think I'm a little bit more traditional when it comes to cognitive behavioral therapy for insomnia, and I'm a very big advocate of sleep diaries, which is not a device and is really getting at the subjective sleep experience. And just speaking anecdotally, when I work with patients who do have devices, whether it be a Fitbit or whatever it is that they're using, they tend to hyper-focus on the sleep parameters, and it can make treatment even a little bit harder because of that. And so in those cases, I do like to encourage these individuals to, rather than focusing on, the objective readings of their sleep, to really focus on their subjective sleep experience and how they're feeling during the day, which I think is, just as well, is also very important.
Yeah, and I would add that, sleep is not just one disorder, so that's a problem. Is resiliency is a bit difficult to define, because is it resiliency to sleep apnea? Is it resiliency to, insomnia? I mean, we know, for example, for sure, and that I think was very well illustrated, that for insomnia contributes to depression, and there is now very nice genetic models that can address causality, and we know that insomnia cause depression, and that depression causes insomnia, and it's kind of a no-brainer. I mean, if you are depressed and you start not to sleep, it becomes worse, and vice versa. If you don't sleep, you start to worry about things, etc. So in that respect, certainly for insomnia, you don't need an EEG or device to measure it. Most of it is really like behavioral, and it has been shown to have very positive effect on mental health in general. But now you should not forget that there's not only insomnia. People may have insomnia and sleep apnea. It's super common. It's 20% of the population. So people may snore and they may try to sleep as much as they can, but their sleep is never restorative. And then, they end up with a stroke. That's a completely different problem. It's a different type of resiliency. And then you need maybe a device is helpful for screening, at least knowing if you have the problem. So I think it's going to be a little bit of a more complex solution,
Okay, so we could accept one last question.
Yes. Thank you. So we've been talking about how we quantify sleep quality and sleep disorders using data during the night. But since sleep affects also our daytime life, I was wondering what's the potential of using daytime data for recognizing sleep disorders or sleep deprivation or even just sleep quality? Can we use any of the wearables that you have presented or even just normal EEG data?
Absolutely, great question. So what can we use during the day? And I think that's something I'm advocating quite a bit. So I would recommend you go to MIT Media Lab. They have some stuff that's published there with smartphone usage. You can think about reaction times. You can think about spelling mistakes. You can think about emoticon usage. You can think about communication protocols. There's lots of things that it's a nice window into it. So there's nothing that I'm aware of on the market today that allows you to do something that is doing it, but I do think you will see that. It's a natural extension to go, because as one of my core theses, we sleep in order to be awake, and by awake we mean high quality, present-minded, attention. And so there's lots of ways to measure attention. If you really go far out and you want me to speculate, I do think that you'll see wearables that are going to be decoding more than just things on your phone. I think Emmanuel is doing a good job of reminding us about non-contact sensors. There's just we're living in a world that's just got ambient computing. It's coming, and ubiquitous computing is another growing trend. And so with that, you might imagine sort of a constellation of devices and constellations of data streams that could get processed that give you even more information about how you are behaving during the day. That again comes back to the night. And so I think when somebody can connect those two things, that's when we'll be in a good space, because consumer behavior is very hard to change. But if you can close that loop and do these slight tweaks, maybe even your Nest thermostat changes its temperature, that enhances your deep sleep, those will be the type of things when I think we'll be in a much better place for sleep.
And sometimes I think that it's during our wake, so we should trust our own feeling about how well we feel, instead of trusting a lot of these sensors, in my opinion.
Yes. Actually, as a sleep doctor, I mean, how do we define sleep, healthy sleep, which is really when people sleep enough to be rested during the day. That's very much what we consider healthy sleep. And a lot of insomnia is a behavioral problem where people actually are almost over-worried about not sleeping enough. And one of the key of cognitive behavioral therapy is actually to reduce a little bit sleep so that it becomes more dense and people kind of relearn to sleep. So in fact, what you hear in the media is very detrimental, because we hear a lot about these books that say, if you don't sleep, you're going to die and you develop Alzheimer's disease. And obviously, it's a bit of an exaggerated claim, and that scares people. So they say, my God, doctor, I only sleep 9 hours. Am I going to die tomorrow? But we see these patients, but they're great because they're very easy to treat. You tell them just sleep 7 hours and leave me alone, But,
and
That's what
also we are in Silicon Valley, right? We like all these gadgets.
So I think the over-focus, we have to be cautious. But on the other side, it's an incredible opportunity to monitor normal health when you're doing nothing. When you're sleeping, you're doing nothing. You're just, so that's, for example, brain waves are uncontaminated by sensory input. When you're moving, there's a lot of artifact, you're thinking, etc. When you're sleeping, you go through a kind of an automatic program, and we know that automatic program is disturbed early in a lot of problems, like, for example, Parkinson's disease, Alzheimer, So I think there will be biomarkers, maybe even depression, that we will find by analyzing more carefully the sleep data, that will have some direct predictive value for intervening early to improving the health, both mental and physical, of a lot of people.
Okay, so I think we thank for our wonderful speakers, and we will end this session on sleep. Hopefully tonight you have a good night of sleep.
VOG. And now please join us outside in the tent for the Corporate Technical Showcase poster session and reception. Thank you very much.